標教授。
Ladies and gentlemen, welcome to the Future Science Prize Week. The opening ceremony will begin shortly. Please be seated. Kindly remember to switch your mobile phone to silent mode or turn it off. Thank you for your cooperation. Ladies and gentlemen, the ceremony is about to begin. Thanks to the support of many parties, the Future Science Prize Week has been a great success. We would like to take this opportunity to express our gratitude. Organizer, the Future Science Prize, and co-organizer, the Hong Kong Academy of Sciences. Strategic partners are Hong San Charity Foundation, New Cornerstone Science Foundation, Sino Group, Shangri-La Group, the University of Hong Kong, the Hong Kong University of Science and Technology, Future Innovation Fund. Our partners include 5Y Capital, Olas Capital, Trust Star Capital, Grace Chan, Sanofi, Go FinTech Quantum Innovation, Huangpu River Capital. Fully supporters are Education Bureau, Leisure and Cultural Services Department, Acknowledgement, Culture Foundation, Adrian and Jennifer Jiang Foundation, All Stars Investment, the Bank of East Asia, China Renaissance, Fortrea Capital, HB Antoine, Joint Luck Jam, Pandu Finance, Times China Foundation, 20 Mimo, Alco Lake Capital, Ascendance Capital Partners, Cloud Lake Consulting, Fountainhead Partners, MSA Capital, Seven Toys, Shoucheng Zhang Foundation, Jinghai Investment, Waterwood Asset Management Limited, Relight Capital, Tomokado, Yanchai Hospital, St. Paul's Co-Educational College Primary School, and our supporters are Hong Kong Science Museum, Hong Kong Space Museum, the Hong Kong Young Academy of Sciences, Hong Kong Subsidized Secondary Schools Council, Hong Kong Direct Subsidy Scheme Schools Council, Association of Principals of Government Secondary Schools, the Chinese University of Hong Kong, City University of Hong Kong, the Hong Kong Polytechnic University, Hong Kong Baptist University, Ningnan University, the Education University of Hong Kong, Hong Kong Metropolitan University, the Hansen University of Hong Kong, St. Francis University, Shanghai Engine Fund, Warsaw Institute for Computational Biology, Hong Kong Mainland Students Association, and our media partner, Radio Television Hong Kong, RTHK, our funding organization, Innovation and Technology Commission. Without everyone's support, the event would not have been so successful. May I invite you all give a big round of applause to our supporters, to all our partners to show our appreciation. Thank you so much. Ladies and gentlemen, welcome to the 2025 Future Science Prize Week and the Science Symposium. It is my great honor to be the MC today. I'm Yo Yilang. Hello, everyone. Good morning. Good morning. Wow, today we're so thrilled to be here with many great minds of the year. The Future Science Prize Week aims to promote scientific spirit and pay tributes to scientists, leading the public to explore the forefront of world science with a forward-looking perspective. This year, our program committee sets the agenda and invites domestic and international speakers to ensure a high level of academic content and extensive global perspective of the conference. Now, we're delighted to have Professor Yuk-Ming Dennis Low, President, Hong Kong Academy of Sciences, 2016 Future Science Prize Life Science Prize Laureate, Co-Chair, Program Committee of the Future Science Prize Week 2025, to deliver a welcome remarks. Let's invite Professor Low.
Ms. Lillian Zhong, Mr. Ivan Lee, Mr. Victor Wang, distinguished guests, esteemed scientific colleagues who have traveled from afar, ladies and gentlemen, good morning. It's a great honor for me to welcome you all to the opening ceremony of the 2025 Future Science Prize Week. This event is jointly hosted by the Future Science Prize and the Hong Kong Academy of Sciences. In my capacity as the co-chair of the 2025 Future Science Prize Week Program Committee, I'd like to extend my heartfelt gratitude for your presence here today. We're especially grateful for the presence of Ms. Lillian Zhong, our Acting Secretary for Innovation, Technology Industry, and Mr. Ivan Lee, the Commissioner for Innovation Technology, who has joined us to witness the launch of this annual mega science event. We extend our sincere appreciation to the Innovation Technology and Industry Bureau and the Innovation Technology Commission of the Hong Kong SAR government for the steadfast support over the years. The backing has enabled us to be successfully held in Hong Kong for the past 3 years. Now, Hong Kong has a number of world-class research universities, with 5 ranked amongst the top 100 in the world. Now, we also have outstanding scientific talents and a supportive and rapidly developing environment for innovation. Now, amongst the 46 laureates awarded the Future Science Prize thus far, 6 of them are based in Hong Kong. And so, this event is of particular significance to many of us. Now, since its inception in Hong Kong in 2023, the Future Science Prize Week here has attracted over 80,000 on-site participants, with more than 25 million participate via live streams. Now, this event has become a significant driving force in advancing scientific and technological progress in China and around the world, now helping to raise global awareness of our research capabilities in this part of the world. Now, this year's Prize Week brings together over 100 outstanding scientists from around the world. Now, our goal is to highlight outstanding achievement in science, as well as to promote the spirit of science. Now, we strive to kindle a spark of curiosity of science in people of all ages, especially those in the next generation, to cultivate a love for science and an eagerness to support scientific endeavors and to engage in scientific pursuits. Now, in the past 2 days, we have organized the Enlightening AI Walk and Talk, the Science and Technology Forum, and the 2025 Asian Young Scientists Fellowship Annual Conference. Now, the Future Science Prize Week will have more exciting programs to come on the 24th to the 26th. Now, starting from today, we'll have a 2-day science symposium that brings together top researchers from home and abroad, now focusing on 5 key areas, which are chemistry, life science, physics, mathematics, and computer science. Now, during which time, the scientists will share the latest cutting-edge research results. Now, we'll also feature insights from 3 Nobel laureates, Professor Ariel Warsaw, and Professor Richard Genzel, and Professor David Gross, who will share the groundbreaking work and perspective. Now, in addition, we're also proud to feature a special 10th anniversary session, How to Run a Successful Prize. Now, together with representatives from the Nobel Foundation, the Wolf Prize, Abel Prize, IEEE Awards, and the Tang Prize Foundation. Now, this part will definitely be a highlight of this year's symposium. Now, on October 26th, we shall have a dialogue session in which science-loving young people will have the opportunity of speaking with the Future Science Prize laureate face-to-face. Now, followed by the award ceremony and concert at the Hong Kong Cultural Center that afternoon. That will be the highlights of the week. Now, this year is especially significant because we celebrate not only the 10th anniversary of Future Science Prize, but also the 10th anniversary of the Hong Kong Academy of Sciences. So 10 times 10 is 100. So, and this is actually a powerful symbol of our shared vision to lay a scientific foundation for the next 100 years of human civilization. Now, science is our universal language and the driving force behind human progress. So my thanks for each of you for being here today. So now, let's immerse ourselves in this feast of science to explore, to learn, and together to unlock the future that science has for us. So I wish all of you a most enjoyable and inspiring week. So thank you.
Thank you so much, Professor Low. Please be seated. Now, we would like to invite Ms. Lillian Zhang, Acting Secretary for Innovation, Technology and Industry, the Government of the Hong Kong Special Administrative Region, to deliver an opening remarks. Ms. Zhang, please.
Professor Low, Mr. Wang, Professor Warsaw, Ivan, distinguished guests and speakers, ladies and gentlemen, good morning. It's really my great pleasure to join you all here today at the opening ceremony of the 2025 Future Science Prize Week in Hong Kong. This year marks the 10th anniversary of the Future Science Prize, a milestone that not only celebrates the decades of scientific excellence, but also invites us to look boldly towards the horizon. And I'm very delighted to welcome you all for the 3rd time here in Hong Kong as the host city of this world-class scientific gathering. And so just introduced by our Professor Dennis Low, that the theme of this year's event, Shining a Light on the Future of Science, could not be more fitting. Science is the torch that illuminates the unknown, the compass that guides us through complexity, and the engine that propels humanity forward. The 5-day programs of the Future Science Prize Week will bring together over 100 brilliant minds from around the world to explore the frontier of knowledge, foster interdisciplinary exchange, and inspire the next generation of thinkers and innovators. Scientific progress is a long and winding road. It's a journey that demands vision, perseverance, and collaboration. And so that is why the HKSAR government has made innovation and technology a cornerstone of our development strategy. Guided by the Hong Kong INT Development Blueprint promulgated in December 2022, we have rolled out a series of targeted initiatives and invested heavily in infrastructure, talent, R&D, and industry development to perfect the local INT ecosystem. And I hope that all our initiatives could be beneficial to all of you. Our goal is very clear: to create a fertile ground where innovative ideas can take root, grow and flourish here in Hong Kong, and to help all of you to make your dreams to get realized very soon. Meanwhile, we are also deepening international INT collaboration, as we firmly believe that science knows no borders. Events like the Future Science Prize Week, therefore, serve as vital platforms for building bridges between disciplines, cultures, and generations. Leveraging the distinctive advantages of enjoying the strong support of the motherland and also being closely connected to the world under the principle of one country, two systems, Hong Kong will continue to play its role as a superconnector and a super value adder in fostering international INT collaboration. So, ladies and gentlemen, the Future Science Prize Week reflects the highest standards of academic excellence and global perspective. In just a short while, the Science Symposium will commence with a very inspiring keynote address by Professor Ariel Warshel, Nobel laureate in chemistry. This keynote sets the tone for a week filled with intellectual vigor and visionary dialogue. And so, indeed, beyond the symposium, the Future Science Prize Week offers a rich tapestry of events designed to engage, enlighten, and inspire. So some highlights including the laureates' dialogue with the youth and the award ceremony and concerts. So I hope that you will find it very fruitful and very meaningful, and also that a very great event for Hong Kong. Taking this opportunity, I would like to also express our deepest gratitude to Professor Dennis Lo, to Mr. Victor Wang, to Dr. Harry Shen, and also the organizing committee for their tireless efforts in bringing this remarkable event to life. So let us seize this moment, not only to honor the achievements of our laureates, but also to reaffirm our shared belief that science is a force for good. So let us work together to illuminate the path ahead, and may the light empower us to build a better and wiser world for ourselves and also for generations yet to come. And so lastly, may I wish you all a very rewarding and inspiring Future Science Prize Week 2025. Thank you.
Thank you so much, Ms. Chen. Please stay and proceed to the center of the stage. We are going to have few photos together. Now we are going to invite our organizers and also our guests to the stage, including Professor Dennis Lo. Let's put our hands to welcome our guest, Mr. Victor Wang, Professor Xie Zuowei. Yeah, don't forget your big hands. Professor Yu Jun. They are the backbones of the event. And Professor Mok Ngai Ming. Professor Ariel Warshel. Let's continue to invite our guests. And also Professor David Cross. Professor Rob Knight. Professor Zhang Nim Kwan. Professor Zhou Qilin. Professor Zhuo Ziwei. Professor Liu Xingyuan. Thank you so much. Now we invite the guests on the stage. Maybe we stand closer to Ms. Zhang. And then let's have a look to the camera on your front. And may I invite the guests on the stage one step to the left? 我们向左一步好吗? Okay, so have a big smile. Have a look to the center, please. 1, 2, 3. 1, 2, 3. 1, 2. Okay, one more to the front. 1, 2, 3. 1, 2, 3. And then we have some camera at the left. We can have a look to the left as well. Okay, thank you so much. May I now invite Ms. Lilian Zhang, Professor Dennis Low, and Mr. Victor Wang. Please remain on stage for the next photo. For the other guests, please be seated. Thank you so much. And for the next photo, we are going to invite more guests to the stage. We invite Mr. Ivan Lee. Thank you for joining us. Mr. Patrick Lau Kai Yip. Yeah, continue your big hands. Professor Nancy Yip. Thank you so much, Professor Nancy Yip. And then we also like to invite Professor Zhi Zhiming. Professor Vivian Yam. Professor Timothy Tong. Professor Timothy Tong. Professor Anderson Shum. Professor Lü Aiping. Professor Alice Wong. Professor Alice Wong. Professor Philip Chill. Professor Raymond So. And also Miss Isabella Wong. I invite you all to the stage. Okay, so now let's get ready. And then, may I invite the guests on the stage one step to the left? Yeah, one little step to the left and one big step to science. Yes, let's have a look to the center. 1, 2, 3. 1, 2, 3. 1, 2, 3. Few more to go. 1, 2, 3. Okay, let's continue to have a look to the center. 1, 2, 3. 1, 2, 3. Few more to go. Okay, so all the cameras are ready. Okay, so now we invite Ms. Lilian Zhang, Professor Dennis Low, and Mr. Victor Wang. Please remain on stage for the next photo. For the other guests, please be seated. Thank you so much for your support. Now, I would like to invite the following guests to the stage. May I invite Professor Frank Zhang. Professor Frank Zhang. Professor Douglas Lin. Professor Douglas Lin. Professor Yong Yuk Lin. Professor Lin Hening. Yeah, you can give, if you want to put your big hands, just do it. Professor Zhang Shouwu. Professor Li Jiayang. And also Mr. Zhang Tao. Mr. Zhang Tao. May I also invite Miss Jessica Chan. Miss Jessica Chan. And also Tam Xin Yi. And also, last but not least, Miss Kathy Wu. And I also invite Xia Younan. I can see many participants and young people here. They are all the experts in the industries and also maybe. So we have all the guests on stage. Now let's get ready and then we can have a look to the center. 我们看一下中间摄影师. Let's have a look to the center. 1, 2, 3. 1, 2, 3. 1, 2, 3. One, few more to go. 1, 2, 3. 1, 2, 3. Okay, thank you so much. Thank you very much. May I invite you, please return to the seats. Thank you so much. Today we're so happy we have many guests, our speakers, and also participants joining us. We will now like to have the bigger photo with all of you. So just remain on your seats, and our photographer will take photo from the stage. 好，我哋有請攝影師可以嚟到台上，準備好為我哋影大合照。So everybody, get ready. Don't forget the big smile for those who are wearing a pair of glasses. You can adjust a little bit so you can look even more energetic. Okay. 好，我們準備好，看一下我們攝影師。Let's have a look to the center. Yeah, and most important, don't forget your big smile. So when the photographer is ready, just let me know. So we are going. Okay, we have one more guest to the front. Yeah. Let's have a seat. Okay, is it okay? Okay, everybody. Let's have a look to the center, please. 1, 2, 3. 1, 2, 3. 1, 2, 3. Okay, one more. Few more to go. 1, 2, 3. 1, 2, 3. So now have thumbs up. 点赞, thumbs up to boost up the energy for the symposium. 1, 2, 3. And A, B, C, D, E, cheers. Yeah. And a few more to go. Yeah, keep up the energy. Energy need to keep up because we are going to have few days as well. Thank you so much. Thank you very much. Thank you. And third, we are so honored to have Professor Ariel Warshel, Nobel Prize laureate in Chemistry 2013, member U.S. National Academy of Sciences, Fellow, the Royal Society of Chemistry, Distinguished Professor at Lodge School of Medicine, the Chinese University of Hong Kong, Shenzhen, CUHK Shenzhen, Director, Warshel Institute for Computational Biology, CUHK Shenzhen, to deliver a keynote speech about perspective on the past and future of computational biology. Let's welcome Professor Warshel.
How does it work? Just a minute. How do I move backward? How do I move backward? No. You can see here. What? I know. But okay. Good morning. I am happy to see so many distinguished people here and also young scientists. And I will try to provide my perspective on the past and the future of computational biology. I will start essentially the whole talk. The whole talk will consider the synergy and also the difference between approaches which are based on physical treatment, which is really causation, and on the use of AI, which is correlation. And I will start with physically based approach in computational biology, and also start with the issue of enzyme catalysis. Now, as all of you or most of you know, enzymes are proteins that catalyze chemical reactions. And they do it by reducing the barrier for different rate-determining steps. So understanding of enzymes require the ability to use physical models that actually describe the key processes. And again, enzymes are a large part of the protein in our body, and they do most of the critical actions. So the main approach to study how enzymes work is this combined quantum mechanical molecular mechanics approach, where we restrict the treatment of the bond breaking to quantum mechanical approach, which should not be used for the whole enzyme because they are too expensive, and describe the rest of the enzyme by classical force field, ball and springs, and electrostatic charges. Now, this approach became very effective in the last, 50 years. And just my favorite example is studying of the enzyme RAS, which catalyzes GTP hydrolysis. This is the GTP. And it activated when it bound to another protein called GAP. So, could we run this movie? So we could use this QMMM approach to simulate the catalytic reaction. In this case, a water molecule attacked the phosphate by first transferring a proton and then by OH minus, and it get help by a magnesium ion, which is shown here in green. Now, the key challenge is actually to get the chemical barrier for the enzyme and for different mutants that could actually cause cancer. And this approach allows you to do it with a reasonable accuracy. And in fact, this approach allows you to study many enzymes. What you see here in blue are the barrier for the reaction without the enzyme. In red is the barrier with the enzyme. And in general, we found that this catalytic effect is mainly due to electrostatic stabilization of the transition state. So you could use this physically based approach to study the main catalytic effect in enzyme and to understand its origin. Now, another question which now become very popular is, could you use your knowledge to design or to improve enzymes? And there are two main approaches. One is experimentally directed evolution, where you just keep choosing in solution the best enzyme in several rounds, and the other is physically based approach. Now, with physically based approach, this is directed evolution, but with physically based approach, what we do, we on the computer mutate different residues and calculate the free energy change of the reaction upon such mutation. Now, it works reasonably well. Here is the case of haloalkane halogenase, but it's not sometimes good enough. Note that when we study the whole catalytic effect, it's a very large number, so small errors do not count too much. Here we look on small effect, and we need to be relatively accurate. So in the last 10 years, we try to improve the physically based approach. The favorite system is this CAMP eliminase, which was designed from scratch and improved by directed evolution. Again, we seem to do reasonably well, but when we try to get the best mutant, the one which makes this enzyme the fastest, even the use of massive scanning, creating many, many mutants, seems to give reasonable result. The blue region is where we have the fastest mutant, but we could not get exactly the observed effect. And we still have, and we are still even struggling to try to get better result. So this is the case of physical-based effort, about 50 years. We are doing okay, but not good enough. So the question is, can we get some help from AI? And the direction, okay, first just a footnote. A long time ago, in 1975, we used coarse-grain model to try to study protein folding. We were able to show that protein could actually fold on the computer. We even got reasonable structure, but this approach and a related continuation could not produce from sequence the exact protein structure. And then come the quote-unquote surprise. Using AI, people were able to generate the AlphaFold. Essentially, it was the Nobel Prize last year, and to get very good results for protein structure prediction from sequence. Basically, to get more or less the ultimate force field. Now, this approach has a huge hype. A lot of people think that it will solve anything in biology, but actually there are many problems that it have not solved. In one of the direction, which is continuing what I told you before, is enzyme catalysis. So we tried to use an idea that was used before in studying protein fitness, to use maximum entropy and to see if it helps in creating correlation for enzyme catalysis. And just show you what happened. Okay, so just in short, maximum entropy is the idea that you look on many enzymes and you try to find the likelihood that a given mutation will appear, the probability of a mutation. So it makes a lot of sense because you look how many times each mutation appears. Now the question is what this information has to do with physical properties like catalysis. So we took different enzymes, and without pretending that we don't know anything on catalysis, we plot the calculated maximum entropy and the observed catalytic effect. Again, the approach does not have no information about catalysis. yet we found very nice correlation between maximum entropy to catalysis. These are several examples. The larger is the maximum entropy, the less is the catalytic effect. These are 3 enzymes. We found out that this works best if we look on mutants not far from the active site. This table we jump, this we jump. We also found that this approach even works for enzymes which were not designed by evolution. And very significantly, we found also that the protein stability is correlated with the maximum entropy, essentially correlated very nicely. So we have here a correlation for activity, for K cut over Km, and for stability. We are not sure why it works. Essentially, I argue with my co-worker. One possibility is that when you have the landscape of the sequence and the activity, we just stuck in a given region and we follow the trend. My co-worker believes that this is more fundamental, but again, we don't know why it works. So we could, in principle, predict activity and stability. We could find mutation that work faster than the wild type. We could find protein which are more stable than the wild type. And essentially, we demonstrate this idea by designing the allogenous which is faster than the wild type. Now, here we have a trick. It's really, really hard to compete with the whole activity of the wild type because evolution spent billion years or less to do it. But for specific steps, like the SN2 step in the allogenous, we just use our correlation and find protein, this one, which is faster than the wild type. We predicted it and then verified it experimentally. So there is something interesting that you could do with this maximum entropy. We even tried this approach on bioluminescence, where we have this cofactor luciferase that emit light after chemical reaction with oxygen. And we actually first studied the action of luciferase by this QMMM approach, and were able to understand its activity, and we plan to use this approach to find better mutant. Now, what we mean better is that it will emit farther to the blue, because these creatures live in the ocean, and you want blue or UV emission, so it will be not blocked by the water. So we use maximum entropy, found correlation between maximum entropy to activity, again, without having any idea why this has happened. We also found, you see difference between groups which are near the active center and farther away, so it works better near the active center. We also found correlation For stability, again, stability is correlated with maximum entropy. But the most impressive finding was that we found correlation with the wavelengths. So when you go to the blue, we know which mutant will take you farther to the blue, and this is the direction for which the enzyme evolve. And we even suggested several mutations that seems to work. Okay, so now we go to, I think, more challenging issue and try to see how and if this AI work. So the issue is drug resistance. It's a major problem, and we have been working on it for a long time with really medium or very small success. We were looking for what is called the vitality, which is based on the following. The pathogen want to not bind the drugs that we have. So it want to have large Ki. But when doing so, it also want to retain its original activity, its original catalytic effect, so it cannot have too small K cut. So what we want to monitor and to calculate is the vitality, which is the ratio between Ki time K cut over Km for the mutant to the corresponding value at the wild type. So we want to find drug that will reduce vitality. The pathogen want to have high vitality. So we were trying to calculate vitality for some system. This is HCV for different inhibitors. We calculated the binding. We calculate the catalysis. Maybe I show you the opposite slides. And from this, we obtain the overall vitality for different drugs. Now, this looks nice, but it's clearly not good enough to use it for drug design. So we got stuck. One of the reasons that we got stuck, we also have no ideas which mutations the pathogen will do. What will be the next step of the pathogen? We know it wants to maximize vitality, but there are other factors in the sequence. So again, in desperation, we move to AI. This is recent paper, which probably appeared today in PNAS, where we took the huge data set of HIV protease and tried to correlate it with this maximum entropy. We got very nice correlation where you could say that the drug with the lowest vitality here is the best drug, but unfortunately, we also found out that you get the same correlation looking at the number of mutations, which means it's really meaningless correlation, though it's very nice, and you could use it only after you've done the experiment. This is expected. See, this HIV protease has huge mutation rate, so we also done it for enzymes which is less mutated, and we found some correlation which is unique to maximum entropy and could help us if we want to simulate the step-by-step resistance. but still no huge success. Now come, I think, one of the nicest examples, so we will try to go relatively slow. This is kinosine. It's a myosin-type system which walks in one direction and carries a load. And one of the questions that we were asking in the last 7 years is why it walks in one direction. And this question dramatized here. I mean, if you have two equal legs, there is no reason that you will not walk in the same speed in both directions. But in these proteins, one direction is good, the other is not good. So the question is why? And this question essentially was almost never asked and still not asked in the field. I don't know why. And after about 3 papers, we realized that what determined the directionality is not any dynamical or kinetic effect, but simply the rate-determining barrier, which appear to be different for the forward and backward direction. So when we look more carefully, this is myosin 5, we found that the one which goes forward has easier exit of ADP, which is the rate determining step, than for the ones that go backward. We published several papers on it, and recently we start to use it to medical questions. For example, there is a major heart myosin, which if it does not work, you eventually could die. And we try to look on the effect of different drugs on the rate determining step, which in this case is phosphate release. We do it by calculating the free energy barrier for the release of the phosphate. And we always find that with the drug, the rate determining step become higher. With the mutations, the rate determining step become low, and it does not, and it's not anymore rate determining step. With the drug, by the way, this this blue should be orange, so always the drug helps to increase the barrier and to make it more similar to the original rate determining step. The last system that we did was the kinosines that you show in the movie. Again, it is a myosin-type system, but the nice thing about it is that there are mutations that makes it go backward, and there are mutations that make it stop walking. So again, we used this free energy calculation. Unfortunately, this is the wrong slide because they did not let me to bring my computer. But we have a very nice slide for the different mutants which reproduce this amazing effect. You see here, there are mutants that go even in the opposite direction, and there are those which just don't move anywhere. So this is what physically based approach could do. And also with this physically based approach, we found that the barrier is correlated with the protein stability. When it's more stable, it's harder to release the ADP. and therefore the ADP step is still rate limiting. Now, here comes the surprise. The guy who does the maximum entropy collaborated with the person who worked on the myosin, and amazingly, they found very nice correlation between maximum entropy to the velocity, and later between maximum entropy to stability. So basically, we have a case where the physically based approach gave you the explanation, and the maximum entropy gave you the correlation, except that it was done where we first done the physically based approach. So I think this is kind of promising for maximum entropy. And I will finish by jumping this. This is design of covalent inhibitors. But what I want to say is that we are competing with our physically based approach with AI, different deep learning approach, where people try to find the correlation. We believe, however, that combining AI with physically based approach could be the direction of the future. Of course, a bleak future will be where we will correlate everything and have no understanding, which is not good for scientists like us who want to understand why. Essentially, we were always trained to believe that understanding is the key to progress, but hopefully, understanding still has major place in science. So thank you very much.
Thank you so much, Professor Warshall.
Okay.
Thank you so much, and please be seated. Thank you very much. The upcoming section will be chemistry for sustainable development. I would like to introduce with you Professor Xie Zuowei as this section's convener. He is Chair Professor, Sylvan University of Science and Technology, member, Chinese Academy of Sciences, member, the Hong Kong Academy of Sciences, fellow, Chinese Chemical Society, fellow, the Royal Society of Chemistry, member, Program Committee of the Future Science Prize Week 2025. Let's give warm welcome to Professor Xie.
Thank you. Good morning, distinguished guests, ladies and gentlemen. A very warm welcome to you all. I'm Zhuowei Xie. It is my great honor to serve as your convener this morning and to officially open our section, Chemistry for Sustainable Development. We are living in a pivotal moment for our planet. The challenges of climate change, resources scarcity, and environmental protection are immense. But in this room, we share a common understanding that chemistry is not just part of the problem, it is absolutely fundamental to the solution. It is a science that will provide new materials, new energies, new drugs, new processes to build a cleaner, healthier, and more sustainable future for all. And to guide us through the frontier of this vital work, we are extraordinarily privileged to have with us three of the most brilliant minds in the field today. They are here to share groundbreaking research that is pushing the boundaries of what is possible. Each of the speakers will present for approximately 30 minutes. Following their presentations, we will transition into a panel discussion, offering you a chance to engage directly with them and delve deeper into these fascinating topics. But before we begin this scientific journey, please allow me to introduce the pioneer who were our guiders. Our first speaker is a scientist whose work has fundamentally reshaped the landscape of molecular synthetic chemistry. Professor Qilin Zhou of Nankai University, a member of the Chinese Academy of Sciences. He is a 2018 laureate of the Future Science Prize in Physical Science and the 2019 recipient of the first prize of the National Nature Science Prize. He discovered a class of chilospirocalasts so revolutionary in that work that these compounds are now known simply as stochastic. He will be sharing his latest breakthrough research today in a keynote lecture entitled Asymmetric Carbon Insertion into NH Bond. Our second speaker represents the brilliant and innovative future of our field. We now turn to Professor Ziwei Zuo, a rising star from the Shanghai Institute of Organic Chemistry, Chinese Academy of Sciences. Professor Zuo is already making waves with his groundbreaking work. His potential and creativity has been recognized with the prestigious honors, including the Explorer Prize in 2025 and the Chinese Academy of Sciences Young Scientist Excellence Award. He will illuminate his path for us in his talk entitled Eliminating Inert Bond, Ligand to Metal Charge Transfer Catalysis at the Frontier of Sustainable Chemistry. And finally, our third distinguished speaker is a scholar who has mastered the art of taming some of the most reactive and challenging species in chemistry. He is Professor Xinyuan Liu, a chair professor at the Southern University of Science and Technology. Professor Liu is a trailblazer in the field of radical chemistry, renowned for a high activity but difficult to control. His work has been instrumental to imposing precision and symmetry onto this wild molecular entity, opening up entirely new pathways for synthesis. The significance of his contribution has been celebrated with awards such as 2023 Explorer Prize and Chinese Chemical Society BASF Innovation Prize. Today, he will take us to the cutting edge of an exciting field, presentation on copper chilo-anionic ligand catalyzed initial selective radical reactions. Now, please join me in welcoming our first speaker, Professor Qilin Zhou.
Thank you, Professor Xie. It's my great pleasure to come to Hong Kong to celebrate the 10th year anniversary of the Future Science Prize. I was asked to talk about the chemistry recently achieved in my lab. In the Shanghai celebration event, I talk about the hydrogenation reaction. Today, I would like to talk about the largely hydrogen bond insertions, because my field is asymmetric catalysis that deal with the chiral molecules. But actually, we know the chiralities is widely exist in nature in different metal levels. Actually, in all levels of the metals, you have the chiralities. Big like the labular, small like the DNA molecules. In all levels, actually, you have chiralities. But for the chemistry, we are most interested for the molecular levels of the chiralities. Why? Because the chiral molecules have two different enantiomers, and those two different enantiomers have different properties, mostly have different bioactivities. For example, the aspartame. Now we eat that every day in your coffee, in some sugar, some ice. You have this aspartame as the sweeteners, because almost all us like sweeter. But if you eat much sugars, you will get a problem. But this aspartame, this molecules is peptide, is healthy, but it gives you much sweeter tastings. It's almost 200 times sweeter than the sugar. But another example is not present. It's a disaster. In former time, we didn't know the enantiomers of the chiral molecules have different properties. And we use, actually, the pregnant women use this thalidomide to treat the pregnant reactions for the pregnant women. Actually, these molecules has two enantiomers. One is the sedatives, is the hair of the woman. But another one can cause fetal malformations, because we didn't know that. At that time, we used a mixture of these two enantiomers, so it gave us a disaster. And after that, the FDA or most that agency in different countries had the rules for the chiral drugs. You must use one enantiomer. That is the medicines. You cannot use the mixture of these two enantiomers. So now in the marketing medicines, you have more than half of them are chiral enantiomers, chiral molecules in the optical enantiomers. And in the developing medicines, you have more than 70. Other 30% mostly are achiral, without chiralities. Or these examples of the chiral medicines we use. For the synthetic chemist, we need to develop the method to making these chiral molecules in the enantiomerically pure form. That means how we can make just one isomer without other isomers. Those are methods we use to prepare it. You can use the racemic compounds, use a mixture of these two enantiomers to isolate one. We call it the chiral resolution, or you can do some asymmetric synthesis, starting from a chiral molecule to make chiral molecule in enantiomeric pure form. That means you make one enantiomer without other enantiomers. If you use catalytic amount of the reagent, that means you are doing asymmetric catalysis. Of course, you can use the artificial catalyst. You also can use enzyme. That's a biocatalyst. Because in this asymmetric catalysis, you only use a small amount of the chiral catalyst. You can make a large amount of the chiral product. So there is the asymmetric amplification in this process. This is why in last few decades, this area developed very fast. Many chiral catalysts has been developed. And we developed one type of the chiral catalyst, lambda spiral catalyst, with these core structures. This is spiral by enden structures. With these structures, now we can make large amount ligand. With this ligand plus different metals, we can make almost unlimited number of the chiral catalysts. Actually, the spiral catalysts have been employed in over 70 or 700 asymmetric reactions. And in MINUP, we have done this many reactions, including carbon-hydrogen bond formations, carbon-carbon bond formations, and carbon-hydrogen bond or hetero-atom bond formation reactions. Today, I just talk about one reaction, is the nitrogen-hydrogen bond insertion. And in this hydrogen bond insertions, actually, it's a carbon insertions. We know the carbon is the intermediate in the organic synthesis. But the free carbon is too active. Too active means no selections. If some reactions have no selections, there's useless in the organic synthesis, because in the organic synthesis, you must do some selective reaction. But free carbon is too active, is less selective, has less application in the organic synthesis, but later on, the metal carbon was developed, but the metal carbon still active, but not that active as the free carbon. So it has some selections in the organic synthesis. So metal carbon have been applied, have been used in the organic synthesis in last few decades. Of course, you have the two types of carbon, Fischer or the Schrock carbon. But in the asymmetric catalysis, using carbon intermediate, and many reactions have been developed, and many scientists have achieved great success in these areas. But reactions like the cyclopropionations and the cyclopropionations and ethyl reactions, or the carbon-hydrogen bond insertions. In all these reactions, they achieved very high initial selectivities. But we are interested in the carbon insertion to the heteroatom hydrogen bond, to making carbon heteroatom bond. Of course, with the initial selectivities. So we are interested in the reactions of insertion to the nitrogen hydrogen bond, oxygen hydrogen bond, sulfur hydrogen bond, or boron hydrogen bond, many heteroatom hydrogen bond insertions. Today, just talk about the nitrogen hydrogen bond insertions. But before us, some NARP already tried these reactions. For example, McCurry used the dirodium catalyst to catalyze intramolecules nitrogen hydrogen bond insertions. He achieved about 50% yield and less than 50% initial selectivity, EE value. Jorgensen used the carbon complex with the dioxazole ligands to do the intermolecules nitrogen hydrogen bond insertion reactions. He achieved also around 50% EEs. And when we developed spiral bisoxazole ligand, we want to try these reactions. In the beginning, we used the copper halide, chloride, and some neutral carbon precursors. We did achieve the very low initial selectivities, as the other people got. But when we try the ionic carbon precursors, and we found these reactions can give us a high initial selectivity, of course, with the spiral catalyst. The best results was achieved with these very bulky anions. This means this reaction needs very bulky anion, very weak coordinating anions. This is why the buff give us best results. Of course, we screen lots of the carbon precursors, but finally we found this one is the best for these reactions. Of course, we studied a different type of the spiral ligand with different chiralities, because in this spiral bisoxazole ligand, we have 3 chiralities. So we must study the combination of these 3 chiralities. The combination of the chiralities SSS is the choice of the catalyst. And in the beginning, the review always asks us to make a comparison with other type of oxazole ligand, but we did. And the bisoxazole ligand with these bilepsal structures or the Evans bisoxazole give us much lower initial selectivities. Of course, a different type of the aromatic amines can be used in these reactions. And Professor Greg Fu and Xiaoming Feng also did the reactions afterwards by using the copper catalyst. They achieved high initial selectivities also, especially the Greg Fu can use this amide. This gives us an advantage because this amide can be deprotected after reactions, getting or obtain the amino esters with the free amino groups. And we studied the structures of the catalysts because almost all the chemists believe the properties come from the structures of the catalyst. In other words, the structures determine the properties of the molecules. So we studied the structure of the catalyst. We try hard to make a single crystal of this catalyst. We spent a few years. Finally, we got the crystal. And we found this catalyst very special. It's different from other type of the catalyst because other copper complex used in this carbon transformation, there always is the complex of the one copper and one ligand. And our catalyst is the two copper and the two ligand. And the coordinate in this symmetric patterns. And if we take the one part and then look at if the reactor with the precursors of the carbon and generate this copper carbon, and then give us this product. So now we understand these reactions happens from these models. And you may ask, your catalyst is a dimer. That means the stable catalyst is a dimer. Is the active catalyst in the reaction cycle, catalytic cycle, is still a dimer? We check this nonlinear effect. We found there is a nonlinear effect in this reaction. That means the active catalyst still contains two ligands. Otherwise, it will not give us nonlinear effect. And we also check the catalyst by mass in the reaction solutions. That show us the catalyst is still dimer there. And we also did the kinetic study of this reaction. We found this reaction is the first order for the catalyst, the zero order for the diazole and the adenine substrate. And this is the mechanism we proposed. The first step is the generation of the metal carbene, and then the attack of the adenine to this electron deficient carbon of the carbene, generate this metal associated elite. And if the proton migration happens at the same time, the chiral catalyst leave. If these two processes happen at the same time, and we can get the chiral product in high initial selectivity. If the catalyst part leave before the proton migration step, we cannot get initial selectivity. So because we got high initial selectivity, so we believe our reaction happens through this process. And now many subjects cannot give us a high initial selectivity. Let's show us probably they go through this way. It goes this way. And the question is, if the reaction goes through this way, can we control the initial selectivity? And we think about that. We thought, if we can control the initial selectivity in the proton migration step, probably we can control the initial selectivity in this way. We don't need use the chiral catalyst to control the first step, but we can use the chiral catalyst to control the next step. If we can do that, we can use many types of the other subjects. As I mentioned in the beginnings, if I use the carbon complex of the spiral with oxyacetylene, we cannot use the amide as the graphic used. But if we can do this way, we can control the initial selectivity in the second step. Probably we can use the amide or other type of the substrate. So we try this reaction. The first, we use the achiral rhodium catalyst to generate the metal carbene. And this step, we don't need to control the initial selectivity. But the second step, we use the spiral phosphoric acid to control the initial selectivity of the proton migration step. And after a modification of this spiral phosphoric acid, we finally can control the initial selectivity. But this E levels is not very high. And after modification of the achiral of the dirodium catalyst, we can increase the initial selectivity to the 92%. But interesting, we already know this dirodium catalyst achiral, it should not give us influence for the controlling of the initial selectivity. Why? With a different group, it gives us a big improvement for the increased initial selectivity. That's interesting. Because we use the two catalysts, one is achiral, one is achiral. So we have to use, study the ratio of these two catalysts. We can use more phosphoric acid catalysts. We cannot use more dirodium catalysts. If we use more dirodium catalysts, it generates the metal carbon too fast, and that one can go the proton migration step without chiral phosphoric acid. So we must use a little bit more phosphoric acid catalyst. And asked by the reviews, we also make comparison with the bilateral phosphoric acids that give us a much lower initial selectivity. Of course, different diazo compounds that carbon precursors can be used in these reactions. And this is a mechanism we proposed. And with this mechanism, now we can understand why different achiral catalysts still give some influence to the controlling initial selectivities, because in this step, this dirodium part is still there. So this is the reason why we need a very bulky dirodium achiral catalyst. Of course, this is normal kinetic cycles for these carbon insertion reactions. With this two methods, we already solved the nitrogen hydrogen bond insertion with aromatic amines amide. But now the question is, how about the aliphatic amines? Because we have much more the aliphatic amines compare aromatic amines and amide. But the question is, this aliphatic amines is more basic, is more nucleophilic, and it may destroy our catalyst. You see, if this aliphatic amine used, it could destroy our catalyst and give this free elite. But can we control this step? Probably. So we try. And now we cannot use the dirodium catalyst because the dirodium achiral catalyst can be destroyed by the aliphatic amines. And we cannot use a normal carbo complex, achiral complex, because it also can be destroyed by the aliphatic amines. But finally, we found those very bulky tridended ligand can protect the carbon catalyst from the attack of the aliphatic amines. You see, if we use that, oh, cannot use, see the last lines, and with that we can achieve the reaction we want. But we didn't use the achiral, we did not use the chiral catalyst to control the next step. And now we need to study which chiral catalyst can use for this reaction. You see, this time the spiral phosphoric acids or other type of the catalyst for the proton migration step cannot be used. You see, all of them give us either racemic or the very low EEs. Only this chiral, this Sia union can give us about 50% EEs. And then we try different type of the precursors, and with the bulky acid group, and we can achieve much higher initial selectivity. And then now we found with this very bulky copper achiral catalyst plus chiral Sia we can get a high EE. And then we study different chiral Sia catalysts, we can increase the EE to the 90%. And now we can use different type of the aliphatic amine to do these reactions. Okay, this is subject scope. It's a different type of the precursors we can use, different type of aliphatic amine we can use. And why this can work? Please remind me if time is. I didn't see the time in there. 2 minutes. Oh, sorry. You see, in this NMR structure shows us that ligand can protect this carbon from the attack of this amine. Aiding this one, the NMR, this proton has now changed. If I aiding this one, and this proton can shift. This means this ligand can coordinate to these carbons, and aliphatic amine cannot coordinate. This coordination of the Sia to the carbon is very important. That's the secret for the reaction success. You see, the pKa of this catalyst increased very much by coordination of this Sia. You see, and the acidity of this one increase. So this is why this catalyst can catalyze the proton migration of these reactions. Okay, this is the mechanism drawn by Jacobson. As he said, this catalytic 1-2 punch is with this coordination of these Sia and this, with this one, is increase this acidity of this, and then helps this proton migrations and generate this product. So I think I cannot talk another stories because the time limitations. And actually, after this aliphatic amines, we think about can we use ammonia? Because it's ammonia, it's much difficult to control the initial selectivity of the reactions in many reactions. But in these reactions, finally, so as quickly. Finally, we found with this catalyst, and we can increase the acidity of this even higher. You see, with this increase of the acidities, we can solve the problem in the ammonia nitrogen hydrogen bond insertion reactions. So I go quickly. Okay. Oh yeah, I just go through. So with almost 18 years effort, finally we solve the nitrogen-hydrogen bond insertion for all the amines, aromatic, aliphatic, amide, and ammonia. Finally, I want to thank my colleagues and students for their creative work, and also would like to thank this funding agency for the support. And thank you.
Yeah, thank you very much, Professor Zhou, for your beautiful work on the catalytic synthesis of ammonium compound, which continue to push the boundary of what it is possible. So now we want to invite our second speaker, Professor Ziwei Zhuo, on the stage to share his exciting chemistry. Ziwei, please.
Thank you, Professor Xie, for the kind introduction and also the very generous invitation. Truly an honor for me to attend this science symposium today. And you probably could feel the pressure on my shoulder right now, speaking after the titan in our research field. Professor Zhou is always the role model that our younger generations always look up to. And I'm truly excited to be part of this Science Prize Week. Personally experienced the joy and the passion when we celebrating the achievements of great science. I was trained as a synthetic chemist, and nothing more have made me more prouder than that. So chemical synthesis have contributed to all the molecules, materials that help us to advance human society. Over 90% of all chemical processes rely on catalysis. So from the fuels in our cars and to the medicines we take. And there are statistics to show that about 1/3 of the GDP is contributed from catalytic process. So catalysis is truly the invisible engine of our modern society. So this is a typical scenario where catalysis is taking action. So on the right side, showing a classic transition metal catalyzed processes where we make acetic acid. To the general public, if you have trouble recognizing its chemical name or the structure with this formula, you probably have tasted a lot of this. It's the main component of vinegar. It goes easily or goes perfectly with seafood. So in industry, we are making this basically from two toxic materials, methanol and carbon monoxide. You probably don't want to taste either of those. But simply mixing those two abundant or inexpensive materials, no chemical transformations will happen simultaneously. This is where we have to overcome a significant amount of activation energy, where chemists tend to call high activation barrier. So we have to develop elegant catalytic processes where we try to insert or activate this CO bond to generate methyl iodide as the intermediate, where then rhodium metal comes in to insert into that, then to couple with carbon monoxide to form the CC bond. So as a matter of fact, most chemical processes rely on noble metal catalysts, such as palladium, rhodium, or iridium. And to overcome that significant activation barrier, we have to enforce like high temperature or high pressure conditions. And most of the time, you tend to generate large quantities of acetic waste. So it will cause a lot of ecological burdens on us. Of course, synthetic chemists have realized this challenge in sustainable synthesis, how to cut down cost, how to reduce waste and energy consumption. So nature, on the other side, are constantly making chemicals in their factory, in living cells. So in the keynote speech, Professor Washoe has shown lots of exciting examples in enzyme catalysis. What I show here is the ultimate model of green and sustainable synthesis in this photosynthesis system, where you can leverage carbon dioxide and oxygen and water as the building blocks to make sugar. So, of course, nature involved so many years and come up with a rather complicated system that allows it to leverage photoexcited electron transfer and charge separation processes. So basically conduct chemical transformation, especially electron transfer at excited states, then bring down the activation barrier, allows the operation to take place under ambient conditions. So us synthetic chemists, of course, can take an important lesson from this. But we are certainly not the first one to look at this perspective. Almost 120 years later, earlier, a pioneer in Italy have already started to take action. So they found out that if we were to put a solution of this yellow compound on the left side in a glass flask and put it on the balcony, and after a whole summer, it can be converted in a rather complicated polycyclic product. So Chamichian was really a pioneer to initiate the photochemistry. And they are true visionaries, because I think probably over 100 years ago, walking down this balcony, look at their amazing results, they probably have to thinking chemical processes would look very different in the future. To quote them word by word in the article published in 1912, they are thinking there will spring up industrial colonies without smoke and without smokestacks. So forests of glass tubes will extend over the plains. Instead of this will take place photochemical processes that have been the guarded secret of plants. For life and civilization will continue as long as the sun shines. These are truly beautiful words. And even AI can, based on these words, to create a picture. But of course, 100 years later, this goal has not been achieved, not yet. To understand why, we probably need to go behind the reason of this chemistry, this exact excitation mode. Because you see, the physical chemicals we use, like alkenes or alcohols or ketones, they only have very simple functional groups, CH bonds, CC bonds, or double bonds. And those type of bonds tend to only absorb high energy UV light due to the large HOMO-LOMO energy gap. After excitation, they tend to form like triplet states, which are rather reactive and cause a lot of reactive pathways. For synthetic chemistry, it's truly challenging to control them. And if you try to excite the CH bond and make a photochemical transformation, chances are you are going to excite the CC double bond or CO double bond in the solution. So basically, this non-selective excitation pattern will cause a lot of challenging in selectivities. So almost like 50 years later, when synthetic chemistry started to merge photons with transition metal photocatalysts, we start to see a viable solution. They start to take this photochemistry to a different level, open a new area of limitless potential. So synthetic chemistry started using like polypyridine ruthenium or iridium complex as photocatalysts, because those photocatalysts can absorb visible light energy through a metal to ligand charge transfer excitation processes. Those processes tend to generate a long-lived, a rather stable triplet state, then itself can undergo single electron oxidation reduction or energy transfer activation patterns, allow us to build elegant catalytic cycles to achieve selective activation of our organic molecules based on redox potential or triplet energies. But not so many metal complexes can absorb visible light and have a relatively long excited state. So this is where we started thinking. And we noticed there's a different type of excitation mode has been previously reported in the literature. The electrons will flow the reversible way. When excited, the electron from the filled ligand orbital will be promoted to the empty orbital of the metal center. It's called ligand to metal charge transfer excitation. One peculiar feature of this excitation mode is that it tends to promote the coordination bond homolysis, leading to the generation of a reduced metal center associated with oxidized ligand center radical. Basically, your photoactive species have been turned into two different parts. And for people who are familiar with catalysis, this is truly not a good thing to develop a photocatalyst. Because the lesson we learned in the past is that we have to have a long-lived triplet state or long-lived excited state allow us to interact with organic molecules. So we actually found a simple solution to turning this decomposition into catalysis. We took a simple lesson from transition metal catalysis, where that most of the time, the active species are generated in situ through in situ coordination, either ligand and metal or substrates between the metal. So if we were to merge LMCT excitation with in situ coordination, LMCT excitation, and homolysis, we could convert the transiently coordinated hydroatom functionality into the open shell radical intermediates. That would help us to address the selectivity challenging in the generation of radical intermediates. And since LMCT excitation has been commonly reported for a variety of high-valent transition metals, especially those earth-bound metals such as cerium-4, titanium-4, iron-3, and cobalt-2, that gave us a very good chance to develop more sustainable photocatalysts. So over the last 3 years, we also realized that LMCT catalysis not only gave us a straightforward activation mode to generate radicals, it also gave us a versatile catalytic platform to us to merge one electron open shell activation modes with two electron transition metal mediated processes in a single catalytic framework using one metal catalyst. So based on this design blueprint, our research group over the last 10 years have mainly focused on two things: the selective activation of sp3 stretch bonds in feedstock alkenes, and the selective cleavage and functionalization of sp3, sp3cc bonds in feedstock chemicals, both of which are recognized as grand challenging in transition metal catalysis. So we managed to leverage hydrogen atom transfer elementary steps and the radical mediated bond decision steps, then to achieve selective transformations of these inert bonds, which previously have been recognized as the molecular framework. We're especially interested in developing new catalysts or new catalytic transformations. We also try to demonstrate scale-up applications using continuous flow. We always try to dig a little deeper into the mechanistic understanding than to guide us to the design of more efficient catalysts and intriguing transformations. And over the last 3 years, we have also taken the data-driven automation approach, trying to accelerate the optimization and the discovery of new transformations. So throughout this talk, I will try to share two most recent research stories. And the first one begins with the methane challenge. So methane, this CH4 molecule, is the simplest organic molecule and represents the most fundamental unit of organic matter. It's commonly recognized that in energy-rich resources with vast natural reserves. It's primarily utilized through combustion to produce heat or power and serving as a cornerstone of the modern energy landscape. In addition to that, enormous reserve of methane also exists in the form of gas hydrates. It exists in the very deep ocean and high pressure and low temperature. Methane and water tend to form a cluster molecule. It's called this combustible ice. So we can easily say that beyond its role as a fuel, methane serves a valuable carbon feedstock, offering unique opportunities to sustainable chemical transformation and carbon resource utilization. but it's truly a challenging task for synthetic chemists. So if you look at this simplified molecule, it only has 4 CH bonds. The molecule is highly symmetrical. And the matrix that qualifies the activity of the CH bond is called the bond dissociation energy. And for methane, is at the top of the chart, 105 kcals per mole. Remember that number. And based on the ionized potential and the proton affinity, it tells us pretty much nothing you can do trying to do a redox or a deprotonation process to try to activate this inert molecule. So this low intrinsic reactivity had made this molecule as a grand challenging in this field, and it has been recognized as the holy grail of catalysis. But this low reactivity has also brought up a different challenge in selectivity. And allow me to demonstrate using these simple transformations at the bottom of this slide. So methanol is a valuable chemical, it's a liquid. And if you look at the chemical structure, you will realize methane and oxygen have all the ingredients that you can use to make a methanol: carbon, hydrogen, and oxygen atoms, right? But if you look at deeper, you will realize there's a serious problem. Because the CH bond of methanol is 10 kcals molar per weaker than the CH bond of methane. So if you ever find a catalyst that can abstract or activate the CH bond of methane, once the first molecule of methanol can be generated, the catalyst will immediately take the hydrogen atom from this activate product. So it will keep going and going. So even if you have not performed any chemical transformation, I'm pretty sure you have done this experiment already if you ever cooked in the kitchen. So we all know that the main product coming from this reaction is carbon dioxide and sometimes carbon monoxide. So synthetic chemistry have endeavored trying to find a viable solution to make a methanol directly from methane. And what's shown here is a classic Shilov process, where you can use in sulfonic acid, a strong acid, and also oxidant, and to make, generate methanol in a selective fashion. Of course, you can produce SO2. So since it's a strong acid here, it can protonate the OH of the methanol, or it can react with the hydroxy group here to form a sulfonate, therefore to deactivate the CH bond in the product and making methanol selectively. And with the advancement of transition metal catalysis over the last few decades, there's significant advancement in the direct CH activation of methane using a variety of metal catalysts. And what's shown here represents the latest achievements. 2 research groups in the States managed to achieve the CH boronation reaction with high selectivity. They have to use in rhodium, ruthenium, or iridium catalyst. They have to use in high temperature for them to overcome the activation barrier, and sometimes have to suffer from low efficiency. So this is where we started thinking. Taking a lesson from nature does not mean just copy it simply. We have no resources to make this complicated cell factory. But we can take an important lesson to conduct redox chemistry at an excited state to break down the activation barrier. So we started thinking, why not leverage alkoxy radical to do a hydrogen atom transfer from this synergistic sequence and transfer methane into high-valued product. So as shown here in this proposed catalytic circle, the most important step is this hydrogen atom transfer. Even if you don't know this radical chemistry, but it turns into a simple mathematical game. Because look at the number here, the CH bond of methane is 105 kcals per mole. And the OH bond actually is way stronger. It's above 106 kcals per mole. So it can easily, for oxygen-centered radicals, to abstract a hydrogen atom from methane to generate methyl radicals. And kinetically speaking, there is an important principle called the polarity matching effect. So methyl radical is a nucleophilic radical, and alkoxy radical is rather electrophilic. So this process should be kinetically favorable. Once we can produce a methyl radical, we can make it to react with a variety of radical trapping reagents. Most of them have double bonds. For here, if it adds into this azo dicarboxylate, we can easily form a new CN bond to trap that high reactive methyl radical, then generate a relatively stable and also oxidizing nitrogen-centered radical. So this nitrogen-centered radical can oxidize serine-3 to close the serine catalytic cycle. Itself gets reduced, and after protonation, you can generate the desired amylation product. So based on this blueprint, we soon found out that there is a simple solution. We can easily use serine source in combination with free alcohol as the co-catalyst to achieve this challenging reaction at ambient temperature with blue LED irradiation to provide the energy and redox neutral and pH neutral conditions. We can use serine trichloride, serine triflate, or serine 4-triflate, which typically recognized as Lewis acid in synthetic chemistry. The turnover numbers can reach nearly to 3,000. And the free alcohols, some of them even used as solvent in synthetic labs, such as methanol, terbutanol, or trichloroethanol, can now act as co-catalysts. And importantly, we did not observe any over-oxidation of our desired product or any side product from methyl radical dimerization. So this is indeed a highly selective process. And we can easily swap this azo dicarboxylate to electron-deficient alkane or electron-deficient arene to form CC bonds in this cross-coupling paradigm. So over the last 3 years, we have also conducted a detailed mechanistic investigation. So allow me to talk short here, but I'll quickly walk you through this. So we managed to isolate and characterize the photoactive species, the serine 4 alkoxide pentyl chloride complex. Regarding the critical question, which type of radical can be produced during MCT excitation, we have been using operando EPR experiments and a transient absorption experiment led us to determine only alkoxide radical was indeed generated in solution. And there's no chance for it to form chlorine radical. And this transient absorption allows us to probe the kinetics in the excited processes, allow us to identify a back electron transfer between the O-center radical and the reduced metal center that causes us quantum efficiency. We have also taken the classical approach of physical org experiments, such as kinetic isotopy experiments, led us to determine that this O-center mediated HAT is indeed the rate-determining step. And in collaboration with Professor Hong Xin at Zhejiang University, we have also looked at the KIE experiment and the radioselectivity experiment from the DFT calculations, allow us to know a little bit more about the transition state. And after that, we try to play around with the radioselectivity. And butane is also recognized as a fuel. But if you look at this molecule more closely, there are two different CH bonds, primary and secondary. Now, either in bond dissociation energy, the bond strength, or the steric environment, those two are very difficult to distinguish. Therefore, recognized as the grand challenge in selective control in transition metal catalysis. So we managed to test a variety of free alcohol as a co-catalyst and found out that methanol, the corresponding methoxy radical, tends to be the most selective one. It tends to abstract from the relatively weakened secondary CH bond and the more electron-rich positions, leading to the generation of a branched amylation product. And the same selective pattern can be verified on the hexane example. We have also managed to demonstrate scale-up applications in our synthetic lab. This we have to use in a glass-made microreactor made by the Corning company. It's a very small size. You probably only have the half size of your iPhone screen, but it costs way much more, maybe like 5 to 7 iPhones. So we managed to build up a 4.5 milliliter reaction volume using 10 parallel reactors. With that, we can easily achieve up to 2 micromolar per hour productivity. The catalytic conditions we optimize for masking amylation can be easily adopted to other selective functionalization of feedstock chemicals, such as shown here on the right side. we can achieve the serine catalyzed CH amylation of adamantane and to generate this amylated building block for this important anti-diabetic agent. We can achieve satisfactory level of yields and radioselectivity. So now we know how to generate radicals. The next important question is, can we also control its reactivity? One striking example is the CH carbonylation of methane under aerobic conditions. So this is truly a simple and elegant transformation, converting like 2 greenhouse gases into a liquid and valuable chemical, and is vastly produced for the plastic industry. However, this is probably one of the most challenging reactions in selectivity control. So methyl radical is known to add into CO to generate a more stable acetyl radical. But this reaction is known to fail in the presence of oxygen or in the presence of air, because people have studied the kinetics of those two reactions. Obviously, the trapping of methyl radical with oxygen is 3 magnitudes faster than the CC bond formation here. So previously, synthetic chemists have made the judgment call that the presence of oxygen results in a strong inhibiting effect in the formation of acetic acid in the radical chemistry. So you probably have to use a chemical oxidant such as persulfate to enforce this reaction. Transition metal catalysis, on the other hand, already made a significant advancement, but also suffering from this side reaction. So the similar report coming from a group at Penn State back in 1994, where they can use rhodium chloride as the catalyst. Basically, rhodium can insert into the CH bond of methane, forming a rhodium methyl species, which can coordinate with CO to form a CO insertion, then generate this CC bond. However, this rhodium methyl species is prone to oxidation. It can be oxidized to generate side products such as methanol, formic acid, or CO2. Almost like 20 years later, a European group tried to leverage this rhodium catalyst on heterogeneous system, and they can significantly increase the catalytic efficiency, but it's the same activation strategy, so they still suffer from the CH oxidation. So the record for this carbonylation reaction is only 2.8 to 1. So we started wondering whether we could leverage the LMCT catalytic platform to enforce the interplay of 1 electron and 2 electron steps to facilitate the CC bond formation. Because we have known to generate methyl radicals from LMCT and HAT event. And in this case, we are wondering whether we could leverage like iron catalysts, because iron 2 are known to coordinate with CO so fast and to generate this iron 2 CO complex. And this complex has been demonstrated previously can interact with alkyl radicals. So if we were lucky enough, if methyl radical can add into this iron coordinated CO, we have a very good chance to form the desired CC bond. And then looking at this, we realize this is sort of like a radical rebound mechanism. And people have studied the methane monooxygenase system. They elucidate that iron oxy cluster could abstract a CH bond from methane to generate a methyl radical. The methyl radical will kick back to this iron complex to enforce the CN bond formation selectively. The only difference here is that before methyl radical interact with our iron catalytic cycle, the CO will jump in to enhance the opportunity to form CC bond. So we started to investigate a variety of iron catalysts and found that iron porphyrin, an icon, I would say, for iron chemistry, could also work in this reaction. It can lead to the generation of acetic acid, although at a moderate level of selectivity, we still suffer from the CH oxidation. So further ligand campaign led us to recognize this terpyridine compound. This iron terpyridine catalyst, which is rather robust for this chemistry, can significantly increase the catalytic efficiency and also selectivity. And the current record can reach up to 20 to 1. We can use in very low catalyst amount of iron catalyst reaching a turnover number of more than 10,000. So this is a classic case where we've shown that we can use in this inexpensive iron catalyst to beat the record set by a low metal catalyst. So we have done some mechanistic investigation, allow us to isolate and characterize photoactive species and done steady-state photolysis experiment. We can also monitor the in situ formulation of iron 2CO using operando IR spectroscopy experiment. And through a coordination with my good friend Neil Peng at Pittsburgh, we look at this open shell radical pathway through DFT calculations. Based on their study, that methyl radical can indeed add into this iron 2 coordinated CO through an out-sphere radical addition pathway to generate a more stabilized iron acetal complex. Although currently it's very difficult for us to probe the identity of those metal complexes directly in situ, but I think this finding helps us to explain the peculiar correlation we observed in the optimization. Because back then we realized that the increasing of CO pressure together with the increasing of iron catalyst loading always help us to boost the catalytic efficiency. As you can see from this paradigm here, you will realize that both ingredients increasing the concentration will help you to build up the concentration of the iron 2CO complex. That's critical for the rapid and selective trapping of methyl radicals and keep it from the reacting its oxygen. So I'll quickly walk through the last part, and this is sort of like a side of the reaction. With the sterics, we always suffer from the beta station, the decomposition of our exact co-catalyst here. So this turns out to be the Achilles heel of our system. So we started thinking out of the box, why not taking this decomposition pathway into a productive activation mode? And by leveraging the alkoxide radical generator from LMCT, we managed to develop a variety of CC bond cleavage and transformation reactions. Basically, we can try to insert a different function group or units into unstrained CC bond, something that previously unheard of pretty much under these mild reaction conditions. And I'll quickly go through the last story. Professor Zhou has shown a lot of exciting chemistry in asymmetric catalysis. I've done a very elegant way, try to elaborate on that point. So we try to start to think outside of the box. So instead of generating the chirality during the construction of the chemical bond, is there any chance that we can impose enantiomer selectivity in reversible reactions? Basically, we can take the exact same molecule, although it's in racemic form, and selectively cleave one of the enantiomer and transfer into the opposite enantiomer without any change in the molecular structure, just the editing of the stereochemistry. This is a new type of transformation called deracemization. We have to overcome the limitation set by the thermodynamics and also the principle of microscopic reversibility. So I don't have enough time to go through all the detail, and also it's a little bit boring for the general public, so I'll quickly walk through this. So we found an interesting strategy, sort of like a one stone, two birds situation. By throwing a chiral ligand in our LMCT catalyst, we can selectively coordinate and activate one of the enantiomer, making to do a selective CC bond cleavage reaction. And at the same time, the generation of a low-valent chiral metal here can mediate alkyl radical addition. If we can do this 1-2 addition asymmetrically, we can achieve our goal and then overcome the limitation of the principle of microscopic reversibility. And so we managed to find out that titanium tetrachloride in combination with chiral phosphonic acid could easily make this reaction work. And this has been demonstrated in a general sense. We can easily manipulate the stereochemistry in a variety of cyclic alcohols, either a strained system or unstrained system. There are cases where we can also editing these cold stereocenters. So basically now with this catalytic system, we can easily manipulate the stereocenter of the starting material to get to the opposite mirror image, and then do it again, it will turn into the corresponding same structure once again. So I will quickly walk you through this skip this mechanistic investigation. And through detailed studies, through kinetic analysis, We now know that we can easily achieve good N-tail selectivity through this multi-pernicative enhancement effect of sterol enrichment. Basically, you don't need to achieve good levels of N-tail selectivity in each step. 60% EE in the bond cleavage step and 60% EE in bond formation step, basically like a B- results. If they can work synergistically together, you could easily achieve 90% EE in the final outcome. So I have to acknowledge all the heroes behind these stories. And I think my time is almost up. I was thanking this funding situation and thank you for your kind attention.
Thank you, Professor Zhuo. Your LMCT catalysis actually provides a powerful and sustainable platform for activating the very inner bond. Okay, and now I will call our last distinguished speaker, Professor Xingyuan Liu. Xingyuan, the floor is yours. Please join me. Welcome.
Okay. This point, okay, thank you, the Professor Xie, for your kind introduction. So at first, I would like to thank you, the Professor Xie and the organizer community to give me so very important opportunities to attend this wonderful symposium. Okay, so just the Professor Zhou and Zhiwei give very wonderful chemistry about the asymmetric catalysis and the photoredox catalysis. So actually, my chemistry also focused on the asymmetric catalysis for the synthesis organ, very powerful, very important, the chiral compound. So just as Professor Zhou share very wonderful introduction about the chiral compound, how wide application in the different field, like the chiral drug or the advanced material science. So today, I just show the detailed chemistry from my lab. Okay, so my chemistry mainly focused on to address the highly reactive radical non-selectivity control with our developed the chiral and ionic ligand combined the couple catalyst. So anyway, so before share my detailed chemistry, I would like to share my my chemistry. So why use our developed this catalyst to address the highly reactive radical non-selectivity control? So we want to develop the 3D transition metal combine the chiral and ionic ligand. So why to develop this chiral anion ligand? For example, we want to use a couple. The couple is a D9 metal, is a Cap2, actually have good interaction with this radical. So maybe to generate the cation or the anion or the directly undergo radical homogeneous substitution the pathway. So anyway, so you can see in all of these intermediate, the chiral anion can provide the chiral environment. So that means maybe provide the diversity possibilities to realize non-selectivity control. Okay, so based on this idea, so in my lab, so maybe in past decade, so we developed different kinds of chiral anion, the ligand, like the phosphate or phosphate combines the neutral ligand. So more recently, we directly use a hybrid, the bidentate or the tridentate and ionic ligand, combine the couple. So we want to use this couple 1 as a single electron transfer catalyst to activate different any the neutral substrate to generate a radical. Then couple 1 oxidizes to couple 2. So I just mentioned if generate the couple 2 combine the chiral and ionic ligand, so actually have good interaction with this radical, provides the different, very powerful the chiral environment, so maybe to realize the asymmetric transformation. So finally, so we can give to the different kinds of chiral carbon-carbon or the carbon heterobond formations. Okay, so this the chemistry mainly focused on the sp3 carbon-based alkyl radical species. So actually, more recently, like the 3D transition metal, like just the GWay shows the photoredox catalysis or the electrochemistry. So we can use any neutral substrate to generate any different kinds of radical species. So like here, you can see the heteroatom radicals or the very highly reactive sigma type the carbon radicals. So actually, this is the radical. So as compared, this the radical have completely the chemical properties. So that means, so maybe it's very difficult to control enantiomer selectivity. So also more recently, we are very interesting about to address this radical enantiomer selectivity control. So very lucky, we continue use our developed the catalyst system. So bonding the different the nucleophiles, we can address, like you can see, the highly reactive vinyl radical, or the allylyl radical, or even more the heteroatom, the sulfonyl radical, or the acyl radical, or the highly reactive cyclopropyl radical in selectivity control. Anyway, so more recently we collaborate with Professor Hong Xin for the DFT calculation. We found this radical actually undergo radical homogeneous substitution pathway. So based on this pathway, more recently we found very interesting reactions. So you can see this reaction, we directly use our developed tridentate anionic ligand bonding the couple, then bonding this different substrate, maybe to generate a couple one their species. So these species have very strong reducing capability, so can activate any neutral substrate to generate different kinds of radical species. Okay, so then CAP1 oxidized to the CAP2. So actually, this the CAP2 is a thermodynamic, the favored the species. So then this institutively generated radical directly undergo radical homogeneous substitution pathway. So then to generate all kinds of chiral building blocks. So you can see in this reaction system, we can tolerate any radical species, like the highly reactive, the primary or secondary or tertiary carbon radical, even more the methyl radicals. So also we can tolerate highly reactive nitrogen or oxygen-based radical species. Also we can tolerate the different, the acyl, sulfonyl, the phosphine, all kinds of radical species. So that means, so based on this strategy, so we can provide a general approach, can tolerate any highly reactive radical species. Okay, so today, because of time limitation, I just show the only one reaction, so cross-coupling reaction. So cross-coupling reaction, so like sp2 So like sp2 electrophiles bonding the nucleophiles to form the carbon-carbon or even more the carbon heterobond formations. So these reactions have wide application in the different fields because can provide very important tool for synthesis of organic compounds. So have wide application like for the synthesis very important the drugs or the advantage the materials. So this reaction have been recognized by many famous name reactions and even more the Nobel Prize. So before mainly focused on the sp2 electrophiles. So more recently, scientists want to move to the sp3 electrophiles. So like these racemic electrophiles, hope to give only one the chiral compound. So because as compared to sp2 electrophiles, sp3 electrophiles want to realize cross-coupling reaction, so it's not easy. So because sp3 electrophiles is very difficult to undergo a fundamental transformation like oxidative addition. So if they realize oxidative addition to generate this intermediate, also easily undergo beta hydrogenation give olefin. Also, it's very difficult to undergo reductive elimination give our design as a product. So that is why this reaction is very challenging. So more recently, some great scientists discovery uses 3D transition metal like the nickel, iron, or the copper catalyst. Because these metal have good single electron reducing capability, maybe directly to activate racemic alkyl electrophiles give prochiral radical intermediate. So then, in the presence of chiral ligand, maybe for the hypervalent, the transition metal, or maybe directly undergo radical homolytic substitution in the pathway, then they can realize the chiral carbon-carbon bonds formations. So also, maybe this chemistry undergoes 2 decades. So also made great progress in this field, still remain unsolved the problems. So because this reaction just electrifies and nuclearizes, so we can see, like in the case of electrophiles, these 2 electrophiles is very difficult to realize the transformation. So first one is unfunctional alkyl electrophiles, gives this unfunctional alkyl radicals, because this radical is highly reactive. So also is very difficult to realize enantiomer discrimination, because in the presence of 2 seminal alkyl groups. So later I will show the detail. So this is the radical, why to realize non-selectively control very challenge. So another is the tertiary electrophiles give the tertiary radicals, because this the radical very bulky. Also is very difficult to have good interaction with this transition metal. So on the other hand, in the case of nucleophiles, I just mentioned use nickel, iron, or copper catalyst, mainly focused on the carbon-carbon bonds formation. So it's very difficult to undergo the carbon heterobond formation in the presence of heteroatom nucleophiles. So maybe this metal is preferred to undergo reductination, so not easy to undergo reductination. Okay, so I just mentioned our chemistry mainly focused on the copper. So however, before the copper pays less attention, use a catalyst to realize this transformation. So actually copper is very cheap and very low toxicity. So why the copper is very difficult to realize this transformation? So actually it's very easy to understand, because copper, as compared this metal like the nickel, iron, copper catalyst, so have very weak reducing capability. That means it's very difficult to initiate this reaction. On the other hand, if initiate to generate a radical, so I just mentioned the radical is highly reactive, also it's very difficult to control in non-selectivity. So anyway, so we want to use our developed the copper catalyst to realize this transformation. So most importantly, we want to use this catalyst to address these challenges and problems, like very challenging electrophiles and very challenging nucleophiles. Okay, so actually the copper, I just mentioned, like the copper-2 is a D9 metal, have good interaction with this radical, maybe form the copper-3 intermediate. So actually, so this copper-3 intermediate is highly reactive, easily undergo reductination, so to generate the carbon, and even more the carbon heterobond formation. So if in the presence of chiral ligand, maybe also to realize asymmetric transformation. So if we want to use a copper as a catalyst to realize the enantiomer conversion cross-carbon reaction is very simple. So maybe to directly increase the reducing capability of the copper to initiate this reaction. So that means maybe to realize cross-carbon reaction. Okay, so actually in this field, from the Caltech, the Professor Peters and the Professor Fu collaborate to use a photo. So just Zhiwei mentioned, the photo catalyst is really powerful. So for example, if it is a copper 1 in the presence of the photo to generate excited state the copper species. So these species have very strong reducing capability directly to initiate this reaction to generate radicals, then to realize the carbon-nitrogen bonds formation. So we are wondering, so maybe directly use one simple chiral ligand. So we hope use this ligand to increase the reducing capability of the copper. So maybe can initiate this reaction and the very mild the thermal conditions. Don't need the photo and don't need the electrochemistry. So at the same time, if initiate this reaction, so we hope use this ligand to provide the chiral environment to realize the radical is not selectively controlled. So this is our idea. So anyway, so at the same time, so many research groups use the same concept to do this chemistry. So because of time limitation, I just show my chemistry. So why we have this idea? So I just mentioned, so in my research group, mainly focused on design chiroanionic ligand. So like you can see this ligand. So this ligand is have the tertiary amine and phosphine and anionic amide. So all of autumn is electron rich. So that means can increase the electron density. So maybe this species combines the nucleophiles from this intermediate, maybe have very strong reducing capability. Maybe can initiate this reaction and the very mild the thermal conditions. Then maybe use this ligand to realize asymmetric transformations. Okay, so anyway, based on this idea, so in my lab, so maybe in past the 5 years, so we set up the different chiroanionic ligand library. So you can see this ligand have NNP or NNN or the tridentate or the bidentate ligand. So actually, so this ligand is very easily available. So because this chiroskeleton is very cheap, like the alkanoid derived the starting material. So we link like the amide on the sulfur amide. So it's very easy to cross to give this ligand. So also this structure is very easily modified. So that means this ligand is very easily available. So up to now in my lab, maybe have 1,000 ligand. So that means it's very easy to screen the reactions. Okay, so I just mentioned maybe this ligand can increase the reducing capability of the couple. So more recently, we isolate the many CAP2 complex. So we test the reduce potential. So you can see this simple couple reduce potential. So this box ligand, the neutral ligand bonding the couple, the reduce potential. So this of the ligand combines the different nucleophiles reduce potential. So you can see like this species can move to the minus 1.8 watt. So that means this species have very strong reducing capability. Maybe directly initiate the racemic alkyl electrophiles to generate radical. So indeed, so more recently, we use our developed the tridentate anionic ligand the library, so bonding the different nucleophiles to form this intermediate. So I just mentioned this intermediate have very strong reducing capability directly to activate racemic halide and the very mild thermal conditions, like the room temperature, so to generate a radical, maybe form the CAP3 intermediate, maybe directly undergo radical homotic substitution pathway, so then we can realize the different chiral carbon-carbon and even more the carbon heterobond formation. Okay, based on this reaction, so you can see the subscope is really broad. So you can see in this reaction, we can tolerate different carbon-based nucleophiles, like SP, SP2, even more SP3 carbon nucleophiles. So also, this reaction can tolerate the different heteroatom nucleophiles. I just mentioned that using nickel, iron, or copper catalyst is very difficult to realize carbon heterobond formation. So in our reaction system, it's okay. So electrophiles not only to realize secondary radicals, so also we can realize the tertiary radical give the all carbon quaternary the centers. So I just mentioned using nickel and copper catalyst is very difficult to realize tertiary radical gives the quaternary chiral centers. So that means based on this strategy, we can provide the complementary approach for the like the nickel and copper catalyst. So gives the different kinds of chiral carbon-carbon and even more the carbon heterobond formation. Maybe have a potential application for the synthesis of very important the chiral drugs and even more the natural products. Okay, so anyway, so based on this chemistry, the first step is deprotonation or the transprotonation to give this intermediate. However, So many nucleophiles is very difficult to undergo the deprotonation or transmethylation to generate like the carbon nucleophile, the intermediate. So you can see the ammonia or the aliphilic amine, so it's very difficult to undergo deprotonation, give the carbon amines and intermediate. So on the other hand, so these species have very strong catalyst coordination properties, so easily cause the catalyst poison. So that means we should to develop another approach to address this cross-coupling reaction. So more recently, we found very special electrophiles. So this electrophiles, you can see the amide. So because amide, as compared like the ammonia or the aliphilic amine, so more acid. So that means in the presence of inorganic base, easily undergo deprotonation of this amide to generate this intermediate. So then, because I just mentioned the copper-1 bonding our tridentate anionic ligand have very strong reducing capability directly to activate this halide to generate a radical. So then maybe form the copper-3 intermediate. So then here, I just use these nucleophiles directly undergo outfield nucleophilic attack of this highly reactive copper-3 intermediate, then to realize the carbon nucleophile, the bonds formations. Anyway, so this reaction, so because directly use nucleophiles undergo outfield nucleophilic attack, the subscope is really broad. So you can see in this reaction, we can tolerate different kinds of amine nucleophiles. Like I just mentioned, very challenging the ammonia, the aliphilic amine, or very bulky aniline, or the hydrazine. So also in this reaction, we can tolerate very easily available the alcohol, even more very bulky the tertiary alcohol. So also can tolerate phenol, carboxylic acid. So more recently, we found this reaction system directly can tolerate very simple water, or the fluoride as a nucleophile also to realize the carbon-fluorine bonds formations. So also this reaction can tolerate very bulky and soft the carbon nucleophiles to give carbon-carbon bonds formations. So anyway, so electrophiles, you can see, also can tolerate the secondary and even more very bulky, the tertiary electrophiles is okay. So okay, so next because of time limitation, I just show the only one the detailed examples. So I just mentioned we use these radicals because these radicals have alpha function radicals is relatively stable. So more recently, we also to realize highly alkyl radicals with a directing group. So why to introduce a directing group? So it's very easy to understand because use a directing group can be stabilized as a couple. So that means maybe stabilize these highly reactive alkyl radicals. Then maybe to realize intramolecular transformations. How was this the radical? It's very just the unfunctional alkyl radicals building very simple the alkyl groups. So this radical is really challenging to realize in non-selectivity control. So first, so because this is the alkyl radical 2 seminar, so it's very difficult to realize in non-discriminations. So just as Professor Zhou shared a very wonderful, developed the very powerful spiral ligand to realize asymmetric hydrogenation, the very simple ketone, and the imine in the presence of two simple alkyl groups. So anyway, so that chemistry gives me very, very strong inspirations. Okay, on the other hand, so I just mentioned this the radical as compared like the benzylic radical is highly reactive. So sometimes this reaction really, really fast. So how will we want to realize in non-selectivity control? So we need to the more energy barrier. How is this species highly reactive? So that means it's very difficult to realize the energy barrier. So that means so this the radical is highly reactive to highly reactive and is very difficult to realize in non-selectivity control. So we want to learn the enzyme. So anyways, the enzyme provides the carried pocket, well-confined carried pocket to realize the like the asymmetric transformation. Yeah. So we want to learn the enzyme, but not enzyme catalysis. Here we want to design well-confined but the partial open the chiral pocket. So like the truncated core, the shape the chiral pocket. Why to develop this kind of the ligand? So you can see this is open the area. So maybe the small alkyl group located is in this field. The large alkyl group located the outside. So I just mentioned this radical is highly reactive. How to use open chiral pocket to stabilize this radical? So this is a very big challenge. So anyway, so more recently, we hope to introduce many aryl group or the alkyl group on this ligand. We hope to, through the non-covalent interaction, like the hydrogen-hydrogen or the hydrogen-pi non-covalent interactions, to stabilize this alkyl group. So if okay, so based on this chiral, open the chiral pocket, so the subscope is really broad. So because this area is really open. So that means not only to tolerate the primary alkyl groups, maybe can tolerate the secondary alkyl groups. So even more, maybe can tolerate very, very bulky tertiary alkyl groups. So that means if okay, the subscope is really, really broad. Okay, so anyway, so we, at first we test this reaction, the racemic iodine, so use amine, we can to realize same bonds across carbonyl reaction. So at the beginning, we use our previous developed the NMP, the ligand. So how was this reaction efficiency and the enantiomer selectivity is really poor. So we tested the couple concentration. We found in the reaction system, the couple concentration is this very, very low. So that means this the ligand, the solubility is not good in this reaction system. So next, at first, we addressed the reaction efficiency. So finally, we introduced the alkyl group on this the phenol ring. So we tested the couple concentration as compared this, they increased very fast. So that means this the ligand solubility is okay. Then we test this reaction. You can see the reaction efficiency is okay. So that means we can address the solubility. So next, we want to provide the chiral pocket to realize enantiomer selectivity control. So continue based on this the ligand to introduce a phenol ring and many alkyl group to provide the well-confined chiral pocket. Finally, we can address this reaction with good enantiomer selectivity and good reaction efficiency. So I just mentioned, so if based on this ligand, maybe subscope is really broad. So indeed, so you can see in this reaction system, we can tolerate the primary, and the primary is a highly reactive secondary radical. So you can see this the primary alkyl group. We can tolerate many function group, also the branched, the secondary, or even more the tertiary, the alkyl group. So I just mentioned maybe this reaction can tolerate the primary and the secondary highly reactive radical species. Indeed, in this reaction, you can see we can tolerate the methyl and the different the cyclic and acyclic. Also, we can tolerate very challenging the primary and the tertiary, the alkyl groups. So that means this subscope is really broad. So also this reaction, we can tolerate very similar the alkyl groups, so ethyl and propyl. So very, very similar. So in this reaction system, still gives a good enantiomer selectivity control. Anyway, so up to now, the enantiomer selectivity is not good. We continue to modify this the ligand, hope to address this the problem. So also this reaction can tolerate the secondary highly reactive radical species, also to realize carbon-nitrogen bonds formations. So anyway, so because this is the cyclic amine, so very important. So you can see to generate and go the transformation, give this the building block. So this building block, so then directly give very, very important the chiral drugs. So you can see, so this the building block are many chiral drugs and click the chiral drugs, the motifs. So that means with our strategy easily to synthesize the very important the chiral compounds. Okay. So more recently, we want to use our developed strategy to realize the C bond functionalization. So that means directly from the very simple alkanes, we hope to realize this transformation. So how was this reaction as compared starting material, the racemic iodines. So we addressed the two problems. First problem, we want to realize site selectivity to generate one special radicals. Then we use this radical, use our developed strategy to realize carbon-nitrogen bonds formations. So anyway, at the beginning, we select these very special alkanes. So because this hydrogen easily undergo HAT, like in the presence of phenyl radical to generate this radical, then use this our strategy to realize this transformation, to have good yet and good enantiomer selectivity. So how we directly from the pentane, the hexane, so you can see the site selectivity and the enantiomer selectivity is not good. So we use the racemic iodine to test this direction, gives the same enantiomer selectivity. So that means maybe we continue to modify the ligand, maybe to address this reaction enantiomer selectivity. How to realize the site selectivity? So more recently, we continue to modify the very powerful HAT reagent to realize the site selective HAT to generate one special radical, then maybe to realize the carbon-nitrogen bond formation. So maybe next time to show this the chemistry, the detail. Okay, so also maybe because time limitation, I want to skip this. So next we collaborate with Professor Hong Xin for the DFT calculation. So we want to know how to interaction in COT generated the Cap2 and the radical. So after DFT calculation, so they found so directly undergo radical homogeneous substitution to give the carbon-nitrogen bonds formation. Okay, so maybe I can skip this. Okay, so finally we want to use our developed strategy, hope to synthesize very important the carrier drugs and the natural products. So for example, so we use our developed strategy to synthesize very important the carrier drug and the natural products. So more recently we use this strategy, give the all carbon content receptors. So these receptors are many natural products and the carrier drugs motifs. So we use this strategy, we can still divergent synthesis this very important compound. So more recently, we collaborated with Professor Hao Hua Li from the Peking University. He used our developed strategy, give this the building block, because this group and this group easily undergo transformation. So with this strategy, they can diverge in the total synthesis of multiple series of natural products. So anyway, so now our ligand is chemistry available. So anyway, so finally, I would like to give a brief summary. My chemistry mainly focused on use couple combine the carrier ligand, we can realize different kinds of highly reactive radical species enantiomer selective control. So we can realize carbon-carbon and even carbon-hetero and hetero-hetero bond formation. Finally, I would like to thank you, my supervisors and many collaborators and research fellows. Okay, so thank you, the funding support agents. So thank you all for your kind attention.
Thank you so much, and please stay. Please remain on the stage. Thank you so much for insightful sharing. And following this insightful talks, our distinguished panel will now explore how this cutting-edge advances in catalysis, polymer recycling, and synthetic methods collectively forge a sustainable future. They are going to discuss integrating these technologies to create cleaner, more efficient, and circular chemical process, paving the way for tangible solutions to global environmental challenges. Now, we are very happy to have the panel. We are very happy on stage already. Our moderator, Professor Xie Zuowei, and our panelists, including Professor Liu Xinyuan, Professor Zhou Qilin, and also Professor Zhuo Zhiwei. Let's pass the stage to Professor Xie.
Thank you, thank you. Yeah, we have just finished the exciting presentation sections this morning. So the first speaker, Professor Washer, talked about the biocatalysis, and rest of three will talk about the chemical catalysis. So I'm going to post a few questions for all of you so that we can share their wisdom with all of us. So the first question will be, let me see, I have prepared a few of them. What are the advantages and limitations of using enzyme, that means biocatalysts, compared to the traditional chemical catalysis in industrial processes. Yeah, Jingyuan, you might be started.
Okay, so maybe, so let's start, okay. So I think the enzyme catalysis and chemical catalysis, the both is very important. So let me think back to maybe 2012, one paper in Nature, so organized by the very famous synthetic biology Professor Kathleen and organic catalysis Professor Baron, about a constructive debate for the synthetic biology and organic chemistry. So they share the key the difference. So anyway, so if you are interested, I recommend to read that paper. So for me, so in my point, like the enzyme catalysis, maybe have some many advantage and maybe have some limitation. For example, like enzyme catalysis, so I just show the chemistry, so learn from the enzyme, because enzyme catalysis, sometimes the optimization reaction is very fast. So because more recently, like develop very powerful the directed resolutions technique, so developed by the Nobel Prize laureate, the Professor Arnold. So because this strategy, so is very quick to give the enzyme the library. So that means the optimization reaction is very easy because have many catalysts. So on the other hand, maybe enzyme catalysis provide the excellent inactive selectivity control, because enzyme can provide the very well confined carrier pocket. So also enzyme catalysis maybe is very quickly to give them the very complex organic compounds with multiple cancers, multiple carrier centers. So however, the enzyme maybe have some limitations. So I just mentioned maybe the subscope and the reaction scope is very limited. So because I just mentioned the enzyme catalyst with well-confined pocket, so maybe the subscope as compared to homogeneous catalysis, so maybe it's narrow. So maybe some reaction also some subscope. Subscope is very narrow. So I want to say maybe like enzyme catalysis, most carry out in the water. So maybe some reagent, so very sensitive to the water, maybe is very difficult tolerate in this reaction system. So anyway, so I want to say the enzyme catalysis and the homogeneous catalysis both are important. So that means we should have enzyme catalysis have the limitation and advantage, and homogeneous catalysis have the limitation and advantage. So that means collaborate with each other, so to become the powerful tool for the synthesis for the very important products. So this is my point.
Okay, thank you, Jingyuan. Professor Zhou, please.
Okay, 这个刘新元老师 ，Oh, sorry, I speak Chinese. Professor Liu already mentioned the both side advantage and limitation of this too. But in my opinion, the enzyme, the biocatalysis has more environment friendship. And another advantage is more specific, it's more selective. Compare chemical catalysis, but the chemical catalysis is much more powerful and can do much more reactions than the enzyme, because the enzyme only can catalyze at the moment natural reactions. But I think both sides need to learn from each other and to address the limitations. And this is the situation already we're facing now. So, this is my opinion. We should learn each other.
Okay, thank you. Ziwei, please.
I think both professors have already expressed very good points on the comparison between like enzyme catalysis and chemical traditional catalysis. I'm not an expert on enzyme catalysis, but I know a lot of the good friends in that area. It seems to be a very hot topic right now, but actually it's not a novel idea. It can go back down like decades. There are even like a lot of good processes currently going on in the industry that rely on enzyme catalysis. But if there is a competition between those two fields, I'm certainly on the team of chemical catalysis. Of course, I'm going to lose. I mean, enzymes are so good at control stereochemistry and radial selectivity and such. But for the long run, I'm thinking, why not limit the space for innovation? There's so much things you can try, like so many metals and so many elements that synthetic chemistry can put together, right? Why not just focus on a very complicated system? And it takes a lot of efforts to do that, and some of the time are not really robust. Because we recently, we played around a little bit with like photocatalysis and enzyme catalysis. One of the major challenges is that those things are not as robust as our organic molecules, and sometimes compared to like transition metal catalysts. So I think, I especially like the quote of the founding mother of biomimicry. Learning from nature is not just to copy it, it's to understand the principle and leverage the very core of that, then come up with like entirely new solutions. I'm absolutely for that. Thank you.
Okay, thanks. Thank all of them. Things we have a few minutes left, so I will turn to very simple questions, but might be interested by all the audience. So what is your dream catalytic reactions and why? Xinge, start.
Okay, so actually, so I just show my chemistry, so use our developed catalyst system to realize looked very beautiful, the carbon-carbon or the carbon-hydrogen bond formation. So actually, so you can see so our ligand structure very complex. And the sun reaction use very high catalyst loading, so reaction efficiency is not good. so why we continue to think about so for me it was a dream reaction. So we want to continue focused on the asymmetric radical reaction. So we hope to develop the reaction directly from the easily available the starting materials, like the alkene or the alkanes or very simple alcohol or the amine or even more the biomass, the source, directly give the value added the chiral compounds. So in one step. So also we hope use our develop the ligand really cheap and very easily available and with high reaction efficiency and very low the catalyst loading. So if the OK, maybe provide a very important tool for the synthesis, very important chiral drug and advanced material. So anyway, so have very long time, very long way to go. So this is my dream reactions. Okay.
Okay, good. Qilin, please.
My dream, of course, is we want to develop a universal catalyst. It can solve all the problems. But we know this is just a dream. We cannot realize that. But what we can do is develop privileged catalysts. Why we say that? Because now we have many reactions, especially in the organic chemistry. Almost unlimited number of reactions, unlimited number of the substrate. If we don't have a privileged catalyst or ligand, that means we need an unlimited number of the catalysts. That's the task we cannot approach. So this is why I say at least we need to develop the privileged catalyst, which can solve many reactions and subjects.
Okay, thanks. Ziwei, please.
I have so many. Maybe just name two. like methane and water to make methanol, and methane and carbon dioxide to make acetic acid.
Good. Thank you very much. It's time for us to have lunch. So I think I have to stop here. Otherwise, you might not have enough time for your lunch. With that, I'd like to thank all the participants this afternoon and thank all our speakers. And thank you very much for joining this chemistry symposium, and I'd like to close this morning's chemistry symposium.
Thank you so much, and please stay for a photo together. Please stay. May I now invite the guests on the stage, stand closer to each other, and then we can have a group photo. Let's have a look to the center. One, two, three. 1, 2, 3. Few more to go. 1, 2, 3. 1, 2, 3. Thank you. Thank you so much for insightful sharing. Thank you. Thank you so much. This is the finale of the section, ladies and gentlemen. We are about to have lunch. For those who registered a luncheon, please follow the instruction from our helpers to the venue. We'll see you soon at 1:30 with different keynote speakers with different insightful topics. See you at 1:30. Thank you. Hello, ladies and gentlemen. The Science Symposium will resume very soon. May I invite you all please be seated. And don't forget to turn mobile phone to silent mode. Stay tuned and see you in a bit. Hello, ladies and gentlemen. Welcome back to the Science Symposium. This section is Life Science section, Gut Microbiome, the living lessons of human health and disease. Now I would like to introduce with you Professor Yu Jun as this section's convener. He is Assistant Dean, Faculty of Medicine, Director, Institute of Digestive Disease, Director, State Key Laboratory of Digestive Disease, the Chinese University of Hong Kong, member, Hong Kong Academy of Sciences, foreign member, European Academy of Sciences, member, Program Committee of the Future Science Prize Week 2025. Let's give a warm welcome to Professor Yu.
Thank you. Good afternoon. Distinguished guests, esteemed colleagues, ladies and gentlemen, welcome to the Future Science Week Science Symposium. I'm Jin Yu from the Chinese University of Hong Kong. It's my great pleasure and honor to chair this particular session. Today, we will embark on an exploration of one of the most dynamic and transformative frontier modern biomedical science, gut microbiome, the living nexus of human health and disease. within each of us resides an immensely complex and interconnected microbial universe composed of trillions of microorganisms that coexist with our cells in a delicate symbiosis. This inner ecosystem exerts profound influence over virtually every aspect of our human biology, shaping metabolism, modulating immunity, protecting against the pathogens, and even influence our mood, our cognition, and behavior. Over the past decades, revolutionary advances in metagenomic sequencing, single-cell analysis, and multi-omics integration have propelled microbiome research into a new era. These innovations have not only revealed the vast genetic diversity and the functional capacity of our microbial communities, but also refined our view of the human body, not as a singular organism, but as an intricate meta-organism composed of human and microbial components, intertwined in health and disease. In this session, we have a privilege to welcome 4 distinguished scientists, each of pioneer in their particular field, who will guide us through the continuum of microbiome research from fundamental ecological and mechanistic discoveries to translational insights with direct implication of clinical practice, therapeutics, and ultimately human well-being. Thank you all for joining us. Let us begin this journey into the living nexus of human health, the gut microbiome. Our first speaker, Professor Rob Knight, Director of the Center for Microbiome Innovation at UC San Diego and a globally recognized authority in microbiome science and bioinformatics. He will present his lecture entitled Understanding the Human Microbiome with Ecology, Machine Learning, and AI. Please join me in welcoming Professor Rob Knight.
All right, great. Thank you, Professor Yu, for that very kind introduction, and thank you for the invitation to kick off this, this symposium and to be part of Future Science Prize Week. It's a very exciting event, and I very much appreciate it. So what I'm going to tell you about is 3 major transitions in microbiome research. The first integrating ecology, the second integrating machine learning, and the third that's going on right now, integrating AI. I have some disclosures, none are particularly relevant to this talk, except I used AI extensively for the illustrations. So why do we study complex microbiomes? Well, we study them because they're intimately involved in many of Earth's problems, and the difference between a good future and a bad future depends on how we respond to these different topics like infectious disease, chronic disease, food production, pollution, and climate change. And the tools to understand and apply these microbiomes are fundamentally grounded in ecology, although, as I'll show you more recently, applying machine learning and artificial intelligence has led us to a lot of advances that we could not do with ecology alone. Now, I did my graduate studies at Princeton in the Department of Ecology and Evolution, and one of the projects that I had was snorkeling around Panama, holding one of these 1-meter quadrats and recording all of the organisms that I saw in each of those square meters, looking at transitions across ecological boundaries. And what I learned there is that ecological sampling, no matter how you do it, is inherently biased. So, for example, anything that crawled out of my little frame I would not be able to sample. And the taxonomic resolution is limited. You can't be an expert on everything that you look at. And to bring together specialists in hundreds of different taxa is essentially impossible. But despite these limitations in what you can do with ecology, no one particularly cares about them in that field, because if you have standardized methods that you apply to many places, you can make comparisons across sites, across time, across space, and derive a lot of useful information despite these biases. So the strategy of applying community ecology has been really transformative. We took techniques primarily derived from Whitaker's studies of landscapes in the 1960s. And so he was applying this mainly to forest ecology. And so there are concepts like alpha diversity, where you're looking at the number of different trees in one patch, or as I think you will see during the rest of the talks in the session, the number of microbes in one biological specimen. And then there's beta diversity, where you want to compare two patches to one another, and you're looking at the dissimilarity in the species assemblages between those two patches. And if you do many of those pairwise comparisons, you can build them up into a general picture of the similarities and differences among organisms in many samples. And these concepts of alpha and beta diversity really dominated microbiome research for a decade, from about 2005 to 2015. We were able to dramatically improve the rate of acquisition of the ecology data we needed to find out about complex microbiomes in 2008, when Micah Hamady, a very talented computer science grad student in my lab at Boulder, figured out that we could use formal error-correcting codes, such as Hamming and Golay codes, to tag the DNA that we amplified out of many different samples, and then mix the results from hundreds of samples together and sequence them at once on an expensive sequencing run from a sequencing instrument. And what we were looking at was one marker gene, the small subunit ribosomal RNA, which you can think of as being like a name tag for your bacteria. It's very phylogenetically conserved, so you can read out from many organisms what this particular sequence is and match it up to a database to find out who's there. And so in this one study, we looked at samples from cystic fibrosis patients' lungs, so an infectious disease example. We looked at rivers across North America. We looked at the air, an incredibly challenging low biomass environment that later became really important to study during the COVID pandemic. And then the Guerrero Negro microbial mat, the most complex microbiome we know of on Earth, although ironically NASA studied it as a model of simplicity because they thought the green things you see there, the cyanobacteria, was all that was in there, not the hundreds of other bacterial phyla. And so we collected 500,000 sequences on this run, and what you can see is that the sample types cluster beautifully together. We got a lot of information about each of these sample types that I won't go into, because what I want to focus on is the cost. So the 500,000 sequences we collected were about equivalent to the total number of those sequences that had been collected by the entire scientific community in the 20 years prior. And the Sanger facility down the hall from my lab at Boulder still charged $8 a sequence. So if we'd done it the old way, it would have cost $4 million and taken a decade. But with the then new 454 sequencing, it cost just $12,000, and we did it overnight. And so this approach was what opened up the Human Microbiome Project, the Earth Microbiome Project, the American Gut Project, which I'll talk about later, and many other large-scale sequencing efforts. But what's most amazing is that that amount of sequencing, it cost $4 million in 2007. We brought down to $12,000 in 2008. Today, it costs you just 75 cents. And that's amazing, right? That's how we can look at so many samples and so many experimental designs. The decline in the cost of sequencing makes this stuff feasible to apply at scale. And so in the Human Microbiome Project, we got the first overall map of how human microbiomes are arranged using a toolkit called CHIME, developed by Greg Cacapareso, then a postdoc in my lab, now a full professor at Northern Arizona University, using the Unifrac distance metric introduced by Kathy Lozapone when she was a PhD student in my lab, and she's now a full professor at the University of Colorado. And so you can see almost emerging like continents on this map, the oral, the skin, the vaginal, and the fecal microbiomes, which are very different from one another. So you want to think of yourself not having a microbiome, but having a series of connected microbiomes across your body, and we're just starting to understand how they connect and change. Now, focusing in on the gut microbiome, this ecological approach where essentially you find for groups of samples, do they differ in their alpha diversity and do they differ in their beta diversity, their community dissimilarity, led us to associate the microbiome with a whole lot of different processes, including its role in digestion, in the immune system maturation, in clearing pathogens, and even in things like brain development and behavior. But we're also increasingly finding it has a lot of negative effects. So when the microbiome goes wrong, it can lead to metabolic syndrome like diabetes, obesity, and so on, GI disorders, cancer, which you're going to be hearing more about in this session, and even neurological and neurodevelopmental conditions ranging from autism all the way to Alzheimer's. So the community ecology approach made a lot of really remarkable discoveries, including things like identifying the natural variation in the human microbiome, weather conditions, including obesity and IBD, two of the early ones we studied, decreased microbial diversity from a healthy state, and things like are the microbial communities different on average between healthy and diseased states. So therefore, might the microbiome have a lot to do with things that no one had any idea it was associated with. But the problem comes when you have ecologists interacting with clinicians, where once you start to get into medical topics, you get questions like, what do all those dots mean on those principal coordinates plots? What are the axes? How do you link that to some kind of medical reality that you understand? Did you find a particular pathogen for real, which is really difficult with the kinds of amplicon sequencing approaches I told you about that are relatively low resolution? Which species are really making the difference, which again you can't do if you don't have species resolution on your underlying data. And then the real challenge is this a clinical test, and basically everything I showed you there is research. And so community ecology using short-read data fundamentally can't answer these types of questions, although you can make a lot of really exciting scientific discoveries. So this led us in 2011 to explore the machine learning approach. And today we can build machine learning models that classify people or animals for a lot of different traits from their microbiome data. So for example, Dan Knights, who was a PhD student in my lab at the time and is now a full professor at the University of Minnesota, found that we could use random forest classifiers of microbiome data to classify an individual as lean or obese with 90% accuracy based on their microbial genes. Whereas if you do that from human genes, you can only do it with about 57% accuracy, even if you look at every mutation that's ever been linked to obesity by genome-wide association studies. Other researchers have shown that the microbiome affects the personalized impact of a huge number of drugs. So for obesity, you don't really need to sequence your microbiome to tell if you're fat or not. But if you want to understand, will you respond to a particular drug, that's invisible, and you really need to do the test to find it out. And if you do that test for painkillers like acetaminophen, for cardiac drugs like digoxin, anti-cancer drugs ranging from cyclophosphamide to the latest checkpoint inhibitors, whether they're safe, whether you'll respond, depends on the genes and those microbes in your gut. And we're now starting to wonder whether most molecules we ingest, whether they're drugs or food, whether the microbiome has a big impact on how our bodies respond to them. And this was taken to a really remarkable level by Aran Segal at the Weizmann Institute, who in 2014 published this groundbreaking paper in Cell, where he hooked 800 people up to continuous glucose monitors and then fed them a defined sequence of diets, and showed that how you individually release blood sugar after a meal is really different one person to another, even for the same foods. And so he measured a whole bunch of stuff for 800 people, including blood tests, questionnaires, body measurements, food diaries, and of course the microbiome. And one of the key findings from this paper was how different people are. So for many people in the study, and for many of you, you'd probably think of rice as a pretty healthy meal, right? But it turns out that for a substantial fraction of the population, it's worse for you to eat rice than it is for you to eat ice cream. And out of all of the things that they measured that were the deciding factor, essentially it was the particular microbes that people have. So on learning this, people typically have two questions. The first is there some sort of test I could do that tells me if I'm in the rice category or the ice cream category? So far, this only works for research in limited populations, but doing that for everyone would be really exciting. And then perhaps more importantly, suppose I do the test and I find out that I'm in the rice category. Could I change my microbiome to get over into the ice cream category? Which might sound frivolous, but in the case of drugs, where you want to find out if you're a non-responder to a drug and move yourself over into the responder category, that's deadly serious. So we're scaling this up in a project called Nutrition for Precision Health, or NPH, where one of the key parts of this is to develop algorithms that predict individual responses to food and dietary patterns. And this is Jack Gilbert, the other PI of the Microbiome Center that we lead at UC San Diego, in a sizable chunk of this $170 million investment from the Common Fund. And essentially the study design is to do 10,000 people cross-sectionally, and then longitudinal studies of 2,500 people at home, and then 500 people in an inpatient setting to really get to the bottom across many different biomarkers of what's most important to predict your response to individual foods, so we can produce better guidelines for the whole population. So machine learning can tell you a lot that you can't get at with ecology. For example, the classifier accuracy scores can tell you how accurately I can classify a single sample as being healthy or diseased. The feature selection algorithms usually tell you which particular features are most important for that classification, so you know what microbes are involved. And then you can tell if the classifier is robust and reproducible. So for example, in IBD, we were able to train classifiers on US populations of patients and apply them well in China. We were able to apply them all the way from humans to dogs. So you can get these very cross-generalizable classifiers that you can apply even across the species boundary. However, again, when you get to the interaction with clinicians, you run into trouble. So for example, they have a lot of questions like, what does classifier accuracy mean? What are all these acronyms that you have to learn about the machine learning stuff to be able to explain it to yourself or to patients? You want to know whether the features are causal, and essentially anything you can get out of random forest support vector machines, artificial neural nets and so on, are association, not causality. Again, you want to know what species are making the difference, which you cannot get at if you don't have species-level resolution input, which you typically don't with short-read sequencing methods, which are prevalent in the field. And then finally, there is a problem with how you explain this to patients, especially if it was a long time since you took calculus and you really don't want to explain different gradient descent algorithms or what a Jacobian is or any of that kind of stuff. So machine learning is still hard. Typically, to do it right, you need a large multidisciplinary team of people to work together across disciplinary boundaries, and it still can't answer these key questions that you need in a clinical setting. So this is where we're turning to AI, and I know everyone says that they're doing AI now, and you're probably sick of hearing about it. We launched the Artificial Intelligence for a Healthy Living Center as a joint project between UCSD and IBM back in 2017 that I co-directed for the first 6 years of its existence, and this was part of the AI Horizons network from IBM, initially focusing on the Watson technology, and then rapidly pivoting to other areas of AI. A lot of what I've told you about so far is conclusions that you draw on large populations, but we really want to be able to take this to the individual level. And the individual I'm going to talk about is possibly the least private person on Earth, so none of this violates medical privacy rules. It's my colleague Larry Smarr at UCSD, who's a physicist who got interested in the complex system of his own microbiome. And he's a very interesting individual because he's been releasing data about himself on the internet for the last 25 years, starting with one dimension, which was his weight over time, and then going to dozens of dimensions with blood tests, thousands of dimensions with human genetic profiling, and now millions of dimensions with the microbiome. And shortly after I got to UCSD in 2014, I had a meeting with Larry where I was explaining to him the Human Microbiome Project data set, much as I showed it to you earlier in the talk, in front of a 64 million pixel display wall. So this is a live rotatable image in 64 million pixels. And he said, well, you know, Rob, I have a very interesting microbiome myself because I'm an IBD patient. How do I get myself onto that map that you made of the microbiome? So shortly after that, this box showed up in my lab, the first one of many. Larry's still on dry ice. I told you he was an interesting character. And he'd actually been doing this for a while. So when we reprocessed all his data, this is what he'd been looking at. And this is the family level of different kinds of microbes in his gut shown with different colors over a period of 3 years. And don't worry if you don't see anything useful in that, because neither did Larry, despite spending some giant amount on sequencing and personnel effort to get to this point. So we reprocessed the data with our tools. In technical terms, this is a principal coordinates plot of unifrac distances between samples. And what you can see, this is just rotating the data frame. I'm going to animate it, and you'll see that he starts at one edge of the blue, and then his successive time points have him traveling through the blue region, crossing over into the red region, and then he bounces around basically at random in the red region. So what, you say? Well, what we can do is we can couple that to all that medical data Larry collected about himself. And what we can see is that this initial shift was caused by a course of antibiotics. This directional travel through the blue configuration space is when he's having frequent IBD symptoms and losing weight, and his life isn't very good. The switch is caused by a change in medications. And then for that region where he's bouncing around apparently at random in the red, his IBD symptoms are basically gone, and he recovers his weight back up to a healthy set point where he stays for about a year. And this is amazing, right? If we've been able to tell Larry about these different regions of configuration space, we could have told him, you know, while you're in this blue region traveling directionally, you really need to do something about that as soon as possible. When you're in this red region, even though your microbiome configuration is not changing, it's in a stable configuration where your health will improve. But the state of the art then was we could only read it out retrospectively, and what we need to do is we need to be able to model it predictively. So that wasn't the end of Larry's health journey, so now I'm showing you a few more years of it, and a few events are big enough that you can see them even on that taxonomy plot. So for example, he had to have 20 centimeters of his sigmoid bowel removed in 2016 as an attempt to cure his IBD symptoms. At about the same time, we were running the American Gut Project, where we looked at tens of thousands of people, citizen scientists contributing samples, and crowdfunding the project to understand what had a large versus a small impact on the microbiome. And on these power curves, what you're looking at is the number of samples per group on the x-axis versus the p-value of your significance test at the extremes of those groups on the y-axis. And so basically, the steeper the curve, the bigger the effect. And for things like age and antibiotics and travel and even things like alcohol and exercise, you can see the effect with a few hundred people down to a few dozen people for the stronger ones like age. But the largest effect is just the number of different species of plants you ate in the week before you sent in your sample. And that's fascinating because that's something you have complete control over, unlike your age, unlike disease markers that are not shown on this plot, but are at about the same level as salted snacks. And this turns out to also be true for the metabolome. So one thing we're doing a lot of at the moment is integrating the microbiome with direct chemical readouts of the gut with my collaborator, Peter Dorrestein. And if you eat more plant diversity, you also have more diverse molecular features when we look at your stool or when we look at your blood sample. So Larry saw this result, and he wondered, could he improve his microbiome diversity and therefore his health, not just by settling for 30 species a week, which was the top of his range, but by consuming 60 plant species per day. So he started making this green smoothie and drinking it every day. If you're interested in his actual ingredients, we have them on the MicroZeta website. So that's the umbrella project for the American Gut Project, including various international expansions. And this was also featured on the Emmy Award-winning Hack Your Health documentary, if you want a more entertaining view of this than I'm giving you today. However, I'll admit that the presenter of Hack Your Health had a pretty hard time understanding all those complex displays that I showed you, which are coming out of the ecological approach, and also had a pretty hard time understanding why anyone would actually want to consume this smoothie, given the ingredients that were in it. And having tried it, I have to say that I don't recommend it from a taste perspective. I only tried it once, and that was enough. But what it did have a big impact on was his blood glucose. So he'd been slipping from the normal range. So that line of 100 is basically the boundary between normal blood glucose and prediabetes. And so he'd been slipping into pre-diabetes and this transition into metabolic syndrome over the course of about 3 years. And the last 3 months of this, he had been eating vegan and gluten-free in an effort to reverse it, and you can see that it did absolutely nothing. But the green smoothies had a huge effect and put him right back down into the normal range for fasting glucose pretty much immediately and durably. And this was also coupled to a big decrease in his total fat, which he measured on his $100 Wi-Fi scale at home. He thought that result was too good to be true, so he went into the clinic and stood on a $17,000 scale, which confirmed the result, looking at a 36% drop in visceral fat specifically. So very large impact of, this, of introducing this plant diversity to his diet. And fascinatingly, most diet-based interventions, as well as most probiotics, don't change your microbiome enough that you look like a different person, because the differences in the microbiome between different people are really large. So your microbiome is probably 90% different from the microbiome of the person you're sitting next to. But Larry was actually able to become 5 different people over 8 years in terms of his microbiome configuration, especially with the surgery, which had a huge effect, the vegan gluten-free period, which had a big effect on his microbiome, but not on his health indicators, and then the green smoothie time-restricted feeding period in green here, which did have a big impact on him metabolically. So what we're trying to do is we're trying to take all of Larry's rich data and build a digital twin of him. And for manufactured products, digital twins are becoming the new normal. So for example, Porsche has a digital twin of every car they sell that predicts that components will fail before they do, so you can do preventive maintenance instead of having to call for rescue on the Autobahn or whatever. And this kind of thing has been applied to biological systems. The first attempt to do so was by Marcus Kovitz's lab back in 2012, looking at Mycoplasma genitalium, a very simple microbe with just 525 genes. But what you can do now is you can extend it to the whole microbiome using a technique called flux balance analysis on whole genome reconstructions. And so we've been doing some pilots on this with Larry, together with Enos Thiele at the University of Galway in Ireland. And the first pilot, looking at just 7 stool samples, what we saw was that some metabolites were 10 times to 10,000 times overproduced in Larry versus a healthy reference population. But we are now doing it with hundreds of samples that he's collected over the period of 15 years and doing it with much higher resolution methods to be able to give them a much better basis for the modeling. So right now, the digital twin we can make of Larry is pretty bad, right? It's crude, it's pixelated, it's low resolution, it's decontextualized from its environment. But what we want to be able to do, and we're doing this with a combination of long-read sequencing, transformer models, as well as flux balance models, and spatial omics techniques, we want a much higher resolution model that can contextualize them in different places, run counterfactual scenarios, and get accurate representations of his reactions. And so the big breakthrough here, performed by Omar Din in my lab, shown here, and Jake Minnick, who should be showing up here but isn't, a former grad student of mine who just started a faculty position at Baylor. What we've moved to is a long-read metagenomics approach, where instead of small fragments that span just 10% of a genome when we try to assemble them, you can get dozens of complete circular closed bacterial genomes from every sample. So we have a much better ability to read out the genome of the species and even the strain level that you need to make clinical decisions than has ever existed before. And this came out in Cell a couple of months ago. But the real problem is that even if you can read out a huge number of genomes at high resolution, still understanding all those thousands of Latin and Greek names is really hard. And the real problem we're trying to tackle is to build a user interface for our microbiomes. And what you want to be able to do is when you're standing there in the supermarket, confronted with 1,000 kinds of yogurt, is to be able to look at one with your phone and ask your phone in natural language questions about it. So I'm sure you've all used ChatGPT by now. We're calling this something related but a little different given the application domain we're targeting. But the idea is you should just be able to talk to your phone and ask it, should I eat this product I'm scanning to improve my health? And then if the answer is no, maybe you can use the phone's camera to highlight with augmented reality the other products that are on the shelf that you should eat instead of the one that you're considering. And what we'd ideally like to do is deploy this kind of thing everywhere. So the Gates Foundation has discovered that the best way to support child health is to support maternal health so that babies in the worst risk categories are born into healthier risk categories from the beginning. So you could imagine deploying this sort of thing in Bangladesh, for example, so that an expecting mother could ask, should I eat this fruit or vegetable or that one so that my baby will be healthy? And that might sound absurdly ambitious, but smartphone penetration in India is already up above 60%, and it's projected to be 95% by 2040. Bangladesh is only about 10 percentage points behind. So the idea that we can develop this sort of thing in high-resource settings like the United States and Hong Kong and Singapore, and then deploy it globally within the next 20 years is really exciting. So that's the kind of crazy stuff we're up to at the Center for Microbiome Innovation that I direct at UC San Diego, where together with over 140 faculty members, we're targeting a lot of hard problems like this in human health, in agriculture, in ocean health, and in all kinds of other things where the microbiome is involved. And so the really exciting prospect is that AI, unlike the previous generations of tools, may finally let us deliver what physicians really want and need in terms of translation and upscaling different kinds of microbiome data, including the old low-resolution data sets, getting explainable and accurate and personalized predictions, incorporating LLMs to make them friendly. And then I didn't talk about this here, but we're very excited about generative AI to design new microbiomes, new diets, new therapies from scratch from the ingredients with sufficiently large training sets. And then the natural language interaction we think is going to be really key, especially being able to ask for explanation of microbiome results trained on the trustworthy scientific literature rather than all of the internet. So together these advances will transform our ability to not just know about our microbiomes, but to actually use them. So with that, I'd like to thank the amazing people in my lab, in Peter Dorrestein's lab, my metabolomics collaborator, and the Center for Microbiome Innovation. And I would like to thank you all. Thanks again for the invitation to start off the session at the symposium, which I'm very much enjoying. And I look forward to your questions in the panel discussion. Thank you.
Thank you very much, Rob, for a fascinating talk. You have nicely shown us advanced computational tools unlock microbiome complexity, advancing personalized medicine, and shedding new light on the forefront of microbiome research. Now, I would like to invite Professor Herbert Tugg from the Medical University of Innsbruck, Austria, an international leader of liver inflammation and metabolic fatty liver disease research. He will show us latest insight on liver inflammation in the pathogenesis and as a therapeutic target in MASH. Welcome, and then Professor Herbert Tugg.
Good afternoon, ladies and gentlemen, dear Professor Yu and distinguished guests and listeners. It's a great honor and pleasure to be here. And I enjoyed very much the last lecture, and my lecture will also cover a bit the gut microbiome, but will focus on a disease which you will realize now is maybe one of the most common diseases in the world. But we have made major progress, and I think it's a quite exciting story now. So I will, in the first part, speak about inflammation as a key concept of MASH. I will then speak about driving forces, how inflammation is generated. And at the end, I will bring a bit about disease phenotypes and new look at those diseases and therapeutic targets. Well, we had a new classification, and the name is not so easy. It's metabolic dysfunction-associated steatotic liver disease. But it was the best name which could be generated internationally after a long discussion. So we now use MASLT, and we use MASH today because MASH is always then when MASLT develop inflammation. And you can see in the next slide, in 80%, by the way, 30% of the world's population have MASLT. 30%, so it's really an epidemic. And when you look at this, in 80% it's isolated fatty liver, which probably will not evolve towards liver cirrhosis in almost all cases. But in 20%, it's still the old name, but the slide is nice because it shows what happens. In 20%, we have inflammation. And inflammation decides on this disease, on the further nature of this disease. This means you develop cirrhosis, you develop decompensation, you can develop liver cancer, and very important here, and this is a concept which I want to bring today, it's not a liver disease, it's a systemic disorder. The liver is part of a systemic disease, and this is because first those patients die of cardiovascular disease, secondly they die because of extrahepatic cancer, and only third they die because of liver disease. Well, inflammation and fibrosis drive the prognosis of NAFLD. But why do only up to 20% of muscle patients develop liver inflammation? We do not know yet. We have no answers. And why are 80% of muscle patients protected from inflammation? Again, we have no answer. Well, I had the privilege 25 years ago to write with Anna Meidil in New England Journal of Medicine an article on cytokines inflammation in those diseases. And interestingly, at that time, people were asking, you're writing about a disease which does not exist. Well, times have changed. It's now again 30% of the population, and it's a major disorder. And we have developed in 2010 this concept. It's a disease hypothesis, and we called it the multiple parallel hits hypothesis, saying that various diverse hits cause liver disease, and hits outside of the liver, first coming from the gastrointestinal tract. It's not only microbe-based, but it's mainly dietary-based also, for example, fructose. And on the other side, the adipose tissue is very important. I have to say 90% of patients with muscle are obese. And in obesity, we have an ongoing inflammation in the adipose tissue, and those patients very often have systemic, chronic, low-grade inflammation. And the adipose tissue is a major source of this inflammation. We know from the circulating IL-6 that a third is derived from the adipose tissue. So again, signals outside of the liver are attacking the liver. I come back to this. On this slide, you can see when we look at liver tissue, we have an increase in pro-inflammatory cytokines, TNF and IL-1. And we call and believe it's sterile inflammation in the liver. I come back to this later, whether it's really sterile. Sterile inflammation means that, for example, damage-associated molecular patterns drive inflammation in the liver. And also other signals are very important, for example, uric acid as a second signal, which finally results in the production of interleukin-1 beta. But what are the players causing inflammation? Again, why do 20% develop inflammation? Is it lipids? Is it diet? We have heard a lot about diet just before, and diet is very important. Let's speak about lipotoxicity. Which lipids might be toxic? Many lipids are toxic. It starts with free fatty acids, and many of those induce inflammation, especially innate immunity. Hepatic free cholesterol is toxic. Sphingolipids like ceramide are toxic, well shown in preclinical models. And also dietary components, I speak about that later. Fructose induces MASH, fibrosis, and liver cancer in preclinical models. And even triglycerides, which are the main lipid in the liver in case of steatosis, are now considered rather toxic. They had been considered over a long time inert, but now, and I will show you at the end, clinical interventional studies, it looks that they are also toxic because triglyceride accumulation increases ceramide and causes inflammation. Now, this is a nice paper by our chairperson. So it has been published in Gut, and it nicely shows that a high cholesterol diet drives liver cancer after more than 1 year. And this was even associated with high levels of alpha-fetoprotein, which are typical for liver cancer. And in this study, it has been nicely shown that it was associated with an altered gut microbiome. So the interaction between diet and the gut microbiome, and it has been demonstrated that certain bile acids like taurocholic acid were also involved. Weight loss is an anti-inflammatory strategy. And we have done this study with Alexander Moschen quite a long time ago. Those were patients undergoing bariatric surgery. And after 6 months, we again took a liver biopsy and a biopsy of the subcutaneous fat tissue. Successful weight loss eliminates inflammation. It's a very powerful anti-inflammatory strategy. And you can see here there's expression of interleukin-1 beta in the adipose tissue decreases 10,000 times. And this is interesting. The concentration of IL-1 beta was 10,000 times higher than in the liver. So again, the adipose tissue is a major source of inflammation. So we have spoken now about the role of innate immunity in this disorder, but it's also important to recognize that adaptive immunity is very important, as shown in this study published in Nature, where we observed the appearance of autoaggressive T cells. So it's not only innate immunity, also adaptive immunity plays a major role in this disorder. What about pro-inflammatory diets? This is a preclinical study, but it nicely illustrates how high sugar acts onto the intestine. And you have to know we have there Th17 cells, which are regulated by certain bacteria. And when you consume high sugar, again, it's preclinical, but very important study, then you increase a certain bacterium called Faecalibaculum rodentium, but you displace those Th17 cells, and this causes metabolic disease. So it's a nice example showing how a dietary component, in this case high dietary sugar, interacts with immunity. And there are many dietary components which drive liver inflammation in muscle. High-fat diet, for example, we know that high-fat diet, even in humans, causes endotoxemia, so an increase in endotoxin in the periphery. Ultra-processed food, we have at least 2 countries in the world, like US and UK, where they make 50% of consumed calories. They drive inflammation. I mentioned fructose, high glucose, red meat, and sodium. All those components in a major way affect muscle fatty liver disease and play a major role. Let's come briefly to gut microbiota. Well, in this seminal study, published 1999, Anna Meidil's group has shown in this mouse, a VOV mouse that's a leptin receptor deficient mouse, that those mice have, first of all, intestinal bacterial overgrowth. Secondly, they produce increased levels of ethanol, and they have a damaged epithelial barrier. They have shown, of course, it's preclinical, and that's something we want to see with the patients, but we do not have yet. Using a probiotic, you can eliminate fat in the liver, but it shows something very important, the association between intestinal bacteria and the accumulation of fat in the liver. And we now know from many studies, this is one of Lomba's studies published in 2017, that we have a clear signature in the gut microbiome dominated by proteobacteria and E. coli in patients with muscle. We also have a decrease, for example, in Faecalibacterium brausnitzii, which is a very important bacterium having mainly anti-inflammatory and protective functions. And they were able, by a combination of various bacteria, plus BMI, plus diversity, plus age, to detect or to diagnose advanced fibrosis, something we will probably do in the future. This is a nice study from northern Germany where they followed almost 1,300 patients over 5 years. And again, they have shown that especially fatty liver disease was associated with a gut microbiome signature, proposing that the gut microbiota plays a role in this disorder. Let's come back to sterile inflammation. There is now even some evidence that bacterial DNA can be detected in the liver in those patients. So maybe the inflammation is not so sterile. Maybe bacteria, or at least bacterial components, are inside the liver and might contribute to disease and inflammation, something we have to learn in the near future. And this is from a recent article from our chairpersons in Nature Review Gastroenterology, clearly suggesting that a diverse set of bacteria are involved in this disease at various stages, either in the stage of steatosis, later in the stage of inflammation, MASH, or in the stage of cirrhosis and hepatocellular carcinoma. And finally, I want to stress that the intestinal barrier is so important in human life and in many diseases. And in muscle, we have an impaired barrier, as you can see on the right side, which means that the barrier is no more intact, that many components enter the liver, that the intestinal immunity is activated, that we have ongoing inflammation in the mucosa. So an impaired intestinal barrier is very crucial, again, for human health. And in many metabolic disorders, this barrier is impaired, and the gut microbiota plays a major role for a healthy barrier. But also certain liver cells are protective. And this is a very nice study where they have shown that there are so-called periportal Kupfer cells which are immunosuppressive, meaning that they control inflammation in the liver by the production of certain cytokines like interleukin-10. And those macrophages are under the control of gut microbes. And interestingly, they have demonstrated that certain bacteria, Odoribacteriacea, promote those macrophages, and that they have also shown that a certain metabolite is involved, namely a certain bile acid called isoallolithocholic acid. I spoke about inflammation. Well, muscle is a disease of systemic, chronic, low-grade inflammation. Again, 90% are obese. Obese patients have chronic low-grade inflammation. And in this very important study by Paul Ritka, they have shown, and I think this is very important for clinical medicine, that high-sensitive CRP was a stronger predictor of future cardiovascular events and death compared to cholesterol. Most physicians believe it's only cholesterol, but maybe it's mainly inflammation, and the inflammation generated by the gastrointestinal tract or by microbes might be very important. And as we have outlined in this article, of course, we have activation of innate immunity and adaptive immunity in MASH and MASLT, but we have overall systemic inflammation. And systemic inflammation might contribute to cardiovascular events and death, first, and second, to extrahepatic malignancy, which is also commonly driven by chronic inflammation. Let me briefly go to disease phenotypes. Of course, so far we thought it's one disease, but it's not one disease, and there are two landmark papers, in my view, this year, where they have proposed that we are dealing with different disease phenotypes. In the first paper, they have shown that there is an association between 6 previously unknown genetic loci and hepatic triglyceride content. I have to say, of course, genetics plays a role in this disease. There are quite some loci which now have been identified. And as you can see here, when you're doing polygenic risk scores, you can identify 2 different subtypes. One subtype has a more liver phenotype, and the other has a more systemic phenotype. telling us that there exist at least 2 phenotypes of this disease. One is confined to the liver, resulting in more aggressive liver inflammation. And the second is more systemic, resulting in higher risk of cardiometabolic diseases. This fits with a second paper, which was published in parallel, where they investigated the UK Biobank. And as you can see in the upper panel, it looks like one disease with a focus on the liver, but here you can see it's liver or cardiovascular disease, liver or more type 2 diabetes, telling us we have at least 2 clusters. One is liver disease with a low risk of cardiometabolic disease. The other one is the same risk of liver disease, but a much higher risk for type 2 diabetes and cardiovascular disease. So much more information into this area is needed, but I think it's a new start to see that patients might differ because they have different disease phenotypes. Now let's go to treatment concepts, because I must admit in the past 2 years a lot has happened, and I think this is a very good thing. Because so far we could do wonderful research about this disease, we could do wonderful preclinical studies, but we had nothing to offer for the patient. While we could say lose weight. That's fine, that's nice. We all know in clinical reality this is very, very tough. So of course we are all convinced we need a therapy, and we also need a therapy because muscle is now #1 of liver cancer in many countries in the world, first. And second, it's a major indication now for liver transplantation in many countries. So, of course, we need a therapy. And it's nice to realize that medicine had made progress, and I will show it to you in the next 10 minutes. So the first drug is resmetirom. Well, what is resmetirom? Resmetirom is a DHR beta agonist. DHR is thyroxine hormone receptor. Well, you will say, thyroid and liver, what is this? Well, this is an interesting interaction because that's the way, one of the ways how the thyroid interacts with metabolism. And this was a very important study published last year. And they have clearly shown, and I usually do things you're looking for. On the left side, you look at resolution of MASH, no worsening of fibrosis. You see a significant effect. And the second thing we look is fibrosis improvement by at least 1 stage with no worsening of NAFLD activity score. On the right side, you can see improvement in LDL cholesterol, which is something we want to see in this disorder, as we are speaking about a systemic metabolic disorder. Well, this drug was approved in the United States and in Europe this year. It was a rather safe drug with almost no side effects. And when we look at mechanisms, I think it's important to mention that when we speak about muscle, then we have a lot of fat in the liver. And the fat in the liver plays a role with the metabolizing of FT4, that's thyroid hormone, by a certain deiodinase towards an inactive metabolite. So in muscle, we have a lack of active FT3, one of the thyroid hormones. And the drug we are administering is activating this receptor and have a major impact on things which are important in muscle. For example, decrease in de novo lipogenesis, improvement of lipotoxicity, improvement of inflammation, improvement of fibrosis. Well, let's go to the next drug, and most of you are aware because I don't know the name in Japan, but at least in many other areas of the world, it's Ozempic or it's Wegovy, and it's GLP-1 receptor agonists. Drugs you are aware which are highly effective in the sense of weight loss drugs. What about muscle? So this was the paper published this year, a large study where they used 2 different concentrations of of semaglutide. And as you can see here, again, resolution of steatohepatitis and improvement of liver fibrosis, both effects being highly significant. So it appears it is the second drug which is effective in the treatment of MASH. And as you can see here, there was also an improvement in the liver fibrosis score, and especially when you're doing transient elastography, which is something we are doing now clinically with those patients, you can see a significant improvement by this drug after treatment of 1 year. And not surprisingly, but importantly, semaglutide improved the blood pressure, glycated hemoglobin, high-sensitive C protein, so it's anti-inflammatory in addition, and it improves lipids, triglycerides, and cholesterol. And there are newer drugs coming now so far in phase 2 studies, but tirzepatide and also tirzepatide, as shown here, improves liver values, so it's obviously effective, and the phase 3 data are still out. And another drug, which is a so-called dual agonist, so activates not only GLP-1 receptor, but also glucagon, and the first results are very promising. So we have 2, and we have many more in the pipeline. And I come back to lipotoxicity because, as said, we believe triglycerides are inert. They are not. And this paper has just been published in The Lancet, and it's the third therapy where they used antisense oligonucleotide-based therapies to target triglycerides. And as you can see here, highly effective as the 2 previous mentioned drugs. So it looks like we will get a third drug. And for me, importantly, it proves the concept of lipotoxicity. It's the first time this concept has been proven in patients, and therefore I believe it's very important and relevant. And here they have, for example, shown that in 50% with this drug, you can eliminate liver steatosis. Well, this brings me almost to the end. Treatment recommendations beyond lifestyle modification in patients. We will always recommend lifestyle. We will always recommend dietary approaches. We have just heard before how important dietary approaches are. We, for example, know when we use a high-fiber diet in type 2 diabetes, we can improve glycated hemoglobin similar to a drug. So diet is very important, is very effective, but is very tough for the consumers and for the patients. So we have now at least 2 therapies I discussed with you. Of course, we have the other drugs which are used in the management of type 2 diabetes. And of course, we use in most of those patients statins. And a lot of new drugs are coming. And I only briefly mention FGF21 pathway, PPAR pathway, and FGF19. Those are 3 very promising pathways. So in the next years, we will have probably other effective therapies in the management of MASH. And finally, I just want to spend 1 minute. How might those drugs be effective? Semaglutide. Now, they have shown in this Nature Medicine paper, when they did an aptamer-based SomaScan assay, that semaglutide acts pleiotropic. What does this mean? It affects so many pathways, and it acts anti-inflammatory and anti-fibrotic. And this has been commented here. So it suppresses fibrosis pathways, for example, ADAMT-SL2. It induces certain anti-inflammatory pathways. But, and this is very important, it works in a liver disease, but there are no receptors expressed in the liver, in hepatocytes. How can this happen? And we have also commented on this study in Nature Reviews Gastroenterology. Again, it works in the liver, but there are no receptors for this drug in the liver. So it must be effective outside. Of course, it's very pleiotropic. Semaglutide acts in the brain, in the small intestine, in the large intestine, in the adipose tissue, in the pancreas, outside the liver, but not in the liver, but it works in the liver, and I think this is fascinating. And this also fits in a way with our hypothesis, which we made in 2010, because we said at that time, extrahepatic signals are the major drivers of this liver disease, and the efficacy of semaglutide fits very well with our hypothesis. Dear Chairperson, dear Professor Yun, dear colleagues, I may conclude it's an epidemic. It's 30% of the world's population. Inflammation is of crucial importance because it's the driving force of fibrosis. Not all patients will have inflammation with a fibrosis, but most will have first inflammation and then fibrosis. Many pathways lead to inflammation. It's lipotoxicity, it's diet, it's the gut microbiome. It's a very complex world of interactions who finally lead to this disease. When and whom to treat is clinically very challenging now, will be challenging in the future, but we will develop tools, maybe some multi-omics, machine learning, AI data from the gut microbiome. I do not know, but we will develop those solutions. We need a pleiotropic mode of action for those drugs. Liver alone is not sufficient. It's a prototypic systemic metabolic disorder. But multiple new treatments are coming. We'll have many more in the future, so I think the future for this disease looks very good. Thank you very much for listening.
Thank you so much, Herbert, for this profound, insightful lecture and to clearly show the dialogue and connection between diet, gut microbiome, and the connect to the liver, inflammation, MASH, and also the targeted therapy, especially for MASH inflammation and MASH fibrosis. Thank you. And then, and following these two fascinating lectures, I'm very happy to share our recent research on gut microbiome in gastrointestinal cancer and from basic discovery and to the potential clinical application. To first evaluate the correlation between gut microbiome and cancer, especially colorectal cancer, we did the population-based screening to show whether microbiome altered in CRC patients, colorectal cancer patients, as compared with healthy subjects, including the Chinese population, Germany, French, US, and Austria. And based on the population-based screening, we demonstrating that based on this heat map, and also you can see, and then the ecological network, and based on the identified bacteria, they are quite different in terms of composition and also the ecological network. And then this is based on the stool samples, and I move on to the tissue biopsy, also the multiple cohort from normal and the paired adenoma, paired colorectal cancer, to see whether this change of gut microbiome is an early event or consequence. And based on the screening and by this biopsy tissue to identify tissue adhesion bacteria, also identify change of gut microbiome occur at early stage in patients with adenoma. And this change is more profound than in colorectal cancer. And based on discovery, we want to answer whether this change of gut microbiome in colorectal cancer patients, whether it can contribute to the colorectal cancer initiation and progression. And based on this question, we pulled the stool samples and from the colorectal cancer patients and also the stool samples from healthy subjects and gavage to the germ-free mice without any additional treatment. And in this germ-free mouse model, we're demonstrating that stool from colorectal cancer patients can spontaneously trigger the enhanced cell proliferation, enhance the pro-inflammatory factor expression, and also enhance the pro-oncogenic factor. And based on this observation, and then especially from the germ-free mouse model and with observation, we're demonstrating that the gut microbiome in colorectal cancer patients is toxin. So we have the group of enriched bacteria and the depleted bacteria in colorectal cancer patients based on multiple population. And then based on the enhanced bacteria, choose one example, the Streptococcus anaerobus. And this study, we're demonstrating that you can see, and based on the electron microscope, and these bacteria have active interplay and with the colon cancer cell line, but not somehow it's a silence, it's a quiet, and with the normal epithelial cell. And then we're demonstrating that this bacteria surface protein can bind into the receptor protein, the integral F2 beta 1 in the host epithelial cell, colon epithelial cell, which can activate the PI3K AKT oncogenic signaling pathway and therefore promote the cell proliferation. At that time, we also performed single-cell sequencing and demonstrating that these bacteria correlate with the suppressed immune microenvironment. And then we further evaluate how these bacteria play a role in suppressing the immunomicroenvironment in colorectal cancer. And my second postdoc fellow, Ya Li, and who is my PhD student and also postdoc fellow, he focus on multiple mouse model, and then both of them can demonstrate enhance the MDSC and also the number and also the activity. And based on this observation, we put effort to identify mechanism how these bacteria can induce and then MDSC infiltration and also the activation of tumor suppressive immune cell MDSC. So we, from the host, and because the bacteria have a direct interplay with the host, we're demonstrating that the bacteria interplay with the host cell by activating PI3 AKT signaling pathway can further induce activation RKB and therefore release pro-inflammatory cytokines, for example, CXCR1. And CXCR1 can bind into the receptor and CXCR2 to recruit this MDSC cell to the tumor site. We try different model and different cell line. It can just recruit in the tumor cell but cannot activate MDSC. And then we further to identify how these bacteria can activate MDSC. And then we're demonstrating that bacteria produce a protein, LYTC22, binding to MDSC receptor. And this binding can activate this MDSC activation in the tumor site. And therefore, the activation of the MDSC and the recruit to the tumor cell and then can suppress anti-PD-1 therapy. Based on this observation, we want to block two receptors to see what's happened. We block the host connection and also block the bacteria produce the protein and binding to the MDSC, and then reversed the resistance to sensitive for anti-PD-1 therapy. So this is one example. We identify the pathogen that can induce, promote colorectal tumorigenesis. And then we move on to the gastric cancer because the gut microbiome closely correlated with the gastrointestinal cancer. And the recent study have demonstrating that screening of H. pylori alone is not sufficient to prevent the incidence or reduce the mortality of gastric cancer. Another study also showed that the long-term follow-up for 14 years, community-wide H. pylori eradication only just slightly reduced the risk of gastric cancer incidence in high-risk population. Our question is that we need to identify additional bacteria in gastric cancer. We also do the multiple population to see the change of microbiome and based on the biopsy tissue from superficial gastritis, precancerous lesion, atrophic gastritis, intestinal metaplasia, and also gastric cancer paired biopsy. And based on the screening, the bacterial screening from the tissue sample, we identified Streptococcus anaerobus as the top enriched bacteria in cancer tissue as compared with non-cancer tissue in the stomach. And another study, because we have in the high-risk area, we do the random H. pylori eradication. We want to see, after H. pylori eradication, if there's any other bacteria can contribute to the persistent progression of precancerous lesion. And this study, we follow up 1 year. So, and this is from the subject, the high-risk population-based study. We have a random H. pylori positive cases. We randomly treat with placebo and treat with the antibiotic eradication therapy. And then we screen the baseline after 1 year follow-up with or without H. pylori eradication to see the bacteria that correlate with the persistent progression of the disease, especially precancerous lesion. We do identify to see, you can see the red color, and then there's a group of bacteria that correlate persistent atrophy intestinal metaplasia. And then we overlap this precancerous lesion, persistent progression after H. pylori eradication, overlap with the enriched bacteria in the stomach. You can see, and these overlap bacteria again, Streptococcus and Robus occur again as one of the bacteria correlated with the persistent progression of the precancerous lesion, atrophy, intestinal metaplasia, and also chronic gastritis. We have the question, what is bacteria for as angionosis? And based on the literature review, is this bacteria just caused, and based on name, it caused the infection? The correlation of these bacteria in cancer is totally unknown. We have the question, because H. pylori just a trigger factor induce acute chronic inflammation. One change to precancerous lesion due to the enhanced pH level, bacteria will left. So what happened for this one? We do the different time point at the 2 weeks post-infection. We choose H. pylori as a positive control. It can induce acute inflammation. All the histology evaluation was done by our 2 senior pathologists in our hospital. And then what's happened without any treatment, only this bacteria long-term treatment. So with the conventional mouse model or germ-free mouse model, the long-term treatment 6 months, 9 months, 12 months, we demonstrating that these bacteria alone can spontaneously cause chronic gastritis, atrophy, metaplasia, and dysplasia. And then only this alone is not only an early trigger effect, but the persistent all the progression from the gastritis to precancerous lesion. And also this bacteria can promote gastric cancer in multiple mouse model. And based on this observation, we spent some time to evaluate the mechanism of how this bacteria interplay with the gastric epithelial cell to promote initiation precancerous lesion and promote gastric carcinogenesis. We identified bacterial surface protein, TMPC binding to the receptor and actin A2 and trigger oncogenic signaling pathway, and summarized in this picture at the acute situation, and this binding to produce a pro-inflammatory factor, but the long-term infection can promote MAPK, JNK oncogenic signaling pathway. If we knock out the TMPC, this protein, surface protein from this bacteria, and this effect will totally abolished. So confirm, and this is a new pathogen and contributing to the initiation, the whole stages progression of gastric carcinogenesis. So let's move on to the potential clinical application, and based on the microbiome research, the first one, whether the depleted bacteria, are they good, are they potentially protective? And this is based on the multi-population-based study, Asia, and also the Western people, because we want to identify a common feature that correlates with the disease, colorectal cancer. This is the depleted bacteria. We set the mouse model and provide this bacteria can significantly prevent the colorectal cancer progression. So, and then we identify this bacteria produce the enzyme beta-galactosidase, and then this is a functional enzyme. If we knock out the enzyme related gene, lactate gene, and then the protective function will be gone. We also evaluate the molecular mechanism of how this bacteria produced beta-galactosidase, contributing to the suppression of colorectal cancer is mainly by suppressing Warburg effect. And then we move on to Second, the candidate, depleted bacteria. And this by depleted just in female colorectal cancer patients, but not in male. And then based on the mouse model, demonstrating that this bacteria only suppress the colon cancer in female mice, but not in male mice. And based on these multiple observation, and we did the mechanistic investigation, and we demonstrated that this bacteria attached to the colonal site. The receptor is estrogen dependent. The SLC3A2 is a receptor in the colonal site and from the intestine, and that with the receptor, and that this bacteria can colonize and stay and produce, harmful metabolite 7-DHC, and further and transfer to vitamin D to protect against the colorectal cancer. So the protective bacteria have a gender difference. And this bacteria, good bacteria package, and then we transfer to a local company, my colleague, and then open a company, and they are working on the clinical trial. They are finished the year 1 clinical trial, focused on the adenoma patients after removal of the adenoma under endoscopy to see whether produce these probiotics to suppress the relapse of colorectal polyps or adenoma, and long-term whether it can prevent the colorectal cancer. But not now. Right now, it's just a short-term clinical trial. They finished the year 1, already published the paper, and this probiotic formula can suppress the colorectal cancer in enriched beta bacteria, pathogenic bacteria. Another bacteria, and this is this unpublished data, based on the population based on a large sample size, and this bacteria particularly depleted in gastric cancer. So we want to identify gastric cancer probiotics as well, and also this bacteria based on the network analysis cohort, a large cohort, and these bacteria have a negative interplay with H. pylori. And based on this initial evaluation, we're demonstrating that this bacteria can suppress H. pylori infection, no matter it's SS strain, the common strain, or antibiotics resistant H. pylori strain. They successfully suppress and this bacteria, the H. pylori growth, and also the H. pylori infection. And based on in vitro study and in vivo mouse model, further, we're demonstrating that this bacteria can also suppress gastric carcinogenesis. And we have the different mechanistic investigation mainly, and this bacteria can produce butyrate. And that number one, this bacteria can compete the common receptor, which H. pylori. The common receptor is ENO1. This is step 1. And step 2, this bacteria produce butyrate. And this butyrate can suppress the H. pylori inside H. pylori ATP synthesis, and therefore suppress H. pylori growth. Number 3, and this bacteria produce butyrate, can suppress oncogenic signaling pathway, Wnt beta signaling pathway, therefore, and suppress gastric carcinogenesis. So we move on to number 2, and then the potential biomarker for microbiome. You can still remember under the heat map the different abundance of gut microbiome in cancer patients as compared with the normal subjects. So we pinpoint and these important or major player as a biomarker for colorectal cancer or adenoma. So we treating F1 is Fusobacterium nucleatum, another bacteria named M3 because it's a new one. M3 is good for adenoma. Fusobacterium nucleatum is good for colorectal cancer. We have the 4 bacteria package, and this package compared with the FIT, they have a good performance. It's better to early stage of colorectal cancer as compared to FIT. You can see the blue column as compared with the green column. They have a significant difference. And also, this we listened to our colleagues' company, and they developed the M3 CRC detection kit, now apply in the clinical side in Hong Kong and some Asia-Pacific region. And we continue to look up whether we can also, because in the clinical side, you ask the patient to contribute the stool sample, is somehow not that easy. You ask them to contribute the blood, it's quite easy. So we want to see whether we can identify the metabolic panel as a diagnosis marker for colorectal cancer. We do a multiple population, 1 discovery cohort, 3 validation cohort, in total over 1,000 subjects. We did the shotgun measurement synchronicity for stool and the metabolomic assay in stool and the plasma, and also cytokine profiling. And then the plasma metabolomic have a good performance as compared with the stool. So I just show the plasma metabolomic feature in normal control, and then in the middle is adenoma and the colorectal cancer. You see there is a shipment from normal to cancer, increased or decline metabolites according to disease progression. And based on this observation, we identified the metabolomic panel. It can significantly distinguish colorectal cancer versus control, early colorectal cancer versus control, and also colorectal cancer versus adenoma. We compare to the FIT, and these plasma metabolomic panel have a good performance to distinguish the colorectal cancer, especially early, and as compared to control subjects. And this as a cover story and just a sample publication in last year. And this is a biomarker, and working with the company and hopefully to translate. And before that, we have the multi-cohort validation to confirm, to prove, and this plasma metabolomic marker is good and for the potential clinical utility. Finally, I would like to briefly introduce the modulation of the gamma micron metabolites in immunotherapy. So, in colorectal cancer, not like other kind of cancer, is the opportunity to use anti-PD-1 inhibitor and the checkpoint inhibitor is not optimum. It's just 15% or 10% is suitable and for the anti-PD-1 therapy. So we want to see whether the changed gut microbiome metabolites can change immune cold tumor to immune hot tumor. And Max, my postdoc fellow, we focus on the Clostridium butylicum. It's a depleted bacteria in colorectal cancer patients. And then we want to see, and because based on the pan-cancer analysis, we're demonstrating that this C. butylicum have a positive correlation with the responders in other cancer types, melanoma, liver cancer, renal cancer, and also the lung cancer. So we want to see whether this bacteria, because the information on colorectal cancer is not available, and based on the pan-cancer analysis correlated with the immunotherapy, we set the different mouse model and demonstrating that this bacteria do and suppress the tumorigenesis and improve the anti-PD-1 efficacy in multiple mouse model, and especially in MSS mouse model is the anti-PD-1 resistance mouse model. So, and based on this observation, we're demonstrating that how this bacteria play a role in increase the efficacy of anti-PD-1 therapy. And based on the mouse model, we also consider whether this bacteria produce the function to increase the anti-PD-1 efficacy is a potential clinical impact. And then we perform the humanized mouse model and prove that this bacteria, C. butylicum, can inhibit the colorectal cancer by enhance the CD4 T cell activity in this humanized mouse model. Again, because we want to consider it's more close to the clinical side. And we have the organoid from colorectal cancer patients. We also have the autologous tumor infiltrating T cell, the TILs, from the same patient. We co-culture C. butylicum with TILs and then treat, and this the same patient organoid. And we have the repeated experiments. We select MSS and MSI, immunosensitive, immunoresistant colorectal cancer. Both C. butylicum can activate TILs to enhance the anti-PD-1 efficacy and with a significant induction of CD8 port T cell. And this, we summarize the mechanistic observation. The bacteria itself, the surface protein SAD, can bind to the colorectal cancer surface receptor GRP78, and which one can reduce the secretion of interleukin-6, and therefore unblock the that can enhance the CD4 T cell activity and then induce tumors associated Okay, and leading to the reduction interleukin-6 and increased activity of CD8 T cell. And this number one. Number two, we did the humanized mouse model and organoid together with the Tu's mouse model to prove and these bacteria have a potential application in the future to possible the screening and in clinical and as an adjuvant treatment in the clinical side. So, and based on this study, we also identified a few other bacteria can trigger the anti-PD-1, the boost anti-PD-1 therapy by trigger the CD8 T cell activity or suppress the Treg activity or suppress MDSC activity. They can change the immune cold colorectal cancer to immune hot colorectal cancer. Our study also summarized in some invited review articles and then to summarize our discoveries and discovery from outside from other scientists in terms of the basic research or translational research. And based on this invited review article, we can recognize that the study for microbiome is a shift from the basic interplay investigation, mechanism investigation, to potential clinical application for prevention therapy or targeted therapy or adjuvant therapy. So I would like to thank my team members, and some of them are sitting here in this session for their particular hard working and particular contribution to the individual project. I also would like to thank the clinicians and scientists from the Institute of Digestive Disease and the State Laboratory of Digestive Disease. Thank you so much. According to the concept of this important symposium, we need to encourage the young faculty to be here as an invited speaker. So our last speaker is Dr. Bingqing Yao from Yale University. Bingqing Yao, yeah. On behalf of the Professor Cai Shang, she will present a fascinating talk entitled The Ins and Outs of Intratumor Bacteria in Breast Cancer Malignancy. Welcome, Bingqing.
Thank you. Thank you for kind introduction. It's such a pleasure for me to represent Shang to join this symposium and discuss cancer microbiome. Our lab focuses on the intratumor bacteria and host cancer cell interaction. So today, I'm gonna show you a very interesting story about how intratumor bacteria invasion influence the breast cancer cell metastases. If I sound a little bit nervous, please forgive me because I'm so excited to be here as a postdoc. So first, let's think about cancer. Cancer is a very complex ecosystem and is composed with many cell types, including the cancer cells, endothelial cells, fibroblasts, and all kinds of immune cells. And all these contribute to the heterogeneity of tumor microenvironment. And interestingly, the tumor microenvironment has been characterized as hypoxic, necrotic, and immunosuppressive, and it's proposed to be favorable for bacterial growth. However, it is very challenging to detect bacteria in tissue samples because of its low abundance. So it's highly debatable whether these bacteria are coming from the environment or from the tumor tissue samples. Actually, the researchers in this field try to figure out these questions, and in 2020, River Stresemann lab optimized the bacteria DNA detection methods and claimed that intratumor bacteria are broadly present in tumor tissues, including those which were thought to be sterile, like brain, bone, and breast tissues. And our lab also improved the bacteria DNA characterization methods in tissue samples, and we reported that in the murine spontaneous PMT breast cancer model, there are culturable bacteria in breast tumor tissues, and the most abundant bacteria are coming from the Staphylococcus, Streptococcus, Enterococcus, and Lactobacillus, which are commensals for the host. And actually, these intratumor bacteria are not just passengers. Both correlative and functional studies review the key roles of intratumoral bacteria in drug resistance, cancer initiation, metastasis, and immunoregulation. And interestingly, the engineered intratumoral bacteria showed promising efficacy in cancer treatment. And in addition to these diverse physiological functions of intratumoral bacteria, researchers in this field study to appreciate that the bacteria can not only live in tumor tissues, but also inside the tumor cells. The first report in 1965 showed bacteria inside tumor cells in a spontaneous new tumor and proposed that this kind of intratumoral bacteria can be a causing agent for tumor formation. And several years ago, Rivers Strassman lab, using correlative light and electron microscopy, found that the bacteria are closely related to the intracellular, related to the host cell nucleus. And our group also observed the intracellular bacteria in a spontaneous murine breast tumor. So it is very interesting to think why the bacteria localize in the cytosol and what's the physiological meaning of it. In our previous work, we're using antibiotics to deplete intratumoral bacteria specifically and found one of the major physiological functions of intratumoral bacteria is to promote long metastasis colonization. And the mechanism is that the bacteria inside tumor cells can reorganize the cancer cell cytoskeleton and help cancer cell resistance to fluid shear stress. So the tumor cell with bacteria can survive and colonize better in the distant organ. However, the metastasis is a multi-step process. The mechanical stress takes in action during the very early stage of metastasis. For example, here, if we inject PUMT Lucifer's tumor cells back into mice through the tail vein, and we can observe drastic reduction of cancer signals in the lung, no matter in FVB immunocompetent mice and immunocompromised mice. And however, in the later stage, only the immunocompromised mice can allow cancer cells to efficient relapse. So this indicates that there is a second wave of surveillance by the immune system to kill the rest of metastatic cancer cells. In light of our previous discovery that circulating tumor cells, particularly circulating tumor cluster cells, contains amounts of bacteria. So our scientific question here is, when the circulating tumor cells carry bacteria to the distant organ, do these bacteria remain function during immune surveillance in the later stage of metastasis? So to answer these questions, we established the in vitro bacteria and the tumor organoid co-culture system to mimic circulating tumor cells containing bacteria. And here we use Staphylococcus dialysis, which is a predominant bacteria in primary tumor tissues, and we add penicillin, streptomycin antibiotics to the co-culture system. These two kinds of antibiotics are cell impermeable, so it can kill the extracellular bacteria efficiently. So you see from the 3D co-culture reconstructed view of tumor organoids, we can observe that the bacteria, most bacteria are inside tumor cells. And the further EM analysis confirmed the existence of intracellular bacteria and showed high efficiency of intracellular bacteria invasion. So this co-culture is a very nice system to study the intracellular bacteria. So using this co-culture system, we ask, after the first wave of mechanical stress, whether the bacteria still play function in the later stage of metastasis. So we injected PUMT Lucifer's organoids with bacteria back into mice through the tail vein, and after tumor organoids home into the lung, we treated one group with doxycycline, which is a cell-permeable antibiotics, can specifically deplete intracellular bacteria. Very interesting, as we checked lung signals in the cancer signals in the lung, and we found the presence of bacteria can efficiently for the cancer relapse, while the doxycycline to deplete intratumoral bacteria inhibit cancer recurrence. And the cancer recurrence inhibition effect is not due to direct cancer killing by the doxycycline, because when we did the same experiment in the immunocompromised NPSG mice, the inhibition phenomena was completely disappeared. So this suggests that doxycycline-mediated relapse inhibition is immune-dependent and probably due to the depletion of intratumor bacteria. So we asked which kind of immune cells respond to the intratumor bacteria firstly. So we injected the tumor cell and the tumor cell with bacteria back into mice through the tail vein and profiled long immune infiltration. And we found that the neutrophil is the major corresponding cell to the intratumor bacteria. And other immune cells didn't show the significant change. And the tail vein injection model only mimics some steps of metastasis. So we also tested under physiological condition whether elimination of intratumor bacteria can reduce the neutrophil population. So we performed the experiments on germ-free mouse model to avoid gut bacteria interference. So you see here, the bacteria-containing tumor group showed a strongly increase of neutrophil infiltration, while antibiotics to deplete intratumor bacteria efficiently decrease it. The neutrophil is the innate immune response cells, so it is reasonable for neutrophil increase under the existence of bacteria. But the question here is, when the bacteria are within the tumor cells, how neutrophils sense and respond to the bacteria? Actually, neutrophils are heterogeneous in tumor microenvironment, and both anti-tumor state of neutrophil and the pro-tumor state of neutrophils have been described in literatures. So here, our hypothesis is that intracellular bacteria can convert neutrophils into a pro-tumor state and reshape the immunosuppressive microenvironment and promote long metastasis recurrence. To test our hypothesis, we set up 4 groups: PBS, bacteria-free tumor, out-bacterial tumor, in-bacterial tumor group, to do single-cell RNA-seq of long immune cells after tail vein injection. And very interestingly, when we analyzed the neutrophil state, we found extracellular bacteria promote neutrophil anti-tumor score while decrease neutrophil pro-tumor score. And on the contrary, intracellular bacteria can enhance pro-tumor neutrophil while suppress anti-tumor neutrophil. Now, the question here is how bacteria-invaded tumor cells determine the neutrophil state. We went back to our previous single-cell analysis of bacteria-invaded tumor cells and asked how host cell respond to the bacteria invasion. So after the single-cell analysis, we found that except the bacterial infection and NF-kappa B related pathways, IL-17 pathway is the most enriched pathway after bacterial invasion. We then checked all the ligands of IL-17 families, and the most frequent studied IL-17A and IL-17F don't express in the tumor cells and the tumor cell with bacteria. It is IL-17B upregulated in the tumor cell with bacteria. And IL-17B is very different from other IL-17s because it is specifically expressed in epithelial cells, not immune cells. So we wondered whether IL-17B can mimic intracellular bacterial function to mediate neutrophil reprogramming. So we treat neutrophils with IL-17 protein directly, and we found that neutrophils were reprogrammed to the reprogrammed to a state that significantly suppressed T-cell activation by testing the IFN gamma expression. And more interesting, if we overexpress IL-17B in tumor cells, and we can find that it is sufficient for tumor cells to escape immune surveillance and give rise to efficient relapse. And all these experiments suggest that the extracellular bacteria all these experiments suggest that intracellular bacteria may reprogram neutrophil state or prevent metastasis through IL-17B. But the question here is whether extracellular bacteria can turn on IL-17B or not. Well, to answer these questions, we designed 2 experiments. The first one is transwell experiment, which allow us to separate the intratumor bacteria and the host cells. So you see here, only the bacteria invaded the tumor cells upregulate IL-17B, while when the bacteria is spatially separate with the host cells, the IL-17B expression don't change. And another experiment is cytokinase D treatment. Cytokinase D can depolymerize the actin filament and inhibits endocytosis and the invasion of tumor bacteria. So after the cytokinase D treatment, the IL-17B upregulation by bacterial invasion was strongly abolished. So these 2 experiments tell us that IL-17B upregulation is intracellular bacteria-specific response. So we wondered whether this dedicated mechanism holds true in the human system. To answer this question, actually we have been collecting the human breast cancer samples for 5 years and found that the bacteria truly exist in the human tissues by imaging. And we also try to isolate the human breast cancer specific Staphylococcus, and the statistics results show that in human breast tumor tissues, the most abundant Staphylococcus is epidermidis. It's not different from the Staphylococcus zealosus in the mouse samples. We then use the isolate human breast cancer specific epidermidis to co-culture with the human breast cancer cell lines and do the bulk RNA-seq of tumor cell with or without bacteria. So you see here the tumor cell with bacteria invaded show different gene signature and enriched IL-17 signaling pathways. All this is highly consistent to our mouse data. And in addition, we also isolate neutrophils from healthy donor, and we found that the live bacteria invaded the tumor cells can reprogram neutrophil into suppressive state, which highly expressed as 100A8A9, PDL1, 6L2, PTGS, while the dead bacteria, which we presumably cannot inside the tumor cells, cannot do that. So next question is, how bacterial invasion of cancer cells influence breast cancer patient survival? Well, to answer these questions, we assembled Staphylococcus epidermidis invaded gene signatures from our bulk RNA-seq data and stratified the human patients into high-level and low-level gene expression of bacterial invasion. So you see here, the worst prognosis are significantly correlate with the bacterial invasion gene signature. And similarly, the neutrophil response to Staphylococcus epidermidis tumor cells and IL-17 pathway are all significantly prognostic. So this data show that bacterial invasion is actually can be a cancer prognosis. Can be a biomarker for worse prognosis for human cancer patients. Well, the last question is, can targeting intracellular bacteria improve post-surgery cancer outcomes? To answer these questions, we set up a model to mimic clinical condition. First, we injected bacteria containing tumor cells, and when the tumor grew into a certain size, we did a surgery to remove the primary tumor, and then treated one group with doxycycline to deplete intratumor bacteria. And very interestingly, after surgery, the doxycycline treatment can still have function and strongly suppress the long metastasis recurrence. And the recurrence rate was reduced from 80% to 20%. And according to our single-cell analysis, the extracellular bacteria play opposite roles from intracellular bacteria in immune regulation. So here we decided to use the bacterial cell wall component, PGN and ILPS, to represent extracellular bacterial effects. After the surgery, we treated the mice with PGN and ILPS, and we found that extracellular bacterial component treatment can strongly decrease long metastasis recurrence. So all these experiments show that appropriate management intratumor bacteria can benefit the cancer patient after surgery and prevent cancer metastasis recurrence. Finally, to summarize our work, we found that in addition to mechanical stress, the intratumor bacteria are important for cancer cells to cope with immune in cancer metastasis relapse. And interestingly, the extracellular and intracellular bacteria play distinct roles in shaping the immune microenvironment. Specifically, intracellular bacteria turn on IL-17B to introduce neutrophil suppressive state. And finally, the therapeutic application should consider bacterial state and antibiotics properties. Last but not least, I really want to thank my supervisor, Dr. Shang Cai's mentorship during my PhD journey, and I want to thank all the lab members and the collaborators, and I want to thank Westlake University Bioinformatics Research Facilities and the lab animal resource and the biorender illustration. And finally, I really want to thank the opportunity to join this meeting and share our recent work to all of you. Thank you for your listening.
Thank you so much for your insightful sharing.
Nice sharing in terms of open us a new insight to intro and extracellular bacteria, and definitely draw a new picture for the cancer initiation progression in breast cancer. So may I welcome all the esteemed speakers to back to the stage and to have a panel discussion and Q&A session to explore the future directions and challenges in this dynamic area.
Thank you so much. Now we have already on stage our moderator, Professor Eugene, and our panelists, including Professor Rob Knight, Professor Herbert Tuke, and also Dr. Yao Bingqing. May I pass the stage to you? Thank you.
Thank you so much. And then I would like to ask any question and then from the audience. Okay, and please, yeah.
Good afternoon, and nice presentation. And I have questions asked Robert Knight. And you are the expert in the bioinformatics, and also you mentioned that the AI in the use in the analyze in the microbiome. So I want to know because you mentioned that, I want to know whether you have some suggestion, excluding the AI in the regression or the classification model, excluding these two directions, whether have the other some treatment or the simulations in the gut microbiota and the DCC, because I am focused on the CRC or the other disease analyze. Thank you.
Great, thank you for your question. So yes, we are indeed using AI to improve on classification and regression over random forests. So there is a recent paper on TRPCA that we just put out, which is transformer-based improvement on the RPCA method for analyzing compositional microbiome data. In addition to that, we are using other attention models where we can build a foundation model of how collections of ribosomal RNA are structured in different microbial communities. And we think the advantage of the foundation models, both at the 16S level and at the whole genome level, which we are working on now, will allow us to not only improve classification and regression, but also to do some of those generative AI tasks that I mentioned. I think so. In particular, being able to do things like arithmetic in the embedding space. So in the same way that you can do semantic arithmetic on words and concepts in an embedding space, we think you will be able to do that kind of thing with microbiomes. So, for example, to project what would your current microbiome look like if you had fatty liver disease or IBD, or could you change your microbiome with diet in a particular way? And as a separate step, could you use AI to build the model of what that diet should look like? So we think there are many different applications.
Okay, thank you.
So thank you. So one question for Dr. Yao. So from your data, I mean, it seems to me naively that clinical trials should be very readily designable for that, right? You just have two groups of cancer patients match somehow, and then one group has some long-term antibiotic, and then you see the prognosis, basically. Is that sort of work being done?
Yeah, thank you for your questions. And I think, yeah, it's very essential to, like, in the clinical trial to test the antibiotics to deplete intracellular bacteria or extracellular bacterial function and see the outcome, the treatment outcomes. And we're trying to do that, but it's very hard to get enough human cancer patient recorded. And we hope that in the near future that we can figure out this. Thank you.
Thank you. I have a question to Herbert. Okay, I think it's interesting to identify two phenotypes of MASH. Do you think the gut microbiome metabolites may contribute to phenotype of MASH?
Well, I'm convinced it contributes, but of course the challenge is we have interaction with dietary components, and are dietary components the major drivers, or is it microbe-based or metabolites released by microbes? And both different worlds might, for example, activate the same mechanisms in innate immunity, let's say targeting NLRP3 or certain cytokines. So it's challenging and to find out, because it's so highly interacting, dietary with microbes, microbes with diet. So I think that's one of the major challenges we're facing now in understanding the disease.
Yeah. Okay, please. Yeah.
Good afternoon, and thank you to all the professors for a very insightful presentation. My question is for Professor Herbert. So in your talk, you mentioned that the liver inflammation and also muscle is also associated with the gut microbiome. So I just wonder, there are a few probiotic cocktails that are under clinical trials right now. So may I ask, what's your perspective in gut modulation? Like, if we modulate the gut microbiome, maybe it's a good strategy for maybe in personalized medicine as well, because the gut microbiome also have varies between populations, and I wonder what's your opinion on that?
Thank you very much for this very important question. I have to say, preclinically, we have so many wonderful data when we use probiotic 1 to X and Z, and it works preclinically. But in a clinical setting, it's much more challenging. First of all, we need studies at least over 1 year. Second, we need sponsors. So industry so far had not been motivated to finance this type of trial. And third, my personal belief is that maybe we should better understand what is going on and then probably target metabolites, because maybe targeting or using 1 or 2 bacteria might not be sufficient. I would rather go for metabolites. And there is a nice example recently demonstrated. There is a metabolite with the name imidazole propionate. It's histidine-derived, and it's generated by certain bacteria. But imidazole propionate is very pro-inflammatory. There was a nice Nature paper now showing that it plays a major role in atherosclerosis, and I told you atherosclerosis is the #1 cause of death in muscle patients. So this could be, for example, a very attractive target. And I think we should go for such targets. And in muscle, I have to say there is still a lot to do, because we have not yet identified many relevant metabolites derived from the microbes. Thank you.
Thank you.
Okay, and please, next one. Oh, so many. Okay, and one by one, please. Yeah. Okay, yes.
I also have a quick question for Professor Knight. So first, thank you for a very comprehensive talk. So my question is that you have mentioned a very interesting slide about that the lean and obese patients are more determined by the microbial genes than the human genes. So as we know, the tumor always occur with numerous genetic mutations and also the microbial dysbiosis. So I want to ask, in your opinion, which one played the dominant role in the tumor development, the genetic mutation or the microbial dysbiosis? Thank you.
Yeah, great question. So for the lean versus obese question, it is not just us. Many other people, including Iran Segal's group, have done direct comparison of the human versus microbial contribution to that phenotype. And in obesity, it is very clear the classifier accuracy is much better, and you need far fewer people to see it if you are looking at the microbial genes than the human ones. For cancer, I don't think we really have the data yet to do the same kind of contribution about microbial versus human genetic causes. And additionally, there is the issue about whether you're looking primarily at the gut microbiome and metabolites and immune cells that are produced or trained by the gut microbiome that then circulate through the rest of the body, or whether you are looking at microbes that literally translocate inside tumors, as you heard in the last talk. So I think it is a very interesting question, but not one where we have the data to decide yet, although many people are working on it, and if you're looking for projects, it would be a fascinating one to tackle.
Okay, thank you. Next one. Okay. The boy first, and then the girl in the front.
Thank you. My question is for Professor Rob Knight. So your talk is very interesting, and I was very interested about the slide, the microbial changes from the same person who undergo different healthy stages. So my question is that which bacteria are responsible for that change, and whether these key bacteria are the cause for the change, for the transition of the microbial, the healthy state, and or are they the result of this healthy status?
Yeah, great question. So I would have to go back and look at the data to tell you the individual names of bacteria that were strongly associated with those different states. I don't remember off the top of my head. But what you are seeing during the changes at different times from that one person are almost complete turnover of the microbial community. So there is essentially nothing the same, especially in his post-surgery setup. His post-surgery state is almost completely non-overlapping from his pre-surgery state. And the other thing to note is that we don't know causality in that time series. So typically, what we know at the moment is we know what bacteria are correlated with the state changes, but we don't know which of those are driving the physiological changes. And I'm not sure whether we are going to be able to get that out of one person's data. We're collaborating with George Sugihara at the Scripps Institution of Oceanography, who has done a lot of exciting work on inferring things like ecosystem collapse parameters from time series data. And the reason why we can apply that now, which we could not do in the past, is that we are now using reference standards for the DNA. So we get absolute quantification in terms of copies per gram of the different kinds of bacteria instead of the relative abundance data that are common in the microbiome field. So we are starting to do that, but we don't have results yet. The other possibility is using things like Granger causality over the whole time series. And even with hundreds of time points, we do not have quite enough data to do those kinds of causal inferences robustly. Typically, those have been more successful in data sets with thousands to tens of thousands of time points. So we have some fundamental limitations. What we really need is more people to be willing to collect their microbiome samples every single week, like Larry has been doing, or ideally every single day. And a lot of what we are trying to do at the moment is to make that cheap and feasible enough that you could actually do it. So for example, for my own time series that's been running for 15 years now, we recently switched to these pre-barcoded tubes. So this one has not been used yet, but essentially what you can do, they have a little barcode on the bottom, so you can scan racks of 96 of them at a time, and the whole DNA extraction process and process of getting them from this format into 96 well and then 384 well plates is automated. So that kind of thing dramatically reduces the cost of the rest of the project. Like I showed you, the cost of sequencing has already been dramatically reduced. And so we are trying to figure out how we can make it feasible to do this sort of thing at scale in a way that individuals could reasonably do it without a lot of difficulty and infrastructure. Now, it is pretty difficult to get people to collect their stool even once in a clinical setting, as you heard in the other talks, and getting them to do it every day is even more challenging. Getting a blood drawer every day, I think there would also be a lot of difficulty getting people to do that. And so trying to find what biospecimens you can collect and analyze in a reasonable way for these kinds of studies is also an ongoing topic of interest in our lab and in my center.
Thank you so much, Rob. And due to the time limitation, we have to close this Q&A session. May I invite all the speakers to still stay in the stage and have a group photo and with Professor Denslow, the chairman of Future Science Prize Week. We have a group photo.
Thank you so much for the sharing. So may I invite all the guests on the stage to step forward for a group photo. Thank you. Please be seated. So it is the finale of this section. Just a reminder, for those who have registered for the Hong Kong Science Museum guided tour, please gather at reception at 3:45 p.m. So may I invite our guests on stage to please be seated. And for those who will be joining the welcome dinner, we have arranged 2 shuttle buses to the venue. The first one will depart at 5:30 p.m. and the other at 5:45 p.m. So please remember to gather in front of the entrance. Next, we are going to have the mathematics section, Perspectives on Geometry. Next, we are very happy to introduce with you Professor Mok Ngai Ming as this section's convener. He is Chair Edmund and Peggy Dare Professor in Mathematics, Chair of Department of Mathematics, and Director of the Institute of Mathematical Research of the University of Hong Kong, member of Chinese Academy of Sciences, member of Hong Kong Academy of Sciences, 2022 Future Science Prize Mathematics and Computer Science Prize Laureate, and member of Program Committee of the Future Science Prize Week 2025. So please join me in welcoming Professor Mok.
So I'll wait just a short moment while some people are leaving. Okay. So good afternoon, everyone. It is my great honor to serve as the convener of this afternoon's mathematics session, titled Perspectives on Geometry. I'm Ngai Ming Mok, and I warmly welcome you all to this to what promises to be a deeply insightful series of talks. Geometry has always been a cornerstone of mathematics, connecting intuition with rigor and inspiring breakthroughs across disciplines. Today, we are privileged to hear from three geometers who will share their latest insights and discoveries. Exceptionally, we also have a speaker in applied mathematics and statistics who will be sharing with us the applications to medical science. And this will also prepare us for a panel discussion in which the pure and applied mathematicians can have a dialogue with each other. Each speaker will present for approximately 25 minutes. Following the presentations, we will invite all speakers back for a panel discussion and Q&A session. Okay, so now let me introduce Professor Xu Chengyang, Professor of Mathematics at Princeton University, Fellow of the American Mathematical Society, and Laureate of the 2017 Future Science Prize in Mathematics and Computer Science. He will speak on a story of two geometries. Let's give him applause of hand.
Okay, thank you very much. Thank you very much, Professor Mark. I mean, it's my great pleasure to speak here. And I want to tell you a story of two geometries. So basically, the two geometries are algebraic geometry and the complex geometry. So in the first part of my talk, I want to talk about the history of some interactions between these two geometries. And in the second part, I want to talk about the very recent interaction between these two fields. So basically, if you look at the history of complex geometry and algebraic geometry, they actually have the same root. So the root was in 19th century when Appel, Jacobi, Riemann, Weierstrass, and many others, they look at the theory of Riemann surfaces or the theory of complex one variables. So basically, that was counted as the birth of algebraic geometry and the complex analysis. So the root can be considered to study the equation of this simple equation, this 1 squared plus x cubed plus ax plus b. So if you change the x cubed to x squared, then that kind of equation also have been studied a lot, but that's considered to be very classical. So but somehow if you increase the degree from 2 to 3, then the story gets much more interesting. And there are very different views to look at this. So for instance, if you want to draw a solution of this, so if you consider this equation, then if you look, I write down two examples, like on the right up corner, which is, the first one is y squared is equal to x cubed minus x, and the second is y squared is equal to x cubed minus x plus 1. They look very differently. I mean, you know, there's two, for instance, they have the first one have a two component, and the second one only has one part. However, if I change the solution from the real values to complex values, so now I still consider the solution of this same equation, but now I just consider x, y as complex numbers and consider all the possible solutions. The geometry, the solution space, the shape looks much more uniformly than the first one. For instance, if you look at the complex solution, they all looks like this torus, this tile. So that's quite surprising, right? I mean, if you just consider the real solution, then it might look difficult, but if you look at the complex solutions, then they behave more uniformly. And so that tells us that if we want to get a better theory, maybe to look at the complex solution is the first step you should do. And when you want to solve the equation, if the x is square, then you can almost find a way to solve it by some elementary function. But however, people realize that if you just increase the cube to increase the degree from 2 to 3, then there is no elementary solution. So one way to find a solution is to look at this kind of complicated doubly periodic function. This PZ is equal to 1 over z squared plus this. This omega is some complex number. So this one will give you a solution. So if you put this one in the place of x, that gives you a part of the solution. And what is this omega? So this omega is like something complex number. And we regard it as a part of something called a lattice. So the lattice has two parts. One is just given by 1. Originally, you can just consider the lattice given by omega 1 and omega 2. And then you consider all the integral number of omega 1 plus integral number of omega 2. But if I normalize it, I send omega 1 to be 1, then the ratio, I call it omega 2. I call it omega. And so we will say that the different omega might give you different torus. But how to understand the relation is actually a central topic, was a central topic in the study of Riemann surfaces. Okay. So basically, you will say that even this simple object, like the solution space of 1 squared plus x cubed plus x plus b, it looks simple, but actually mathematicians have studied for centuries, and even now we are still studying it. So now let me explain what I mean by two geometries, because as I just described you see that even with this solution space, we have many different viewpoints to look at it. So if we consider algebraic geometry, then we basically study the zeros, the solutions of this polynomial equation. So we regard this equation as a polynomial, and we think about its solutions. And if you increase the degree, increase the number of variables, and then the object you study is called the algebraic variety. And in a more abstract word, there is something called a scheme, or even more abstract one. And in complex geometry, that's the main difference to start with is the functions we consider is not necessarily polynomial function. It's actually complex analytic function. Of course, if I consider polynomials, it's just like a bunch of variables increased up to some degree, and then we take the sum of them. That's an analytic function. But there are more complicated analytic functions, like this y power 2 exponential function, which is a limit of this type. So if I fix n, then this function is still polynomial. But if I take a limit, it's not going to be a polynomial. It's still complex analytic, but it's not in the algebraic. So in some sense, this function doesn't live in the world of algebraic geometry, but it still lives in the world of complex geometry. And if I want to study the object from the complex geometry viewpoint, if we study the space cutting out by complex analytic functions, then we are studying complex manifolds. And if we want to study differential geometry viewpoint, we study something like a Kähler geometry and so on. So, however, if I have a solution of polynomial functions, I can regard them both as algebraic and complex. So in other words, we have the same kind of space, but we might want to study it from different angles using different tools. So in other words, we have this like common goal to understand the geometry of kind of common space. So, I mean, this is a long story. I mean, basically, this interaction between the two subjects is very mainstream in the mathematics, especially in the last, well, especially starting from 20th century. There are many, many major developments. For instance, the Seal theorem and the Sells-Gaga theorem tells us that if I look at some like compact algebra varieties, then if you just regard it as analytical space, essentially the information you get from the analytical side is the same as the algebraic. So a priori, if I start with this complex algebra varieties, if I know itself is algebraic, it might have a space and many like other object which is not algebraic. However, this Chow theorem and Gaga tells you that essentially they're the same. That's quite an important conceptual progress that if we study compact objects, we don't study anything more. It's still everything is algebraic. You can say, basically, put it that way. Also, another very deep subject is called the Hodge theory. So basically, we study algebra variety, but we consider its underlying, so we regard it as a complex space. And being a complex space, it has some topology. And we study the topology. This topology has a very interesting special structure called the Hodge structure. And we study the Hodge theory on that. And then one can even try to recover the Hodge theory purely through an algebraic viewpoint. And that's also a very, influential subject. Started from Hodge's work in 1950, even now, people are still making huge progress. And again, there is a classification theory. We want to classify all the algebraic varieties. We can classify them as algebraic varieties, and also we can classify them as complex objects. And these two viewpoints also interplay a lot. So again, we come back to the key message that the analytic and the algebraic methods basically describe the same geometrical world. So we look at the same thing, but we use different tools, and we got very different way to think about it. But at the end of the day, they will interplay. So now I want to tell you some very recent, exciting interplay between these two objects, between algebraic and complex geometry. So one major theme in complex geometry is to find canonical metric. I think you will probably hear this more in Professor Sang-Sun's talk. So for the Riemann surface, that's basically the complex dimension 1 case. There is one big theorem which essentially tells us all. That's a so-called Poincare uniformization. That says that when complex dimension is equal to 1, any Riemann surface admits a metric with either curvature positive, curvature negative, curvature 0, or curvature negative. So here, curvature is some mathematical notion which people use to capture how things are curved. I mean, if you look at the picture in the left-hand side, somehow you say that from some direction it curve in like this way, and some curve from different way. Somehow this, this kind of complicated geometric vision can be captured by some notion called curvature. And to give you example of curvature positive, the standard example is a sphere. So we all know that a sphere, the curvature is equal to, positive. So in other words, if you, for instance, if you draw a triangle on the sphere. And then if you take the sum of the degree, it's always larger than 180. And a flat one, a priori, you might just think about something like a flat paper. But actually, the torus one, you can also say it has flat metric. Because if I have a paper, I can just glue the two sides to make it looks like a column, and then I just glue them again to get a torus. So the torus one, essentially, it has curvature 0. And the curvature negative one, that's more complicated. I mean, I draw a picture. I don't know how helpful it is. That's basically the Poincare model of the geometry with curvature negative one. So here, if you look at some buildings, we say that I think this is IFC in Hong Kong. The curvature is positive because you say that it somehow go out a little bit. And I think this is the Hopewell Center. And even, it's curved, but it only curves along one direction. Another direction, it's flat. So as I tell you that the torus has curvature 0. This building also has curvature 0. I mean, I couldn't find a building in Hong Kong with negative curvature. I think anyone might be able to help me. But I find the one, this is the Canton Tower in Guangzhou. So that's, so it's not very far away from here. And if you look at the curvature there, that's negative because on one direction it curves like this, but on one direction it curves like this. So you can imagine that the curvature is negative. So this is a one-dimensional picture. So now, how about a higher dimension or in general? So I think my slides the shape was changed a little bit, so some of the symbol, we couldn't say it. But let me try to just give you by words that in general, we consider Kähler metric. And again, remember, in computer geometry, the question is we want to find the canonical metric. And here, the canonical metric means that we want to find a metric satisfy the Einstein equation. I think Professor Sangsen, in his talk, he will explain to you more about why people regard Einstein equation as the equation give you the canonical metric. But you can imagine that after Einstein's work, people always want to find a geometric object which is satisfy Einstein equation. And here the symbol was messed up. I mean, it was there in my original slides. I don't know what happened. But let me just say that we know when lambda is negative, that's a negatively curved case, or lambda is equal to 0, that's a flat case, there is always a solution. So you can always find the Kähler-Einstein metric. I mean, there's a big theorems, but we know it. But the more delicate case is that when lambda positive, that's the IFC center case, that it's know that there is not always a Kähler-Einstein metric. But when does it have? I mean, people spend a few decades to understand it. And I think now we have a pretty satisfying answer that the answer to it depends on algebraic properties of X. So somehow, if you just look at the question itself, it's a question about whether it has a canonical metric. So that lives in the complex side, but the answer we use to characterize this complex question is actually given by the algebraic side. So somehow there is a deep relation between two sides. So here I draw a picture. So if one want to guess whether this one is what the curvature is, I mean the answer is it's not easy to guess, but the answer is this one belongs to the world of flat object. So this one, the lambda is equal to 0. I mean, it doesn't look like very flat, but that's a case that this one, it has a solution that the lambda is equal to 0. I mean, it's called Calabi-Yau. So on the other hand, in algebraic geometry, we have a completely different question that algebraic geometers are very interested, that classifying varieties. So we want to look at all the different solutions of algebraic equations, and I want to classify them. Sorry, again, I think this was a little bit, I mean, my equation and my words are somehow a little bit misplaced in this slide. That in this one, if you look at this equation, you realize that there are two coefficients here, A and B. So we can vary A and B continuously. So if you just look at the shape essentially is the same. You know, if I have a torus, I can contract a little bit. I mean, the topology looks like the same, but actually they give you different elliptic curve. The solution space of this is called an elliptic curve. And you might ask, how do I know they are different? Or how do I tell two of them are different from each other? The naive guess is that if A and B are different, then they are different. That's not true. Actually, it's not parameterized by A and B, but by some more complicated function called J function, that if you have this number, if you have two of them which are different, then you got two different elliptic curves. This is a deep theory. I mean, well, by now it's well understood, but it's a very nice theory. I think go back to Albert Jacobi's time. And another very deep question is understand what happens when the denominator approximates 0. So here, when I write down this J function, of course, the denominator, a priori, if you choose A and B are general, it's not 0. But then you can just approximate to some solution of this denominator being 0, and then what happened there? That's also very interesting and deep question. So basically, to understanding the space parameterizing this is called moduli space theory. So this is a central theory in algebraic geometry. And in the case lambda is negative, people studied a lot. So one very nice answer, which we know in 1960, around 1960, that one can basically construct a moduli space as an algebraic object parameterizing all Riemann surface of genus at least 2. So genus is some algebraic notion. Basically, only when genus at least 2, the Riemann surface can have a curvature of negative ones. And in that case, we can parameterize them using moduli space. So this is the answer to the lambda negative case in dimension 1. And we can do the same thing, answer the same question, even in general dimension, as long as lambda is negative. So we can always parameterize negatively curved moduli, objects using moduli space. So here, I write down this called like Gauss-Bonnet equation that connects genus and the curvature. So you say that if I have a curvature negative, then that means, so in my Riemann surface, there is no boundary. Now if I take the integral over this negative curvature, that gives me the Euler number. So if the curvature is negative, then the Euler number is negative, but Euler number is 2 minus 2g. So that exactly when G is larger than 2, the Euler number is negative. That's, again, the curvature negative case. So then, how about the positive curvature case? So this question has been mysterious for many, many decades in two hydrogeometers. I mean, people even didn't believe there was a nice solution until very recently. And because if you look at the existing examples, all this like a positively curved objects, if you consider all of them, they behave very wildly. So there is no one good modular theory one can use to parameterize all of them. However, until very last decade, we start to realize that there was one point missing in this story. And the missing point was exactly the point at which I mentioned a few minutes ago, is that instead of looking at all space with lambda positive, we only look at those with Einstein equation solution, or in other words, which is algebraically stable. So modular space only parameterizes stable objects. And here, the stability, I mean, even the notion was defined algebraically. The root was a solution of Einstein equation. I think that was attribute of this story. And in general, that to think about the solution of Einstein equation has some algebraic stability. This was a huge subject in the modern geometry. By modern geometry, I mean modern geometry in the last 40 years or half century. So it manifests in a number of major fields of geometry. And here we look at one piece of that is we study varieties. And in that case, the lambda positive corresponding to some notion called K-stability. So in a hybrid view, this can be regarded as the solution of Einstein equation corresponding to some kind of algebraic stability. And this algebraic stability here, the notion is called K-stability. So then K-stability enables us to classify varieties with lambda, when lambda is positive. So here, lambda should be positive. So here I wrote a book on this subject, and it was published in May. So if you're interested, I suggest you to read it. So let me summarize what I have talked about in the last 20 minutes. So basically, there is algebraic geometry and complex geometry. These are two mathematical subjects which interact with each other for many, many years, or even centuries. I think going back to 19th century, they even have the same root. However, in the most recent story, there was one thing behind them and inspired both of them. That's physics, because we are looking at the solution of Einstein equation. And somehow this idea flows from all three different directions and have a very big influence on both algebraic geometry and the complex geometry. Okay, I think my time is over. Thank you very much.
Thank you, Professor Xu. So now I would like to invite Professor Mo to introduce our next speaker.
So thank you, Professor Xu. And thank you for the elegant exposition on the interplay between different geometric theories. And your exposition offers us a profound understanding of how diverse mathematical fields can converse and enrich each other. Our second speaker is Professor Lawrence Ein, distinguished liberal arts professor at the liberal arts and sciences professor at the University of Illinois at Chicago, a fellow of American Mathematical Society, He will speak on a brief introduction to algebraic geometry. Professor Im, please.
Thank you very much for the invitation. It's an honor to speak in this symposium. So I just want to give a very simple talk by introducing two classical algebraic geometry theorems, the Boussu theorem and the 27 lines on the cubic surface. So my own personal experience is that when I travel on a plane, and I often would do some mathematical calculations, and my neighbor will look at my diagrams and symbols, and they find it fascinating, and they often ask, what is my profession? And I would tell them I'm a mathematician, and I work on algebraic geometry. Now, then I say the algebraic geometry study geometric objects defined by algebraic equations. And I often wonder that what happened instead of 20 seconds to answer the question, if I have 20 minutes, how would I do it? And anyway, this talk is just my modest attempt to do this in the 20 minutes. For this talk, the algebraic equation just simply means polynomials. Well, let's start with a very simple example, like a polynomial of degree 2, x squared minus 1 equal to 0. And you find two solutions, plus 1 and minus 1. They define 2 points on the real line or define 2 points over the complex numbers. Now, the next equation is x squared plus 1 equal to 0. Well, you don't find any real solution anymore. But you still find two complex solutions, namely I and minus I. And in general, you have a degree n polynomial. You write down an x to the n plus an minus 1 x to the n minus 1, etc., up to a0. The ai are complex number, let's say. And the classical theorem of fundamental theorem of algebra tell you that such a polynomial always has a complex root. And now, if you have such a root, then you can factor out by the root the x minus r, and then you can decrease the polynomial by 1 degree, and then by induction, you can always factor a polynomial into n linear factors, so x minus r1, x minus r2, etc., up to x minus rn. Now, you can combine the like term together, and then you have, let's say, r1 to rs are all the distinct roots, and then you can group them together and count them, how many times R1 repeated and how many times R2 repeated, etc. And mi are called the multiplicity of the roots. And when you count them properly like that, then you see a polynomial degree n has exactly n solutions. But if you count them with multiplicity, so if they got repeated 2 times, then you count with multiplicity 2, etc. Right? And now one can ask what happened in higher dimensions. So you have a polynomial of 2 variables, let's say. Yeah? And for instance, in this example, you have 2 equations. Both are degree 1 equations. Geometrically, they would define 2 lines. And you find that there's only 1 solution. And now, you look at the next example. You have 2 degree 2 equations. One is x squared plus y squared equal to 1. Next one is x squared plus y squared equal to 0. Well, since 1 not equal to 0, so obviously there would be no solution over the complex plane. So there are no complex solutions. But if you take 2 general ones, then this is the picture, yeah? And that you would expect 4 solutions. So somehow there's some missing solution. Yeah, the picture is missing some of the points. And so one way to fix it is to introduce so-called projective space. And this is to look at a complex projective space, that's C to the n plus 1. This is n plus 1 dimensional complex projective space. And take away the origin and quotient out by the non-zero complex number. Well, what that just simply means is that the 2 points on the n plus 1 space, and they will be equivalent if they're different by a multiple of a non-zero scalar. Now look at this quotient, and then what you have is just simply all the lines through the origin. And this is an n-dimensional object. Yeah? And so to try to understand the space, for instance, you look at the open set where the last coordinate is not equal to 0. Now, since I can scale it, I may well assume the last coordinate is 1. And you just see that the point x0 to xn is equivalent to x0 over xn, comma, x2 over xn, etc., and to xn minus 1 over xn, comma 1. And what you need to add is simply the places where xn equal to 0, and that is a complex projective n minus 1 space, and these are the points we add to it to the usual complex n space. Yeah? The open part is just simply a copy of Cn. And so often this point is called the point at infinity, and these are the new points that we add to the space. Now, to define algebraic equation on the complex projective space, you just look at, instead of regular polynomial, you look at so-called homogeneous polynomial. The homogeneous polynomial are just simply the combination of monomials. All of them have the same degree d. And so we have the following simple property that if you scale it by a non-zero number, lambda, then the value of the polynomial will be scaled by lambda to the d. And this thing would define, this kind of equation would define an object up in Cn plus 1 that's invariant under the non-zero scalar action. So the descent to a geometric object in the projective n space. And the projective n space is an n-dimensional object. And this equation would define one condition on the relation among the points, and this would define a n minus 1 dimensional geometric object in the complex projective space. Now, let's look at the example we had before, the x squared plus y squared equal to 1 and x squared plus y squared equal to 0 equation. And in the funny coordinate we introduced, you can write that equation as x0 over x2 squared plus x1 plus x0 squared equal to 1, and x0 over x2 squared plus x1 over x0 squared equal to 0. And you multiply it by x2 squared, and you get these two equations. And you look at the difference of these two equations, you just get x2 squared equal to 0. And basically, you can think of, you replace one of the equations, for instance, the second equation by the equation x2 squared equal to 0. So that tells you all the solution is on the line at infinity, defined by x2 equal to 0. And it's easy enough to check that basically there will be two solutions at infinity, 1 comma I comma 0, and 1 comma minus I comma 0. And since the line x2 squared is counted with multiplicity 2, altogether, you will find 4 solutions again if you count it with multiplicity. So each of these solutions have to be counted twice. So this is the classical pursuit there. So if you have f and g, a homogeneous polynomial of degree m and n, and let's say of the positive degree, and suppose that they have no common factor, the f and g, and then if you count it with multiplicity, they are exactly m times n that many zeros. So just like in the case of polynomial of one variable. So this is exactly the same picture. Now, so this is a talk about geometry. So really, to understand this better, it's really better to look at the corresponding geometric objects. And you look at the solution given by the equation f equal to 0. And I look at this CF. So this is a complex one-dimensional object in the projective 2 space. Yeah, and it's given by the solution to this equation f of x0, x1, x2 equal to 0. And similarly, you can define COG. That's another algebraic curve. There's a complex algebraic curve. There's a complex dimension 1. And now the solution is just simply the intersection of these two curves, complex curve. So the assertion is basically counted with multiplicity. The number of points in the common intersection is exactly m times n, and that is Boussou theorem. Now the Boussou theorem is going back to 17th century, and I mean, maybe Newton may be the first one who asserted, and Boussou claimed it, write it down more explicitly in sort of late 17th century. But the rigorous proof came much later. Okay, let's try to understand the picture a little bit in this very simple picture. So we have already seen in the plane the equation x squared plus y squared equal to 1 and x squared plus y squared equal to 0 actually have no common solution at all, even though they're both of degree 2 when you say that there are 4 solutions. Yeah? And so maybe first thing to see is there are always solutions in the complex projective space. That would be the first thing we want to check. And so look at the picture back in C3 and look at the equation defined by f of x0, x1, x2 equal to 0 in C3. Yeah? This is a one equation in 3 space, so we would define a 2-dimensional object in the 3 space, so that is an algebraic surface. So you have CF hat and CG hat, they both are surfaces. And the intersection could be empty, but if it's not empty, then it's at least a curve, because the intersection of 2 surfaces inside a 3 space. Now, but the fortunate thing is these are homogeneous equations. There's one simple solution always exists, namely the origin, like 0, 0, 0 is always a solution. So you know that the solution space or the intersection is always not empty, so therefore it's at least a curve. But since the curve has infinite many points, so there will be a solution outside of the origin. And this corresponding to the fact that down in the projective space, the CF and CG will have always solution in the plane, in the complex projective plane. And then Boussou theorem is to simply say that if you count it with multiplicity correctly, then number solution is exactly m times n. So in the following, I would like to sketch a heuristic proof. This is not a rigorous proof. I mean, it could be made rigorous, but you need to develop quite a bit of theory to make this a rigorous proof. So basically, you just look for places where the Boussou theorem is true. And it's true if one of the equations is a linear equation, then the thing is defined a line, then basically you just reduce it by restricting the first equation to this line, then you reduce back to an equation of one variable, and that's fundamental theorem of algebra will tell you that there are exactly m solutions. Yeah? And now, but because it's true for one line, it's also true for union of lines, if you count it with multiplicity. And so therefore, the second equation is also true for union of n lines, L1 times L2, where they're defined by product of n linear equations. But now, you can link the original solution to the given one, to this given special one that's given by union of line, just by this family, 1 minus t times L1, L2 up to Ln, plus t times g. And at t equal to 0, you get just the union of line. At t equal to 1, you get back the curve CG. Now, the intersection number is a discrete invariant. So it should be invariant under deformation. When you perturb the picture, if number will not change, this number will stay constant. And so since it's true for union of line, therefore it's also true for t equal to 1 at g equal to 0. And this gives roughly the heuristic reason why the Boussou theorem should be true. Okay. You can find a fairly elementary rigorous proof in Fulton's book on algebraic curve. And you can, for intersection theory, is a more sophisticated subject. And for instance, you can find a very thorough treatment in also a book by William Fulton on intersection theory. Right. The second theorem I want to talk about is 27 line on a cubic surface. So the statement is the following. If you have a degree 3 homogeneous polynomial in 4 variables, that's called the F, and then XF is the solution to this equation. Again, this would define an algebraic object, a geometric object in the projective free space, and this time would be a 2-dimensional geometric object, so this is the algebraic surface. Okay. And we want to look at the so-called smooth surface. So basically, it looks like I think that without corners, a smooth object, and more precisely, would be defined by the non-vanishing. I mean, if you look at all the vanishing or the partial derivative, and they should have no common solution at all in the projective free space. And so, a classical theorem first asserted by Cayley, Arthur Cayley, in the middle of the 19th century. And basically, the theorem is that at least for general cubic surface, there are exactly 27 lines. And basically, now we know that really what is true is every smooth projective surface has exactly 27 lines, no more and no less. And even more true, conversely, if you have a surface that has exactly 27 lines, then it is a smooth cubic surface. Oh, sorry, I didn't go wrong. Get the wrong direction. Okay, all right. So again, just like the last example, I first look for places that really I can check there are exactly 27 lines. Yeah? Just like the case that with the Boussou theorem, I look for the case that is union of n lines. So again, I look for some special cubic surface that is smooth and has exactly 27 lines. And the example I choose is the so-called Fermat cubics. That this is just simply x cubed plus y cubed plus c cubed plus w cubed. Okay? So I want to let you see that really there are 27 lines on this surface. So what is a line first? A line is something defined by two linear equations, two linear independent algebraic equations. Yeah? That's like x plus y equal to 0, c plus w equal to 0. Yeah? That would define a line inside the free space. You need two linear independent equations of degree 1. But here you can see some of this equation. Namely, you look at x cubed plus y cubed. Over the complex number, you factor into a factor of 3 linear forms. And similarly, y cubed plus w cubed factor into x plus w, or c plus c omega w, and c plus omega squared w, where omega is just simply the e to the 2 pi I over 3, and it has the property that omega q is equal to 1. And now you look at two of these linear equations, x person, take any s and t from the set 0, 1, 2, and look at x plus omega s y plus c plus omega t w. And there are two linear independent linear equations that define a line. In this fashion, what I did just fine for you is 9 different lines. I get by the different choices of s and t. Okay? But really, I can do this more generally as long as I choose this, breaking the set, the XYCW into two disjoint pairs. I can play the same trick. And so in this way, you can, there are three different ways to separate this into three disjoint pairs. So therefore, altogether, you have 3 times 9. There are 27 lines altogether. Now, with a little bit more work, elementary work, nothing, just more than high school algebra, and you can check that really there are no other line other than this 27 lines. So what you will find is a single example of a cubic surface with exactly 27 lines. That's what we just did. Now, a very pleasant geometric argument using the fact that there is existence of a single algebraic cubic surface has finite number of lines. Then looking at the family of cubic surface, the number of monomial, degree 3 monomial, there are 20 of those guys. So this gives you a 19-dimensional projective space of all the cubic surface. And you can also count all the pair of S comma L, where S is a cubic surface, L is a line. And you can count that there's also 19 dimensions. And the fact that there's some surface that's only finite linear line, and then by dimension theory, you can argue that in fact, every cubic surface has a line. So now I don't know there are 27 lines, but I know every single one of them has a line. Right. Now, so what I need to do for you is for a smooth cubic surface, starting from this line, I need to find you 26 other ones. Yeah? And this can be done in the following fashion. So you look at the projection map, let's say the equation defined by, I don't know, after change the coordinate, it could be x, y equal to 0. Then the x and y will define a map from the free space, from the surface x to the projective line, P1. And geometrically, what this projection map does is just simply look at all the plane section of the cubic surface containing this line. So when you cut the cubic surface by plane, you get a cubic curve. You get a degree 3 curve on the plane, but one of the lines is always fixed. What is remaining would be a degree 2 polynomial. And there are two cases. Either it is a smooth degree 2 polynomial, or it may be singular. In the case it's singular, then the thing is a union of two lines. The two lines could become together, but in a smooth surface, they don't come together. They always remain two distinct lines. Yeah? And with a little bit of work, since we understand degree 2 polynomial very well, and so given the cubic polynomial, you can write this thing as all the plane section down very easily. And you can look at all the singular fibers of this mapping. And there are exactly 5 singular fibers. And so what you do, so each time it's a singular fiber, it is union of 2 lines. So what you did is finding 10 other lines in this fashion. So altogether, I find you 11 lines. But also, I find you that each of those singular fibers corresponding to a plane with a union of 3 lines. And let's say they are L1, L2, and L3. And you can just apply the same construction to each of this line. Yeah? So each time, for each of this line, you get 11 minus 3 new lines. And you can do it in 3 different ways. that is 3 times 11 minus 3. And then you add the original 3 lines, then you get exactly 27. And in this fashion, you find 27 lines. And this is a picture that actually, that always the case that on a smooth cubic surface in P3, you will always find 27 lines. And the picture, then you can ask what happened to smaller degree, for instance, degree 2, then what you can find is that, in fact, there are always infinite many lines. And in the case of degree 4 or higher, then, in fact, the general one will have no lines, but special one like degree 4, you get x4 plus y4 plus c4 plus w4, just using the same argument that we have, you can find some number of lines on them. Yeah. Anyway, this is the picture.
Thank you for the wonderful sharing. Please be seated. So may I invite Professor Mok to introduce our third speaker. Professor Mok, please.
So thank you, Professor Ein. You have masterfully guided us through the foundations and frontiers of algebraic geometry, highlighting its power and elegance. We now welcome Professor Song Sun, professor at the Institute for Advanced Study in Mathematics, Zhejiang University, and recipient of the Oswald Veblen Prize in Geometry. His presentation is titled The Journey Through the Geometry of Einstein Matrix. Thank you.
Thank you very much for the invitation. It is my great honor to speak at this wonderful meeting. So I will explain the geometry of Einstein matrix. So how does this work? Okay. So let's begin the journey by discussing the notion of curvature. So geometry is a branch of mathematics that studies shapes. It originated from our need to measure the Earth in ancient times. The Euclidean geometry we learn in school focuses on regular shapes in our three-dimensional space. For example, we have triangles, circles, cubes, spheres, and so forth. So it was not until the 17th or 18th century that the systematic study of the notion of curvature has begun using calculus. So for a plane curve, for a curve of, for example, a straight line in the plane has zero curvature, no curvature, we all know that. A circle of radius r has curvature, which is constant everywhere, but the value is 1 over its radius. So that when the radius is small, the curvature is big, and when the radius gets bigger, the curvature gets smaller, and it looks more and more flat locally. For a general curve, what we can do is to approximate this curve at each point by a best circle, which is tangent to this curve at the point, and approximate the curve the best. So here at A, this is so-called osculating circle. At this point A, the small one. At this point B, you can find a bigger one. So this curvature at A is bigger than the curvature at B. It's a fun fact that for a reasonably smooth curve in the plane without the self-crossings, then the total curvature is always 2 pi. So if this curvature is distributed equally everywhere, then this is the standard fact that the radius r circle has a perimeter 2 pi r. And on the other hand, if we want the curvature to be concentrated, for example, on a triangle, the curvature is 0 except at the 3 points where the curvature is actually infinity, and the concentration at each vertex is actually the exterior angle at this point. So this is just the fact that the sum of exterior angles of a triangle is 2 pi. It's the same as saying the sum of interior angles is pi. So one thing to notice is that the curvature of a plane curve is extrinsic, not intrinsic. In other words, you have to leave this curve to the plane to see that this is actually curved. If you just leave on the curve itself, you're not going to feel the curvature because you can just simply pull this curve to a straight line and without changing the distance on the curve. Now, if we jump to two-dimensional, consider surfaces. For example, here, this picture is the surface of a round cylinder. And we can consider the notion of curvature by reducing to the case of curves, by taking a so-called normal plane sections. At each point, this red dot, there's a direction which is normal to the surface. And then if we consider a surface, a plane which contains this normal curve, normal direction, then we can cut we can get a section of the surface. For example, if we get a horizontal plane, I will get a circle, round circle. If I tilt it a little bit, we will get a ellipse. And if this plane become vertical, we will get a straight line. And so each time when we have a curve, we can measure the curvature of the curve with a section. So we will get a family of curvature, not just one curvature. So among them, there's a maximum one. Here it's obtained when the plane is horizontal. And the minimum one, when the plane is vertical, which is 0. The horizontal one, we get a circle, which is a non-zero curvature. So these are called principal curvatures. So we get two numbers, and these two numbers, they are also extrinsic. They are not intrinsic. For example, this round cylinder can be obtained by folding the flat plane. Of course, locally, these two surfaces are isometric. The distance are the same. But we can see one is curved, the other is not curved, only in this street space. If we just leave on the round cylinder, we will not feel the curvature. So it's a remarkable theorem of Gauss in the 19th century, 1827, that if we take the product of the two principal curvatures, then it is actually intrinsic. It only depends on the distance measured on the surface itself, and it can be measured intrinsically. And then this leads to one of the three discoveries of non-Euclidean geometry. So we know on the flat plane, we have a zero curvature, that's zero Gaussian curvature. But then we can also have spaces with constant but non-zero curvature. This is also mentioned in Professor Xu's talk. So in the case when the curvature is positive, then there's a spherical space, and when the curvature is negative, the so-called hyperbolic space. And one can tell the curvature is positive or zero or negative just by measuring on the surface itself. We know that on the plane, the sum of interior angles of a triangle is equal to pi. On a general surface, we can still pick 3 points. We can still define what is a triangle, just connecting them by this geodesics, which are distance minimizing curves. And then you see that in this case, when the curvature is positive, this triangle looks fat, and the sum of interior angles is bigger than pi. And on the hyperbolic surface, the triangle looks thin, and the sum of interior angles is smaller than pi. And so we can tell the difference by measuring these angles. So it also, we have this world map. You have many ways of doing projections. So one of the common way of doing this is so-called Mercator projection. It preserves the angles, so it's very important in navigation. But notice that this can never preserve the distance. It does not represent the true distance on the Earth. For example, near the North and the South Pole, it's largely distorted. So in 1854, Riemann, who was a student of Gauss, developed intrinsic geometry further, and extended to higher dimensions. So this is a huge conceptual leap, and it also, from the philosophical point of view, challenged the previous counting viewpoint that the space is a priori determined by intuition. Instead, it only belongs to one of the many possibilities where the actual geometry can only be determined, empirically determined by physical laws. So what it introduced is the important notion of a manifold, so which is a space which locally looks like a flat Euclidean space, but the measurement of length can vary continuously. This measurement of length is, at each point, it is reflected by a positive definite symmetric matrix. So you have a family of matrices. It's called a Riemannian metric, G. So for a Riemannian metric, one can define a so-called a curvature tensor, which measures how far the metric deviates from being flat. So this is completely intrinsic. You don't need an ambient space to work on. But this curvature tensor is normally a very complicated object. And a simpler quantity called the Ricci curvature tensor, which was I think, after the Italian mathematician Ricci Cubastro. So it measures the deviation of the volume density of G from that of a flat space. So it's a slightly weaker notion, but it's much simpler quantity. So when we consider surfaces, then these are just the Gaussian curvature. So for surfaces, we only have one function to measure the curvature. That's the Gaussian curvature. But in higher dimensions, we need this tensor. So Riemann's work laid the mathematical foundation that allowed Einstein to develop his field equations in general relativity. So now let's talk about the Einstein metrics. So these are motivated by Einstein's equation in relativity. So according to relativity, the gravity is described as the Ricci curvature of the space-time. So here the space-time is 4-dimensional, three-dimensional space, one-dimensional time. But now instead of Riemannian metric, you put a so-called Lorentzian metric on it. So the space-time receives 3 positive directions, and the time direction is negative. But in any way, the framework, the mathematical framework that Riemann laid can apply equally to Lorentz metrics. And this equation of Einstein is of this form. That's capital G. That's essentially the Ricci curvature. And then, so and this lambda and the kappa are just constants. So, so on the left-hand side, it's the curvature and the metric tensor is the geometry. And on the right hand, this tensor T, stress energy tensor, is determined by matter. So according to a famous quote of John Wheeler, matter tells space-time how to curve, because this equation says that the curvature of the space-time is constrained by the matter. And on the other hand, space-time tells matter how to move, because the equation of motion is according to the geodesic equation in this space-time. That's geometry. So what we will, in mathematics, in geometry, we will study is called Einstein metrics. So these are Riemannian metrics whose Ricci curvature is proportional to geometry itself. The equation they satisfy is similar to the Einstein equation in relativity, but for Riemannian metrics, and it's essentially the vacuum Einstein. There's no matter here. So it just says the Ricci curvature is proportional to the metric. And this is a partial differential equation, which is a complicated, nonlinear equation. So you can roughly say that these Einstein metrics, they represent optimal shapes in geometry. You can actually write down some action function so that these are stationary points for that action. But this is just saying that the Einstein metrics are analog of the relativity equations. But also, the Einstein metrics themselves also play an important role in high-dimensional gravity in physics. When you deal with high-dimensional gravity, then the space-time direction, the space direction could be higher, and this Einstein metrics naturally lead to solutions. So we introduced the Einstein metrics, and the central questions regarding these metrics twofold. One, we want to this construction. We want to construct solutions to this PDE. It's a very complicated PDE. We want to construct solutions to them, and they have to be complete. They don't have to contain holes. And also, once we have sufficient many examples, we're interested in classification. Can we classify all Einstein metrics? And this requires a deep understanding of geometry of these metrics. So the situation changes in dimension. So in lower dimension, the dimension at the most 3. So Einstein metrics, they are rigid objects. So they actually have a constant curvature. So they are locally given by the 3 models, just like in the surface case, the Euclidean space, the spherical space, or the hyperbolic space. And in dimension higher or equal than 5, so Einstein metrics are too flexible. And the PDE system is very complicated to study in general. So instead, in dimension 4, which is, of course, the dimension that the relativity concerns, but it's also, in terms of geometry, this is a borderline case, and it's also the most intriguing case. And in higher dimensions, in general dimensions, if we do not consider just the general Einstein metrics, if we consider Einstein metrics with structure compatible with special numbers, the complex numbers, the quaternions, or the octonions, then there will be deep interactions and rich theory. So in the rest of this lecture, I will explain some of these directions and results. So let's start with dimension 2. So here, an Einstein metric in dimension 2 is simply a metric with a constant Gaussian curvature. And so this is a 19th century theorem, according to also Professor Xu's talk. So we have a uniformization. So every oriented closed surface admits an Einstein metric. So in the case with positive curvature, that's the round sphere. In the case of zero Ricci curvature, that's a flat torus. So topologically, it is the same as this donut we see in 3 space. But to notice that this donut does not have itself, this shape itself does not have is not flat. So instead, we should abstractly think of this flat torus as obtained from this flat round cylinder by gluing the top and the bottom. So this cannot be seen in 3 space. Instead, if you jump to 4 space, then actually you can see it, the flat torus. And similarly, when you have when your surface have a higher genus, when this surface the inside has some holes, more than 1 hole, then they admit Einstein metric with negative curvature. Again, so this is just a representation of the topology. These surfaces themselves do not have a constant negative curvature. And to see this, you have to jump into higher dimensions. So that's dimension 2. Everything is well known. In dimension 3, as I said, so Einstein metrics are still rigid. But then starting from dimension 3, it's not every closed manifold admits an Einstein metric. So this brings the interaction with topology, like which manifold can admit an Einstein metric. And this has deep connection with other subjects. So this is a famous Poincare conjecture. If we have a closed three-dimensional manifold, which is simply connected, meaning that every closed loop in this manifold can be continuously shrink to a point, then this manifold is homeomorphic to a three-sphere. So notice that this would follow if one can produce an Einstein metric on the manifold, because if we have Einstein metrics, then we know that locally it has to be this rigid models, one of the models, and then using this simply connected assumption, it's easy to conclude that space is three-sphere. And to attack this, so Hamilton in 1982 invented these tools of Ricci flow, which is a nonlinear flow that smooths out the curvature of a space over time. You're starting with any shape, and then you try to make it as close to Einstein as possible by deforming the metric along the direction of Ricci curvature. So it's analog of the linear heat flow that smooths out temperature over time. But because it's very nonlinear, this is a very difficult mathematical problem. The central issue is to deal with singularity formation. So very likely, if you start with a shape, you run this flow, you will get to singularities, and you have to understand this singularity and try to get around them. And then this was finally proved by Perelman using this called Ricci flow with surgery. So when you first have to analyze the singularity in a deep way and try to perform surgery to continue the flow. And then as a consequence, he proved this Poincare conjecture. And moreover, so for three manifolds, there is a geometrization theorem, which says that every closed three manifold can be decomposed into simple building blocks. And then each building block admits one of the 8 standard geometries. So this Einstein geometry is only 3 of them. There are 5 slightly more complicated, but still standard geometries. So this is dimension 3. So in dimension 3, having Einstein metric is good, but to search for them is a deep question. And now let's first jump to general dimensions when we consider Einstein metrics and the complex geometry, which is related to, again, Professor Xu's talk. So here we will consider so-called Kähler metrics. So Kähler metric is a Riemannian metric that is compatible with complex numbers. So we all know that in complex numbers we have this imaginary number I, with I squared equals -1. So for a Riemannian metric to be compatible with complex numbers, we need the notion of I for this metric. And this just means that at the tangent space, you have a way of doing linear transformation, which preserves the metric. And when you do it twice, you get to a negative identity map. So this is, and then you have to do this coherently on the space. So for example, this Earth of the surface of the Earth is a Kähler metric, because when I stand here, I can always, if I give a direction, I can always, for example, turn counterclockwise 90 degrees. And if I turn twice, I will get to negative of the original direction. So that's the simplest example of Kähler metric. So special examples of Kähler metrics include natural metrics on projective algebraic varieties. And for Kähler manifold, there's a notion called the first Chen class, which is after Professor S.S. Chen, and it's often computable. There's some vector, let's say. So the Einstein equation for Kähler matrix then reduced to a PDE. Still complicated, but then it's a PDE for a scalar function, which is considerably simpler than the general Einstein equation. So then there was a conjecture of Calabi, says that it gives which gives a criterion for Kähler manifold to admit a Kähler-Einstein metric, which is a solution to the Einstein equation for Kähler matrix, which is it's the same as saying that the first Chern class has a sign. So okay, so the first Chern class, when there's a number, we can make sense of a sign, but this is not a number. You can still make sense of it. It has a sign. In general, it does not have to have a sign. But in any case, if it has a sign, then it has a potential of admitting a Kähler-Einstein metric. So the case of negative first Chern class and zero first Chern class was known by the work of Oban, Yao, and Yao. In the case when the first Chern class is positive, this is a so-called Fano manifold. It's known that this is not always true, and then there's a conjecture due to Yao, Tian, and Donaldson that a Fano manifold admits a Kähler-Einstein metric if and only if it is K-stable, which is an algebra geometric notion, which again appeared in Professor Xu's talk. So this conjecture bridges differential geometry and algebraic geometry. On the one hand, you want to solve this Einstein equation on this Fano manifold. On the other hand, this K-stability can be tested using algebraic geometry. So this one direction was previously known by many people, Tian, Stoppa, Berman, and then in 2012 this was proved. The other direction was proved. So at that time, this K-stability was a new notion, and not a lot was known. Now, I think we have a much deeper understanding of K-stability of Fano manifolds due to Professor Chen Yang-Xu and his collaborators. So this is just an example that when you study general dimensions, so that if you put the interaction with complex geometry, then things are very interesting. So the proof, there are many proofs of this theorem. The original proof is quite geometric. It's via the so-called inflating the balloon until it is round. So we know that when you have positive Ricci curve, it's hard to find a solution. But if you want to blow into a balloon, you start with a flat thing. So it looks flat, but it is not exactly flat because there's edges where this curvature is infinity. It's just like these triangles. It has points where the curvature is infinity. But nevertheless, it's still flat in most places. You can solve the equation there, and then you try to inflating air into the balloon, make it round, and then the positive curved. And the central issue there still involves understanding singularity formations, but this time in terms of algebraic geometry. So in our case, we study positive curvature. The singularities are reasonably good. They are so-called conical. So in particular, the dimension does not drop. So here is an example of formation of a conical singularity. So this is a sequence of shapes. On the right-hand side, this handle is getting smaller and smaller. In the end, it disappeared. But then after it disappeared, it looks like a cone around there. So there's a conical singularity. And here is an example where the curvature actually goes to infinity. But this is just a very naive example. In general, it could be much more complicated than this. And if we do not consider the positive case, curved case, if we consider the general situation, that's more complicated singularity may arise. For instance, if we just consider flat torus, right, we can have flat torus actually collapse, which lose its dimension in the limit. So this cylinder is getting thinner and thinner in the end. You don't see the direction. You only see a circle. It's a one-dimensional thing. So it is an active topic in geometry to study singularities and especially of their collapsing behavior. So now finally, let me move on to dimension 4. So the geometry in dimension 4 is known to be very rich and mysterious. There are many constructions of Einstein metrics, but there are also many obstructions related to topology, and especially smooth topology, which itself is known to be mysterious. For Einstein metrics in dimension 4, they may also form singularities because they are not rigid. They can form singularities, but then singularities models here are known to be given by so-called gravitational instantons. So these objects were first introduced by Stephen Hawking in 1977 in his search for Euclidean quantum gravity. So they are just a four-dimensional Riemannian matrix which has a vanishing Ricci curvature and is complete, and with reasonable curvature decay at infinity. So these are models of singularity formation, because if you have such an object, I can just shrink down a space and form a singularity. As a mathematical object, it has been extensively studied by mathematicians and physicists for decades. So most known gravitational instances have connections with special numbers, again, with complex numbers or quaternions. They are either scalar or conformally scalar. So it's scalar. It's conformal to a scalar metric. It has the same angle measurement as a scalar metric. These special gravitational instances are essentially classified due to the work of many people in the past decade. Then in particular, one needs to understand. So there are many examples of this gravitational instance constructed and very rich geometry. But then you want to control its structure at infinity and to classify its asymptotic structure. So this was done in my work with Robin Zhang, who is now a faculty at the UC San Diego, and in the conformal scalar case, it was done by my former student Mingyang Li, who is now a postdoc at the Simon Center for Geometry and Physics at Stony Brook. So just to give you a sketch of some examples of gravitational instances, so I cannot draw 4 dimensions. This is actually it's a 2-dimensional object, but it just says that as you move to infinity, the geometry could be complicated. Some direction could expand, some direction could shrink. So it's very rich subject. So beyond this, so Mingyang and I recently produced a new family of examples of gravitational instance. This time without obvious connections to complex geometry. Instead, we draw relations to so-called harmonic maps theory from the surface to a 3-dimensional, to a 2-dimensional hyperbolic space. The construction of this was motivated by the so-called black hole uniqueness questions in general relativity. There, you don't expect such solutions to exist, but in Riemannian signature, this actually exists in abundance. So it is a long-term question to classify gravitational instance, and I believe to understand the gravitational instance just one step, and to understand the Einstein matrix in 4 dimensions is important in our understanding of 4-dimension geometry. Yeah, so thank you. That's it. Oh.
Thank you, Professor Sun. Please be seated. So now I would like to invite Professor Mok to introduce our last speaker for this section. Professor Mok, please.
Thank you, Professor Sun. Your journey through the landscape of Einstein metrics not only deepens our theoretical understanding, but also inspires new questions in geometric analysis. So finally, we come to Professor Arno Frigessi, Professor of Statistics at the University of Oslo, and Director of the Norwegian Center for Trustworthy AI. So he will discuss learning the differential equation of tumor density in a breast cancer patient under treatment.
Thank you very much, Professor Mock, for invitation. It's a great pleasure and honor to speak to you today in the Future Science Prize Symposium 2025. We jump now a bit out from geometry into applied mathematics, if you would like to say so. You will see another piece of mathematics that is hopefully as fascinating as the other three speakers have been so far. I will show you the first digital twin of a breast tumor of one patient under treatment, and I will show you the first ordinary differential equation that has been assigned to a breast tumor under treatment before the person was treated. There are many, many drugs approved in the world to combat breast cancer. Why are there so many drugs? Because breast cancer is not one disease, it is many diseases. They're called subtypes. And it is difficult, very difficult, to assign the right treatment to the patient that comes to the doctors and needs a treatment. It is difficult because, of course, there are many, many options. Combinatorically many, you can combine drugs, you can decide doses, you can decide regimes, and so on. There are no biological biomarkers, so things that you can measure in the blood of the patient or by taking images that clearly tell you what is the drug that will work. And to do randomized clinical trials would be impossible and extremely costly. So what we do instead is very simple. We make a copy of the one patient on a computer. So we produce a digital twin of that patient so that we have very, very many copies of that unique patient and can test on each of these copy in silico treatments. So suddenly we have not one patient that is a mysterious patient to treat, but we have very many that we can test different treatments on. This is the in silico approach to personalized medicine, to personalized treatment, where mathematics plays a fundamental role. The approach that I will tell you about is mechanistic mathematical modeling, which is based on a first-order approximation of the complex interactions between the various components of the biological system of a breast tumor in a patient. This is one tumor, the one of that patient that we need to treat, not the general population of breast cancer patients. It is the one patient. We have heard today after lunch a wonderful lecture by Professor Knight, who was telling us about digital twins in nutrition. And now you will see a digital twin of one tumor. I will start with just one treatment and discuss the question, will it work for the patient? Will I be able to give a recommendation to the oncologist on what treatment to use? Will I be able to say which dose to use on that patient and when to give the drugs? We will also see how we can write a mathematical formula that suddenly is a biomarker of treatment in the sense that it describes carefully if that treatment will work for that patient or not. So here is the situation that we are imagining. The patient arrives at the hospital with a terrible diagnosis of breast cancer. A lot of data are collected about this patient. At baseline, we will measure blood quantities, we will take images, various types of images, measure genomics and genetical features of the patient. That really, before the treatment starts, we will have a picture of how big the tumor is at that point. The treatment starts, and then biopsies maybe are taken after a week, or images are taken. Here you see two trajectories that in time, that's on the x-axis, show how the cancer density, the quantity of cancer cells, the percentage of quanta cells are in the patient after treatment, just 1 week during treatment. And the question is, what will happen in the consequent 12 weeks when the patient will be treated? Now, it's a very serious question because of these 60 drugs that I showed you in the beginning, very often, if one is given to a patient, it will work only with 30–40% of chances. So the risk of having given the wrong treatment to this patient is high. But we would like to really simulate the trajectory of the tumor growth forward in time so that we can predict with uncertainty how the treatment will work. So this is how we will do it. So here is one patient. We will obtain a lot of data from that patient at baseline. We will run all this data through a mathematical mechanistic model of the treatment response, simulate various types of treatments, and make a recommendation to the oncologist on which one are the most successful. So what biology do we measure? And I show you now this to illustrate how mathematics plays a central role in describing a very complicated phenomena of how a cancer in the breast of a patient develops. It's a very, very simple representation of a much more complex reality, but still complex enough that allows us to make a prediction of what will happen with that treatment on that patient in the future. So we start with biopsies. This is extraction of small portions of the tumor and imaging these biopsies through something that is called histopathology. There we see every single cell, every cancer cell, every normal cell. We see blood vessels. And what we do is that we project all these cells on a grid, on a two-dimensional lattice. There are many cells. So you can imagine that these biopsies are very few millimeters long and large, but they contain about 2 million points on the numerical grid. So on each point, there can be a cancer cell, there can be a normal cell, they're called stroma, there can be a vessel that goes through the plane here, and each cell needs to be modeled because the treatment wants to kill every cancer cell. And then you learn that every cell has its own life. It's called a cell cycle. You've learned it when you did biology at school. The cells double in certain frequencies. And this happens because the cell has a certain cell cycle, and at a certain point in the cell cycles, it is mature, and it can produce a daughter cell, and it doubles. So when we give treatment to a patient, then the treatment, the drug, will reach the tumor through blood vessels, through capillary blood vessels. Here they are. So we need to model the blood vessels if we want to understand how it will work. And the blood vessels are leaking. The perfusion, that is what makes us living. The fact that we have a system of blood vessels that are leaking is quite terrible to think, but that's the truth. They're leaking. And they're leaking so that we get oxygen everywhere, other minerals and so on, but also, when needed, we get the drugs to the right places. The perfusion of the blood vessels is very, very important. So when the oxygen or the drugs are perfusing from the blood vessels, they diffuse in the tissue, and they might reach the cancer cells. And if they reach the cancer cells during the right moment of the cell division, then they can kill it. This is a very simple mathematical equation that describes the cell cycle of one cell. It is described by a state vector, a state quantity, phi, that describes the cell state at time t in location x. So we have one such thing for every 2.4 million cells. And it is an equation that simply says that this cell cycle is regulated by the quantity of oxygen, kxt, that is available in the tissue. We need oxygen, otherwise the cell will die. Another very important thing is a parameter, Tmin, which says how fast these cell cycle turns. We have cells that double within hours. We have cells that double within weeks. That number is important. And when this cell state phi reaches 1, then we say that the cell is ready to double. It opens, in some sense, to produce the daughter cell. And when it opens, it is fragile. And that's when standard chemotherapy can kill the cell. Otherwise, it doesn't. So we need the process of producing a daughter cell, which means that the cancer enlarges, to kill it. The drug, the chemotherapy here is called FEC. It's a combination of 3 drugs, F, E, and C. So if the quantity of drug at position X on the grid at time t is big enough, bigger than some threshold, then the cell and the cancer cell is open, is in state 1, then it can be killed. And this is a stochastic event that happens with a certain probability that has been studied before in labs, that depends on a parameter beta, and it simply says that if there is enough concentration of the drug in the right moment, the probability of killing that cell is high. So the blood vessels are not constant. There is a full fantastic process of creating and destroying blood vessels in our body. So imagine that you would like to know if there is a blood vessel in position X at time t. That's the quantity G of xt. So here there is a protein that is called VEGF. It's a protein that also is available in various places of the tissues at a certain time point. And if this protein is large enough, then there is a tendency of new capillaries to be created. You can imagine like this, that if a cell feels that it needs oxygen, also a healthy cell in your body needs oxygen, it will produce this VEGF protein to call for blood vessels to be created in its vicinity so that oxygen can be given to her. But this VEGF is also problematic because if it is too high, then the blood vessels that are present die. And if it is too low, they can't be born. So it's a very, very fragile balance related to the birth and death process of blood vessels. Then I will stop soon to show you an equation, but to give you an idea of how they are. This is how we model the oxygen diffusion. So the oxygen at position X in time t is a solution of this partial differential equation that simply says that it is supplied by vessels, where the vessels are. It is consumed by cells. It's a nutritional aspect of cells. And otherwise, it diffuses in the tissue. And there are parameters here that are important. For example, the parameter that says how fast the diffusion is happening. We have an equation for the chemotherapy that is also supplied by the vessels. It diffuses. I just watch here. So the time is impossible to read, but you know, right? So it's impossible to read the time. So we will find out when I have to finish, right? The chemotherapy diffuses, it's supplied by vessel, and it's taken up by cells also. And I don't show you how this VEGF is produced in the body. And all in all, there are various components of this first-order digital twin of the breast tumor. They're described by ordinary and partial differential equations, by stochastic cellular automaton, and it looks like this. It's many equations, but they're all very, very clear and mechanistically understood. And here there are many parameters, and this is when the patient comes and the data of the patient are used. Now I use exactly the data from the one patient that I have to decide something about. to estimate these parameters. Some of them are known in the sense that they have to do with the pharmacodynamics of the drug, and they have been studied in labs, so some of the parameters, I don't need to estimate them. They're the same for every patient. But others need to be estimated per patient, and we do it by something that is called approximate Bayesian computation that gives us estimates, for example, of that parameter beta that I show you in the birth and death process of the blood vessels, or that time, the cell cycle time. So let me show you an example. So this is a combination therapy of a chemotherapy and a drug. The drug is trying to kill vessels, and the chemotherapy is trying to kill cells. You want to kill vessels because by starving a tumor, you think you can kill it. So this drug is traditionally given every 3 weeks in a certain combination, 4 times, and after 12 weeks, it is stopped, and at that point, the hope is that the tumor has disappeared. So this is a patient that we have analyzed coming from a clinical trial in Norway. This patient had these are 2 biopsies, the blue and the green biopsy. You see where they started. In the x-axis, it's times 0. In the y-axis is the cancer cell density. And you see that after the drug has been given, the tumor collapses right away. But then it comes up again because the drug disappears from the tissue, and cells start, the remaining cells that have not been killed, they start to double again, up again. After 3 weeks, a new drug is given, and the density goes down again. And in this case, the patient was free of cancer after 12 weeks. The drug worked perfectly. Now, the simulation, the thing that you see in the middle is simulated. We have no idea if they are true, but that's how we explain why the drug works. This patient here the drug was not successful. So the patient started with a quite big tumor, and after 12 weeks, the tumor was still there. This is how we explain why this happened. Because simply the drug did not succeed to kill enough cells all the time, and this is because the cycle of the cancer cells of these patients was very slow. There were very few open cancer cells when the drug was given, so only very few are killed. But now, I can now simulate a completely different treatment regime and see how it would work. Instead of giving the drug every 3 weeks, I will now divide the dose in 3 and give it every week and run my simulation on my digital twin. And this is how it would work in that case. The same patient, if she would have been treated with a reduced dose but more frequently, the cancer, in my prediction, would have disappeared. When we show this to the oncologists, they're interested in digital twins. They understand that this is an instrument that they would like to have. The second point of my talk is to investigate how we can describe the digital twin of this tumor in a mathematical way, in a condensed mathematical way, so that I can use this condensed mathematical way to decide if the treatment will work or not. This is to do with producing an ordinary differential equation that describes how the tumor will evolve from the start. So here is where I am. I am at the beginning. The treatment has not been given, or just maybe for a week. And I ask the question before the treatment is given, what will the cell density, the cancer cell density, which ordinary differential equation will the cancer cell density follow in closed form, mathematically written with a notation that we would understand? If I have this estimated ordinary differential equation, then I will call this a mathematical biomarker of the treatment effect. Mathematical biomarker is different from biomarkers that are used today in a clinical setting that have to do with measuring clinical quantities in the body of the patient. This is a mathematical biomarker, but the use will be the same, to decide what to do with the patient. It helps to understand the effect of the biological parameters. For example, this cell cycle length, how it influences the therapy. This is, for one patient, the ordinary differential equation that her tumor growth will follow after therapy has been given. This has not been shown before, and it is a mathematical biomarker of that patient, that tumor, at that time point. So how do we do it? Well, we simply can use our digital twin to simulate the trajectory of the cancer density forward in time. So here you see the drug has been given at time 0, and this is the first week, for example, where we have simulated 336 time points. What I do now is that I use machine learning to estimate in closed mathematical form, the ordinary differential equation from this data. So the question is, given noisy data in time, I measure, I simulate at time t, at density x, can I find the right-hand side of an ordinary differential equation of f of x and t in closed symbolic form? So this is done through something that has been called ODE former, which has been suggested a couple of years ago by some colleagues in Switzerland and Germany. And the first thing I have to tell you to understand what this is that every ordinary differential equation can be written as a tree, as an unary or binary tree. These are trees that have in the nodes the operators, and in the leaves they have either numbers or constants or x. So you see, for example, that equation there can be written in this tree here. So these are trees that have special topological properties, but there is a one-to-one correspondence. So what really the OD former produces is a tree. And to train such an OD former, what has been done is to simply produce random trees, which are random differential equations, solve them, produce data, and use all this enormous quantity, 50 millions of systems of differential equations, to train a transformer machine learning deep neural network that has about 86 million parameters. And it has stochastic elements. Stochastic elements means that if I run the OD former on my data, not just once, but several times, I will get not one ordinary differential equation, but many. So the problem is more complicated, and it connects to uncertainty quantification. Because really, I don't have one equation per patient. I have a sample from a distribution of unary and binary trees, which have the constants or the x's in the leaves. So how do I now summarize, to produce this famous biomarker, which characterizes these patients, how do I summarize this distribution of trees? How do I find the mean? What does it mean, a mean of a family of trees? What does it mean, the quantiles? How do I define a confidence set? And here we are working on Fréchet means that are generalization of centroids to metric spaces in order to give precise definition of these quantities by using different functions, distance functions. Before I finish, I noticed one thing, that is, here you see the red dots is the simulated trajectory of the patient. The blue one is what is expected from the equation that I've shown you before. So that equation fails to really understand that in the beginning, when the drug is given, the cancer density collapses before it takes up again. So in order to improve this, we can go back to the digital twin and not only use the quantity, the simulated density, but also use the simulated concentration of the drug in this biopsy at every time point. So now I have two curves from my digital twin. I can therefore produce a system of ordinary differential equations. So this is the system of two ordinary differential equations in this case, that for this patient would make it work much better. So I think I'll stop here, assuming that it's almost zero there in time. by simply saying that we have produced the first digital twin of a breast cancer under treatment for one patient. It is a combination of mathematics, numerical analysis, stochastic processes, and statistical inference. And we have a way of estimating in closed form the ordinary differential equation that this patient will have, which is a useful biomarker for the patient. Thank you.
Thank you, Professor Frigassi. Please remain on stage. We will have the panel discussion. So the panel will now synthesize our diverse perspectives on geometry, from pure theoretical frameworks to groundbreaking applications in AI and oncology. And our experts will explore how geometric principles provide a unifying language across disciplines, driving innovation in both abstract mathematics and the computational modeling of real-world phenomena like cancer treatment. So now I'd like to introduce our moderator, Professor Mok Ngai Ming, and our panelists, including Professor Lawrence Ai, Professor Arnaldo Frigassi, Professor Sun Song, and Professor Xu Chenyang. So welcome on stage again. I'll pass the time to Professor Mok.
So thank you, Professor Frigassi, for the wonderful lecture. So let's now come to the panel discussion. First question I want to raise is the following. So geometry is a beautiful subject, and we have seen from some of you its many manifestations. So nowadays, the training of basics of Euclidean geometry is minimized in secondary school. Should the teaching of such basic mathematics be revived, or are there better ways to motivate children to learn geometry as early as possible? So anyone is free to answer this question. Maybe speaking from your experience, Professor Frigassi?
Yeah. So the non-geometrist can speak first.
Yeah, you can do that.
So I think that geometry has these fantastic features when you are learning it at school, that because it is for the first time that the pupils see that you can do mathematics not as a simple calculation. You see structures, you start to understand that mathematics is relations. And the other fantastic thing of geometry is that for the first time you understand that things generalize, that properties and theorems are there and can be proved. So I think that this is the first moment where the pupils understand what mathematics fundamentally is. And therefore, I think it is dramatically important to have it quite early.
So how's the situation in Italy?
So I remember when I was a child, we learned Pythagoras when we were 10, 11 years old. That was early, with a puzzle, right? You can prove it with a puzzle. But I also I have to also say to protect a little bit my other disciplines, that if there is too much trigonometry and too complex trigonometry, that's maybe not such a good idea. So I would suggest to think in the development, take geometry early, but maybe think to probability theory and statistics at high school in a stronger way, in some sense.
Yeah. That's, I remember a wonderful way that our school teacher approaches, because we were at a transition from the old system to the new system, right. and then Euclidean geometry was taught within the framework of set theory, and then we also, because of set theory, started with probability theory. So that's one way to do it. So I understand that perhaps in mainland China, this is taught in good schools at least a little earlier. So maybe Professor Sun, can you say something about this?
Yeah, I think, of course, I mean, to motivate children into geometry, I mean, there are many play activities like puzzles or art projects, and they are important in building an early geometric sense of geometry. It's like when you expose to music, you build a musicality sense of music. But I think the training of Euclidean geometry is probably more than just go beyond than just playing. So I think when I was in middle school, this training of Euclidean geometry allows us to develop in skills like logical and deductive reasoning. I think that's important, not just in mathematics, in science, and I think it's everyday life and also in the way of viewing the world. It is something I think you may have other ways of acquiring this, but I think in schools, in secondary schools, I think it's definitely the best way to teaching this skill in a profound way. I think. So I support that you should be revived.
So I'm glad also to have heard from you that in some good schools they can do it quite early, still in China.
Yes, but maybe sometimes too early is also a problem.
Too early. Okay. So Professor Xu, perhaps you have experience, of course, both with the Chinese system and the system in the United States. How to compare them? How early can it be done in either of these systems?
Actually, I don't know how U.S. kids start to learn geometry. But in China, I think, at least in my case, I was learning it when I was a secondary school student. But I think it was a very important step for the student to build up their logical thinking, logical way of thinking. I think I cannot imagine any other way which I find more effective to build up a logical way of thinking than doing geometry.
Okay, very good. So Lawrence, of course, your children were going through this system, so you might be able to tell us some.
I guess in the U.S., I think students learn about Euclidean geometry when they're 10th grade. And many students find the first time learning about proof to be quite difficult. And I suppose with some of the more difficult problems, you may need to draw extra line, extra circle in order to see the geometric insight to the problem. And I think often that are quite difficult for the students.
I see. Okay. So we have gathered some the collection of experience from different systems. Now let me go to a question that is also very nice for this panel. So in the university curriculum, students in pure mathematics and applied mathematics normally take very different courses. So how should the curriculum be revised to respond to the fast-changing role of mathematics, both in the real world and in the eyes of the public? Anybody who wants to volunteer first opinion?
I can say. So, yes, I think traditionally you're very right that there is this strong distinction after a first year in common between the more applied curriculum and the more theoretical curriculum. This division is weakening enormously. So I believe that there is not such a serious distinction anymore in terms of education in particular between the more theoretical and the more applied side, in the sense that, for example, modern machine learning needs theoretical guarantees that don't exist today. So here there are very important open questions in theoretical mathematics that no machine learning person can on its own solve if she or he doesn't have a background in theoretical mathematics. So I would encourage very much to weaken the boundaries between these two areas in order for students to be able to take parts on this in both sides. Also, the theoretical mathematicians have to learn computational instruments and tools in a stronger way.
Yeah, great. So would it be a good idea, anyone can answer me, that you revise the curriculum so that you have a minor project, if you are in pure mathematics, that you do it in applied and vice versa? Would that be a good idea? And what kind of projects would that be possible?
Yes, I think especially in this differential geometry course, maybe I think something related to applications to engineer or physics. I think it would be a wonderful thing. I think even in textbooks, maybe there should be some inclusion of that. That's not just for the benefit of the applied majors, but also help the pure students understand the things better, I think more broader.
Was that done at Berkeley, or was not
Unfortunately,
quite?
no. So I think it should be something that should be done, I think.
So Cheng Yao, so what do you think?
I think in Peking University, where I did my bachelor degree, I think for the first 1.5 years, every student took exactly the same class. So there was no distinction between.
I see.
And then by the fourth semester, people can choose like which direction they want to go.
I see.
And but I think people first, for applied math major, they build up a pretty solid.
Okay, very good.
Yeah,
so someone eventually doing applied mathematics will have learned abstract algebra and maybe even Galois theory or something like this.
I think abstract theory, Galois theory is not there, but
group theory or maybe some.
Yeah, some group theory.
Some idea of abstract algebra.
Yeah, some topology.
So that's very good.
Yeah.
So how's that done at UIC?
Yeah, I'm afraid that, like for instance, things like linear algebra, applied students often more emphasizing things like solving system of equations and matrix manipulation.
Yes.
Yeah, rather than the abstract vector space and things like that. I think it would be good to have both, really. I think really, for pure mathematics, people studying pure mathematics, I think it's good to have some appreciation of application of mathematics.
I agree completely.
Like graph theory or like
I
optimization
mean, the classical thing, physics and things like that. I think it's.
But there is also, if I can comment a second on this,
please.
So there is also, I think it is a bit unfair to say that the applied mathematician is close to the reality and the others are not. I think that we should be able to understand that there is a distance to reality, right? And my distance is closer than yours, right?
Yes.
But you're not so far away either from reality, right?
Yeah.
Yeah, well, I guess pure and applied mathematicians need each other. For inspiration and for sources of problems and so on. And maybe the age of digital revolution gives some impulse and some motivation for revision or for reforms in the curricula, so that the future generation of students of mathematics can learn different aspects of mathematics, pure, applied, and in the mathematical sciences. So in view of the shortage of time, let's stop here.
Thank you so much for the wonderful sharing. And may I invite all guests on stage to step forward for a group photo. So let's give all our guests another big round of applause. Let's take a look at our photographer in front of you. Thank you so much. Please be seated. So it is the finale of today's symposium, and tomorrow's topic will cover physics and computer science, and I hope you enjoyed today's program as much as I did. And for those who will be joining the welcome dinner, please remember to gather in front of the entrance now, because we have arranged a shuttle bus for you. See you around during the Future Science Prize Week. Thank you.